Section 1 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please contact LibriVox.org. Recording by Peter Yearsley. Preface. The textbook now offered to the public has been prepared to meet the existing want of a practical handy-book for the assayer. To mining men, the word assaying conveys a sufficiently clear meaning, but it is difficult to define. Some writers limit it to the determination of silver and gold, and others imagine that it has only to do with furnace work. These limitations are not recognized in practice. In fact, assaying is becoming wider in its scope, and the distinction between assayers and analysts will in time be difficult to detect. We have endeavoured rather to give what will be of use to the assayer than to cover the ground within the limits of a faulty definition. At first our intention was to supply a description of those substances only which have a commercial value, but on consideration we have added short accounts of the rarer elements, since they are frequently met with and occasionally affect the accuracy of an assay. Under the more important methods we have given the results of a series of experiments showing the effect of varying conditions on the accuracy of the process. Such experiments are often made by assayers, but seldom recorded. Statements like those generally made that this or that substance interferes are insufficient. It is necessary to know under what conditions and to what extent. Students learning any particular process cannot do better than repeat such a series of experiments. By this means they will at the same time acquire the skill necessary for performing an assay, and a confidence in their results based upon work under different conditions. The electrolytic method of copper assaying, given under copper, is a modification of Lacau's. It was introduced by us into the offices of the Rio Tinto Copper Company, and has been in use for many years with success. This modification is now employed in copperworks in Spain, Germany, and England, and is used in place of the dry assay for the commercial valuation of copper ores. We have adhered to the gram and the cc as the units of weight and volume. Those who prefer working with grains and grain measures can use the figures given multiplied by 10. For example, when 1 gram is mentioned, 10 grains should be used, and 10 grain measures take the place of 1 cc. It is not advisable to mix the two systems, as by using gram weights and grain measures. We have intentionally, to a large extent, omitted to mention the names of those who have originated or modified the various processes. The practice of naming a process after its discoverer has developed of late years and is becoming objectionable. It is a graceful thing to name a gas burner after Bunsen, or a condenser after Liebig. But when the practice has developed so far that one is directed to Finkenerize a residue, or to use the Reichert-Meisel-Volney process, it is time to stop. We are indebted to the standard works of Allen, Crookes, Fresenius, Lunge, Mitchell, Percy, and Sutton, and wish to express our sense of special indebtedness to Mr. Richard Smith of the Royal School of Mines. One or two of the illustrations are taken from Mr. Sexton's excellent little book on qualitative analysis. Our obligation to some others is mentioned in the text. Finally, we have to thank for assistance in the experimental work Messrs. Bailey, Beswick, Clark, Grant, Higgins, and Smith. The authors, Camborne, November 1889. Chapter 1. Introductory. Assaying has for its object the determination of the quantities of those constituents of a material which add to or detract from its value in the arts and manufactures. The methods of assaying are mainly those of analytical chemistry, and are limited, by various practical considerations, to the determination of the constituents of a small parcel, which is frequently only a few grains, and rarely more than a few ounces, in weight. From these determinations calculations are made, which have reference to a mass of material of perhaps hundreds of tons. But in all cases, whether the mass under consideration be large or small, whether the material be obtained by mining, grown, or manufactured, the assayer is supposed to receive a small quantity called the sample, which is or ought to be the exact counterpart of the mass of material that is being dealt with. The taking and making of this sample is termed sampling, and the men whose special work it is to select such samples are the samplers. But although sampling is thus distinct from assaying, the assayer should be familiar with the principles of sampling, and rigorous in the application of these principles in the selecting from the samples sent to him that smaller portion upon which he performs his operations. Sampling. In the case of gases there is absolutely no trouble in mixing. The only difficulty is in drawing off a fair sample where, as in flues, the body of the gas is in motion and varies a little in composition from time to time. In this case care must be taken to draw off uniformly a sufficient volume of the gas during a prolonged period. Any portion of this larger volume may then be taken for the analytical operation. In the case of liquids, which mix more or less easily, and this class includes metals, etc., in the state of fusion, more or less severe agitation, followed by the immediate withdrawal of a portion, will yield a fairly representative sample. In the case of solids, the whole mass must be crushed, and, if not already of fairly uniform quality, mixed before sampling can take place. Most of the material which a sampler is called upon to deal with is, however, in a more or less divided state and fairly uniform. In practice it is assumed that 5% of the whole, note 1/20th, end note, if taken in portions of equal weight and at frequent and regular intervals, will represent the mass from which it was taken. Taking a heap of ore, A, and selecting 1 out of every 20 spade, bag, barrow, or waggonfuls, according to the quantity of stuff in the heap, there is obtained a second heap, B, containing 1/20th of the stuff of the heap A. If we crush the stuff in B until this heap contains approximately the same number of stones as A did, which means crushing every stone in B into about 20 pieces, B will become the counterpart of A. Selecting in the same manner 5% of B, there is got a third heap, C. This alternate reduction and pulverizing must be carried on until a sample of suitable size is obtained. This may be expressed very clearly thus: A equals 1000 tons of rocks and lumpy ore, B equals 50 tons of rough stones, 1/20th of A, C equals 2.5 tons of small stones, 1/20th of B, D equals 0.125 tons of coarse powder, 1/20th of C. If the material to be sampled is already a dry powder, 5% of it should be heaped in a cone, each lot being added on the apex of the cone already formed, so that it may distribute itself by falling evenly in all directions. When the cone is completed, convert it into a low frustrum of a cone by drawing stuff uniformly and in a direct line from the centre to the circumference. Draw 2 diameters at right angles to each other, and reserving any 2 alternate quarters, reject the others. Mix and form another cone, and proceed until a sample is got of the bulk required. Note: Figure 1 illustrates side views of a cone, a partly reduced cone with some of the material moved from the centre out toward the sides, and the side view of a frustrum, effectively a disc with a sloping outer edge. There is also a plan of the frustrum divided into 4, with opposite sectors shaded, to be discarded. End note. This is the usual plan, and all samples should be tested in this way when the stuff is fine enough to fall evenly down the sides of a cone. Samples as they reach the assay office are seldom in a fit state for the work of the assayer. They are generally too coarse, and ought always to be more than he wants for any particular determination. The portion he requires should never be taken at haphazard. The sample must be reduced systematically to the quantity required. 1. If the sample is a liquid, it is sufficient to shake the bottle and take out a measured or weighed quantity for the assay. 2. If a liquid with a solid in suspension, measure the whole of it, filter, make up the filtrate with the wash water or water to the original bulk. Assay it. dry and weigh the residue, and make a separate assay of it. 3. If of a creamy consistency, free from heavy particles, mix well, spread out evenly on a glazed tile, take up equal portions at equal distances, mix and assay. 4. If a mud of coarse and fine particles, or of particles of unequal density, weigh and transfer to a porcelain dish, or weigh in the dish. Dry at 100 degrees centigrade. Weigh. Treat the residue as a solid capable of being powdered. 5. If a solid capable of being powdered, or already powdered, heap up into a cone, flatten with a spatula, divide along 2 diameters at right angles, and carefully reject the whole of 2 alternate quarters, brushing away any fine powder. Mix the other quarters and repeat if necessary. For small quantities a fine state of division is essential. 6. If a solid with metallic particles, powder and pass through a sieve, the metallic particles will not pass through. Weigh both portions and assay separately. Sifting should be followed by a very thorough mixing. 7. If a metal or alloy in bar or ingot, clean the upper surface of the bar and bore through the bar. Use the borings. If the ingot or bar is small, cut it through and file the section. Filings must be freed from fragments of the file by means of a magnet, and from oil, if any be present, by washing with a suitable solvent. Note: ether or carbon bisulfide. End note. Where practical, metals and alloys are best sampled by melting and granulating. The student must carefully avoid any chance of mixing dirt or particles of other samples with the particular sample which he is preparing. 1 ore should be done at a time, and when finished it should be labelled and wrapped up, or bottled, before starting on a fresh sample. When an ore requires to be very finely ground in an agate mortar, it is often advisable to mix with a little pure alcohol and rub until free from grit. Dry at 100 degrees centigrade and mix before weighing. When an assay is required of a quantity of ore made up of parcels of different weights and quality, each parcel should be separately sampled, and parts of each sample, bearing to each other the same proportion by weight as the original parcels, should be taken and mixed. For example, a lot of ore is made up of one parcel of A, 570 tons, one of B, 180 tons, and another of C, 50 tons. A sample representing the whole may be got by mixing 57 parts of a sample of A with 18 parts of a sample of B and 5 parts of a sample of C. A bruising plate, like that in Figure 2, is convenient for general office work. Note: Figure 2 shows a rectangular wooden table with a thick solid block of wood on the top of the table. On the top of the block of wood is a slab of metal fashioned as a shallow tray, open at one end, and tilting on a hinge attached to the wooden block, so ore can tip out of the open end. There is a flat-faced metal hammer resting on the table also. End note. The slab is of cast iron, about an inch thick. It is firmly supported on a solid block of wood and pivoted for convenience in emptying. The bruising hammer is steel-faced, about 4 inches square and 1½ inches thick. The block is firmly fixed to a small table or trestle, so that the slab is about 2 feet 6 inches from the ground. The slab is cleaned and the sample collected with the help of a stiff-haired brush. Drying. Determination of moisture. In practice, the moisture is generally determined by the samplers, and the proportion is specified in grains per pound on the label attached to the sample when it reaches the assay office. The method adopted is usually to dry 1 pound (= 7,000 grains) of the ore in a frying pan heated over a gas flame, or in an ordinary oven, until a cold bright piece of metal or glass is no longer damped when held over it. The loss of weight in grains = moisture. Properly, however, the work should be done by the assayer, if only for the following reason. It is assumed that the dry ore of the sampler and of the assayer are the same thing. According to the nature of the ore, this may or may not be the case. The assayer, however, uses the sample which he has dried for his moisture determination. as the dry ore on which he makes his other assays, and no variation in moisture would influence the other and more important determinations. Some ores are sent to the smelter with from 5 to 15% of adherent water. In these cases it is best to spread out the sample and, taking equal portions fairly at regular intervals, weigh into a Berlin dish 20 grams. This should then be dried over a sand bath, or, if the ore is likely to be injured by excess of heat, over a water bath until the weight is constant. The loss of weight multiplied by 5 gives the percentage of water present. Example: weight of dish plus wolfram 32.67 grams, weight of dish 12.67 grams. Therefore, weight of wolfram equals 20 grams. Weight of dish plus wolfram 32.67 grams. Weight of dish dried 30.15 grams. Weight of water 2.52 grams. 2.52 times 5 equals 12.6. Moisture 12.6%. There are other ores which are not apparently wet, but in the state called air-dried. It is easier to take fair samples of these, and consequently it is not necessary to use so large a quantity as 20 grams. But with a smaller quantity, extra precautions must be taken. All dry solids at ordinary temperatures absorb moisture from the air. The amount varies with the nature of the material and with the quantity of surface exposed. Light, bulky powders absorb more than heavy ones, because of the greater condensing surface. It is on this account that it is well to weigh substances which have been dried between close-fitting watch glasses. The method of determining moisture is to weigh out into the glasses 5 grams of ore and dry in the water oven until there is no further loss of weight. On taking the glasses out of the oven, they should be at once closed, the clip put on, and, after cooling in a desiccator, weighed. If after a second trial the loss is the same, or only increased by a milligram, the determination is finished. Sometimes it may be advisable to dry 10 grams, in which case multiplying the loss by 10 will give the percentage. The dried ore should be transferred to a weighing tube and reserved for the subsequent determinations. The weighing tube with the ore must be marked and kept in a desiccator. Most ores and inorganic substances can be dried, and their moisture determined by the loss in this way. When, however, the substance contains another somewhat volatile ingredient, it is exposed over sulphuric acid in a desiccator for 2 days. Note: if in vacuo, all the better. End note. And the loss determined. Moisture in dynamite should be determined in this way. When water is simply mechanically mixed with a substance, it presents but little difficulty. The combined water is a different matter. Slaked lime, even when perfectly dry, contains much water, and if the water of soda crystals were separated and frozen, it would occupy a volume equal to that of the original crystals. Perfectly dry substances may contain much water, and this combined water is retained by different materials with very unequal vigour. Sodium sulfate and sodium phosphate crystals lose water even when exposed under ordinary conditions to dry air. Soda crystals, when heated, melt, and at moderate temperature give off their water with ebullition. The temperature at which all the water is given up varies with each particular salt. The actual determination of the water in each case will require somewhat different treatment. Such determinations, however, are seldom required, and from a practical point of view this combined water causes no trouble. In assaying ores, we term moisture all water which is lost by exposure in a water oven at 100 degrees centigrade, and the dry ore is the ore which has been dried at this temperature. No advantage, but rather endless confusion, would be caused by varying the temperature with the object of estimating the whole of the water which a hydrated salt may contain. The results of the assay of the other components should be calculated on the dry ore. One advantage of this is obvious. The dry ore has a constant composition, and the results of all assays of it will be the same, no matter when made. The moisture, however, may vary from day to day, and would be influenced by a passing shower of rain. It is well to limit this variability to the moisture by considering it apart, and thus avoid having the percentage, say of copper, rising and falling under the influence of the weather. In the case of certain salts, however, such as soda crystals and hydrated sulphate of copper, when these constitute the bulk of the substance to be assayed, it is as well to perform the assay on the moist, or at any rate air-dried, substance. Note: such substances are best dried by pressing between folds of dry filter paper. End note. It would be equally convenient to calculate on the substance dried at 100 degrees centigrade, but in this case it would be well, in order to avoid a somewhat shallow criticism, to replace the term moisture by the longer but equivalent phrase water lost at 100 degrees centigrade. Calculation and statement of results. By far the most generally convenient method of stating the results of an assay is that of the percentage, or parts in 100. And to avoid a needlessly troublesome calculation, it is well to take such a quantity of ore for each assay as, by a simple multiplication, will yield the percentage. In these calculations decimals are freely employed, and students should make themselves familiar with the methods of using them. Other methods of statement are in use, and have advantages in certain special cases. With bullion, the parts in 1,000 are given, and in those cases in which the percentage is very small, as in water analysis, it is convenient to report on parts in 100,000, or even on parts per million. These are easily got from the corresponding percentages by shifting the decimal point 1, 3, or 4 places to the right. Thus 92.5% is 925 per thousand, and 0.0036% is 3.6 per 100,000, or 36 per million. With ores of tin, silver, and gold, the result is stated as so many hundredweights, pounds, or ounces in the ton. With dressed tin ores, as they are sent to the smelter, the produce is given in hundredweights and quarters to the ton. The corresponding percentage may be obtained by multiplying by 5. Or inversely, if the percentage is given, the produce may be got by dividing by 5. A produce of 13.5 equals a percentage of 13.5 times 5 equals 67.5, and a percentage of 70.0 equals a produce of 70 divided by 5 equals 14. With tin ores as raised, in which the percentage is small, the reduction must be carried to pounds per ton. 1% equals 22.4 pounds to the ton. Consequently, if we multiply the percentage by 22.4, the produce will be given. Thus, if an ore contains 6.7% of oxide of tin, the produce is 6.7 times 22.4 equals 150 pounds. Note, or 1 hundredweight, 1 quarter, and 10 pounds. End note. To the ton. With gold and silver ores, the proportion of precious metal is small, and it is necessary to carry the reduction to ounces and pennyweights to the ton. And since gold and silver are sold by troy weight, while the ton is avoirdupois, it is of importance to remember that the ounces in the two systems are not the same. A ton contains 15,680,000 grains, which equal 653,333.3 pennyweights, or 32,666.6 ounces, troy. The following rules are useful. To get ounces, troy, per ton, multiply parts per 100,000 by 0.327. To get pennyweights per ton, multiply parts per 100,000 by 6.53. To get grains per ton, multiply parts per 100,000 by 156.8. Where liquids are being assayed, cubic centimetres are held to be equivalent to grams, and the usual method of statement is so many parts by weight in so many by measure. Where the statement is made as grams per litre or grains per gallon, there can be no doubt as to what is meant, and even if it be expressed in parts per 100,000, parts by weight in a measured volume must be understood, unless the contrary is expressly stated. In some cases, where the density of the solution differs greatly from that of water, the percentage by weight may be given, and in others, mixtures of 2 or more liquids, the percentages may be given by volume or by weight. as so many cc's in 100 cc's, or as so many grams in 100 grams, or even as so many grams in 100 cc's. In such cases it must be distinctly shown which method of statement is adopted. 1 grain per gallon means 1 grain in 70,000 grain measures, or 1 part in 70,000. Dividing by 7 and multiplying by 10 will convert grains per gallon into parts per 100,000. Inversely, dividing by 10 and multiplying by 7 will convert parts per 100,000 into grains per gallon. Grams per litre are parts per 1,000. Multiplying by 100 will give parts per 100,000, and multiplying by 70 will give grains per gallon. Among foreign systems of weights, the French is by far the best. Kilograms, 2.205 pounds, per quintal, 2,205 pounds, are parts per cent, and grams, 15.43 grains, per quintal are parts per 100,000. From the rule already given, grams per quintal may be converted into ounces to the ton by multiplying by 0.327. The German loaths per centner, note half an ounce avoirdupois to 100 pounds, end note, equal parts per 3,200. They are converted into parts per cent by dividing by 32, or into ounces troy per ton by multiplying by 10.208. In the United States, as a sort of compromise between the avoirdupois and metric systems, a ton is taken as 2,000 pounds. There too the custom is adopted of reporting the gold and silver contents of an ore as so many dollars and cents to the ton. In the case of gold, an ounce is considered to be worth $20.6718. With silver, the nominal value is $1.2929 per ounce, but frequently in assay reports it is taken as $1. The practice is objectionable. The prices of metals vary with the fluctuations of the market, and if the assayer fixed the price, the date of his report would be all important. If, on the other hand, he takes a fixed price which does not at all times agree with the market one, it leaves a path open for the deception of those unacquainted with the custom. American dollars on the ton of 2,000 pounds may be converted into ounces in the ton of 2,240 pounds by dividing by 1.1544 in the case of silver, and by 18.457 in the case of gold. Laboratory books and report forms. The record which the assayer makes of his work must be clear and neat, so that reference, even after an interval of years, should be certain and easy. One method should be adopted and adhered to. Where there are a large number of samples, 3 books are required. Sample book. This contains particulars of the sample, marks, etc., which are entered by the office clerk as they arrive. He at the same time puts on each sample the distinguishing number. Illustration. Example of a page of sample book. Reader's note. There are 4 columns: date, number, sample, and remarks. End reader's note. Date February the 1st, number 482, sample tough copper, remarks for arsenic. February the 2nd, number X, sample piece of metal, remarks for nickel and copper. February the 2nd, number 483, sample tough copper. February the 2nd, number 73, silver precipitate, 4 casks, 2400 weight 1/4, remarks with letter. February the 2nd, number 494, purple ore 200 tons. February the 2nd, number 1JT, lead ore 1JT, from Corsica. February the 2nd, 2JT, lead ore 2JT. End of illustration. Laboratory book. This is the assayer's notebook, in which he enters clearly the particulars of his work, the results obtained, as well as how these results were arrived at. The calculations should be done on scrap paper and should not be entered, although of course detail enough must be shown to enable the results to be recalculated. The assay book. This is the official book, and is a combination of the sample and laboratory books. It corresponds with the report forms. Without being loaded with detail, it should contain sufficient to characterize each sample. Illustration: example of page of assay book. Under description of sample there are 3 columns: date, material, and weight, given in tons, hundredweights, quarters, and pounds. Then columns for number, water lost at 100 degrees centigrade, assay on the dry material, and date reported. End of illustration. When the number of samples is small, the sample book may be omitted, and the entries made in the assay book as the samples arrive. Report forms. These should entail as little writing as possible in making out the report. For general purposes, the form given on page 12 is useful. Reader's note. The assay note gives the address of the assay office, for example, Assay Office, the Mining School, Camborne, Cornwall, a line for the date, 2 lines for extra notes, then description of sample, water lost, and assay on the dry material. End of illustration. The quantity of substance to be taken for any particular assay depends largely upon the method of assay adopted. There are, however, some general considerations which should be remembered, and some devices for simplifying the calculations which should be discussed. The smaller the percentage of the substance to be determined, the larger should be the amount of the ore taken. The following table will give a general idea as to this. Percentage of the substance to be determined: between 100 and 10. Amount of ore, etc., to be weighed: 1 gram. Percentage to be determined: between 10 and 5. Amount of ore: 2 grams. Percentage to be determined: between 5 and 1. Amount of ore: 5 grams. Percentage to be determined: between 1 and 0.1. Amount of ore: 10 grams. Percentage to be determined: between 0.1 and 0.01. Amount of ore: 20 grams. The rougher the method of assay adopted, the larger should be the quantity of ore taken. If the degree of accuracy attainable with the methods and instruments at the assayer's service is known, it is easy to calculate what quantity should be taken for any particular case. If the results are good within 0.001 of a gram, then taking 1 gram of ore we can report within 0.1%, or if they are good within 0.0002 gram, taking 20 grams of ore we can report within 1 part per 100,000, or very closely within 6½ pennyweight to the ton. If it is wished to be yet more particular in reporting, larger quantities must be taken. The difficulty of manipulating very small or very large precipitates, etc., must be borne in mind. So too must the fact that the greater the weight of the final product of an assay, the less, as a rule, is the percentage error. The distinction between absolute and percentage error, often overlooked, is important. If 0.5 of a gram of silver be cupelled with 20 grams of lead, there may be obtained a button of 0.495 of a gram. The absolute loss is 0.005 of a gram, and this equals 1% of the silver present. Similarly, cupelling 0.1 of a gram, the resulting button may be 0.098. The absolute loss is only 0.002 of a gram, but this equals 2% of the silver present. In the same way, the student should see that the two results, 91.5% and 92.0%, are really more concordant than the results 9.1% and 9.2%. A device often adopted in practice where a large number of assays of one kind are made, and the report is given as so many ounces or pounds to the ton, is that known as the assay ton. The assay ton may be any arbitrary and convenient weight, but its subdivisions must bear to it the same relation as pounds and ounces bear to the actual ton. On the other hand, in a laboratory where many kinds of work are performed, different sets of weights of this kind would only tend to confusion, even if they were not unnecessary. With a set of gram weights and its subdivisions, anything may be done. If it is desired to report as pounds to the ton, then, since there are 2,240 pounds to the ton, A weight of 2.240 grams may be taken as the assay ton, and each 0.001 of a gram yielded will equal 1 pound. Or 22.4 grams may represent the ton, and each 0.01 of a gram a pound. Similarly, since there are 32,666.6 ounces Troy to the ton, if we take 32.6667 grams as the assay ton, each 0.001 of a gram will equal 1 ounce to the ton. In some cases it may be convenient to have, in addition to the usual gram weights, one or other of the assay tons mentioned above, but generally it is better to work on a purely decimal system, and convert when required into ounces per ton, etc., either by actual calculation or by reference to a set of tables. End of section 1. Section 2 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 2. Methods of Assaying. Dry Gravimetric Methods. The methods of assaying are best classed under two heads, gravimetric and volumetric, in the former of which the final results are weighed, whilst in the latter they are measured. A commoner and older division is expressed in the terms much used in practice, wet assays and dry assays. Wet assays include all those in which solvents, etc., liquid at the ordinary temperature, are mainly used, and dry assays those in which solid reagents are almost exclusively employed. Dry assays form a branch of gravimetric work, and we shall include under this head all those assays requiring the help of a wind furnace. Wet assays, as generally understood, would include not only those which we class as wet gravimetric assays, but also all the volumetric processes. Gravimetric methods aim at the separation of the substance from the other matters present in the ore, so that it may be weighed, and therefore they must yield the whole of the substance in a pure state. It is not necessary that a metal should be weighed as metal. It may be weighed in the form of a compound of definite and well-known composition. For example, 1 part by weight of silver chloride contains, and if pure always contains, 0.7527 of a part of silver, and a quantity of this metal can be as exactly determined by weighing it as chloride as by weighing it in the metallic state. But in either case the metal or its chloride must be pure. Exact purity and complete separation are not easily obtained, and methods are used which are defective in one or both of these respects. It is well to note that an impure product increases the result, whilst a loss of the substance decreases it, so that if both defects exist in a process, they tend to neutralize each other. Of dry methods generally, it may be said that they neither give the whole of the substance nor give it pure, so that they are only calculated to show the amount of metal that can be extracted on a manufacturing scale, and not the actual quantity of it present. Their determinations are generally rough and always low. The gold and silver determinations, however, will compare very favourably with any of the other processes for the estimation of these metals in their ores. The calculation of the results for gravimetric assay has already been referred to. If the result is to be stated as percentage, it may always be done by the following rule: multiply the weight of the substance got by the percentage of metal it contains, and divide by the weight of ore taken. Gravimetric methods are divided into 3 groups: 1. Mechanical separations, 2. Dry methods, and 3. Wet methods. Mechanical separations. Under this head are classed the method of assaying tin ores, known as vanning, and the amalgamation assay for gold. A set of sieves to determine the relative proportion of powders of different degrees of fineness is sometimes useful. A set with 10, 20, 40 and 80 meshes to the inch is convenient. Dry assays. An important distinction between wet and dry methods of assaying is that in the former the substance is got into the liquid state by solution, whilst in the latter fusion is taken advantage of. The difference between solutions and fusion is easily illustrated. A lump of sugar heated over a candle flame melts or fuses. Suspended in water, it dissolves. Many substances which are insoluble or infusible of themselves become soluble or fusible when mixed with certain others. Thus, in this way, solution is got with the aid of reagents, and fusion with the help of fluxes. For example, lead is insoluble in water, but if nitric acid be added, the metal rapidly disappears. It is convenient, but somewhat inaccurate, to say that the acid dissolves the lead. If the lead be acted on by nitric acid alone, without water, it is converted into a white powder, which does not dissolve until water is added. In this case it is obvious that the water is the solvent. The function of the acid is to convert the lead into a soluble compound. Fluxes may act as true solvents. Fused carbonate of soda dissolves baric carbonate, and perhaps in many slags true solution occurs, but in the great majority of cases a flux is a solid reagent added for the purpose of forming a fusible compound with the earthy or stony minerals of the ore. Few of the minerals which occur in the gangue of an ore are fusible, and still fewer are sufficiently fusible for the purposes of the assayer. Consequently, the subject is one of importance, and it ought to be treated on chemical principles. An idea of the composition of some of the more frequently occurring rocks may be gathered from the following table, which represents rough averages. Sandstone, grit, quartzite, etc. 80 to 100% silica. Granite, gneiss, quartz porphyry, fire clay, etc. 70 to 75% silica, 13 to 20% alumina, 2% oxide of iron, 2% lime and magnesia, 5 to 8% alkalis, less in fire clay. Mica schist, 65% silica, 18% alumina, 5% oxide of iron, 3% lime and magnesia, 3% alkalis. Trachyte, cyanide, 60% silica, 17% alumina, 7% oxide of iron, 4 to 7% lime and magnesia, 6 to 9% alkalis. Clay slate, 60% silica, 18% alumina, 10% oxide of iron, 8% lime and magnesia, 3% alkalis. Diorite, 54% silica, 17% alumina, 12% oxide of iron, 9% lime and magnesia, 3% alkalis. Hornblende rock, 50% silica, 18% alumina, 15% oxide of iron, 12% lime and magnesia, 3 to 4% alkalis. Brick clay, 50% silica, 34% alumina, 8% oxide of iron, 6% lime and magnesia. China clay, 47% silica, 39% alumina. Basalt, dolerite, etc. 50% silica, 15% alumina, 15% oxide of iron, 16% lime and magnesia, 3% alkalis. Serpentine, 44% silica, 44% lime and magnesia. Chalk, limestone, dolomite, etc. 45 to 55% lime and magnesia. Silica itself and the silicates of alumina, of lime, and of magnesia are practically infusible. The silicates of soda, of potash, and of iron are easily fusible if the base, soda, potash, or oxide of iron, be present in sufficient quantity, and if, in the case of the iron, it is present mainly as lower oxide. Note ferrous silicate. End note. The addition of lime, oxide of iron, or alkali to silicate of alumina results in the formation of a double silicate of alumina and lime, or of alumina and iron, etc., all of which are easily fusible. Similarly, if to a silicate of lime we add oxide of iron, or soda, or even alumina, a fusible double silicate will be formed. Thus, lime, soda, oxide of iron, and clay are fluxes when properly used. But since lime, clay, and oxide of iron if there be any tendency to form peroxide, are of themselves infusible, any excess of these fluxes would tend to stiffen and render pasty the resulting slag. So too soda, which is a very strong base, may act prejudicially if it be in sufficient excess to set free notable quantities of lime and magnesia, which but for that excess would exist in combination as complex fusible silicates. There are many minerals which with but little soda form a glass, but with more yield a lumpy scoriaceous mass. There are many minerals too which are already basic, note, for example, calcite, end note, and which when present demand either a less basic or an acid flux, according to the proportions in which they exist. For purposes of this kind, borax or glass or clay with more or less soda may be used, and of these borax is by far the most generally useful. An objection to too basic a slag, and a very important one, is the speed with which it corrodes ordinary crucibles. These crucibles, consisting of quartz and clay, are rapidly attacked by lime, soda, and bases generally. In considering what is and what is not a good slag, certain chemical properties are of importance. If a mixture of many substances be fused and allowed to solidify in a crucible, there will be found some or all of the following. At the bottom of the crucible, a button of metal. Resting on this, a spice, then a regulus, next a slag made up of silicates and borates and metallic oxides, and lastly, on the top, another layer of slag, mainly made up of fusible chlorides and sulfates. In assaying operations, the object is generally to concentrate the metals sought for in a button of metal, spice, or regulus, and to leave the earthy and other impurities as far as possible in the slag. Whether there be one or two layers of slag is a matter of indifference, but the chemical action of the lower layer upon the spice or regulus or metal is of great importance. Note: in relation to one or two layers of slag being a matter of indifference, there is an exception to this, as when the slag is liable to be acted on when exposed to the air and to the gases of the furnace. In this case, a layer of fused common salt floating on the slag, so as to protect it from the air and furnace gases, is a distinct advantage. End note. A regulus is a compound of one or more of the metals with sulphur. It is usually brittle, often crystalline, and of a dull, somewhat greasy lustre. It is essential that the slag, when solid, shall be so much more brittle than the regulus that it shall be easy to crumble and remove it without breaking the latter, and it must not be basic. The effect of fusing a regulus with a basic slag is well seen when sulphide of lead is fused with carbonate of soda. The result is a button of metal, more or less pure, and a slag containing sulphides of lead and sodium. And again, if sulphide of lead be fused with an excess of oxide of lead, a button of lead will be got, and a slag which is simply oxide of lead, with whatever it may have taken up from the crucible. Or if a sufficient excess has not been used, oxide of lead mixed with some sulphide. When, as is most frequently the case, the desire is to prevent the formation of regulus, these reactions may be taken advantage of, but otherwise the use of a flux having any such tendency must be avoided. A good slag, from which a regulus may be easily separated, may be obtained by fusing, say, 20 grams of ore with borax, 15 grams, powdered glass, 15 grams, fluorspar, 20 grams, and lime, 20 grams. By quenching the slag in water as soon as it has solidified, it is rendered very brittle. Sulphide of iron formed during an assay will remain diffused through the slag, instead of fusing into a button of regulus, if the slag contains sulphide of sodium. The same is true of other sulphides if not present in too great a quantity, and if the temperature is not too high. Spices. Reader's note: spelt S-P-E-I-S-E-S. End reader's note. Spices are compounds of a metal or metals with arsenic. They are chiefly of interest in the metallurgy of nickel, cobalt, and tin. They are formed by heating the metal or ore in covered crucibles with arsenic and, if necessary, a reducing agent. The product is fused with more arsenic under a slag consisting mainly of borax. They are very fusible, brittle compounds. On exposure to the air at a red heat, the arsenic and the metal simultaneously oxidize. When iron, cobalt, nickel, and copper are present in the same spice, they are eliminated in the order mentioned. Slags from which metals are to be separated should not be too acid, at least in those cases in which the metal is to be reduced from a compound, as well as separated from earthy impurities. Where the object is simply to get a button of metal from a substance in which it is already in the metallic state, but mixed with dross, made up of metallic oxides, such as those of zinc or iron, from which it is desired to separate it, an acid flux like borax is best, or if the metal is easily fusible, and there would be danger of loss of metal by oxidation or volatilizing, it may be melted under a layer of resin or fat. Common salt is sometimes used with a similar object, and is often useful. Under certain conditions, however, it has a tendency to cause the formation of volatile chlorides, with a consequent loss of metal. In the great majority of cases, the fusion of the metal is accompanied by reduction from the state of oxide. In these, the slag should be basic. It is not easy to reduce the whole of a reducible oxide, say oxide of copper or of iron, from a slag in which it exists as a borate or silicate. There should be at least enough soda present to liberate it. When the object is to separate one metal, say copper, without reducing an unnecessary amount of another, iron, at the same time, a slag with a good deal of borax is a distinct advantage. The slag will then probably not be free from copper, so that it will be necessary to powder and mix the slag with some soda and a reducing agent, and to again fuse the slag in order to separate this residual metal. In all those cases in which the slag retains an oxide of a heavy metal, this cleansing of the slag is advisable, and in the case of rich ores, necessary. Slags containing sulphides are especially apt to retain the more easily reducible metals. The following are the ordinary and most useful fluxes. Soda. The powdered bicarbonate, sold by druggists as carbonate of soda, is generally used. It gives off its water and excess of carbonic acid readily and without fusion. Where the melting down is performed rapidly, the escaping gas is apt to cause trouble by frothing, and so causing waste of the material. Ordinary carbonate of soda, when hydrated, soda crystals, melts easily and gives off its water with ebullition. It is unfit for use in assaying, but when dried it can be used instead of the bicarbonate. 1 part of the dried carbonate is equivalent to rather more than 1½ parts of the bicarbonate. From 2 to 4 parts of the flux are amply sufficient to yield a fluid slag with 1 part of earthy matter. This statement is also true of the fluxes which follow. Borax is a hydrated biborate of soda, containing nearly half its weight of water. When heated, it swells up, loses its water, and fuses into a glass. The swelling up may become a source of loss in the assay by pushing some of the contents out of the crucible. To avoid this, fused or dried borax may be used, in which case a little more than half the amount of borax indicated will suffice. Borax will flux almost anything, but it is especially valuable in fluxing lime, etc., and metallic oxides, as also in those cases in which it is desired to keep certain of the latter in the slag and out of the button of metal. Oxide of lead, in the form of red lead or litharge, is a valuable flux. It easily dissolves those metallic oxides which are either infusible or difficultly fusible of themselves, such as oxides of iron or copper. The resulting slag is strongly basic and very corrosive. No crucible will long withstand the attack of a fused mixture of oxides of lead and copper. With silicates also, it forms very fusible double silicates, but in the absence of silicates and borates it has no action upon lime or magnesia. Whether the lead be added as litharge or as red lead, it will exist in the slag as monoxide, litharge. The excess of oxygen of the red lead is thus available for oxidizing purposes. If this oxidizing power is prejudicial, it may be neutralized by mixing the red lead with 1% of charcoal. Glass. Broken beakers and flasks, cleaned, dried and powdered, will do. It should be free from lead. Fluor. Fluorspar as free as possible from other minerals, powdered. It helps to flux phosphate of lime, etc., and infusible silicates. Lime should be fresh and powdered. It must not be slaked. Powdered white marble, carbonate of lime, will do, but nearly double the quantity must be taken. 1 part of lime produces the same effect as 1.8 parts of the carbonate of lime. Tartar and black flux are reducing agents as well as fluxes. The black flux, which may be obtained by heating tartar, is a mixture of carbonate of potash and charcoal. Reducing agents. The distinction between reducing agents and fluxes, too often ignored, is an important one. Fluxes yield slags. Reducing agents give buttons of regulus or of metal. The action of a reducing agent is the separation of the oxygen or sulphur from the metal with which it is combined. For example, the mineral anglicite, lead sulphate, is a compound of lead, sulphur and oxygen. By carefully heating it with charcoal, the oxygen is taken away by the charcoal, and a regulus of lead sulphide remains. If the regulus be then fused with metallic iron, the sulphur is removed by the iron, and metallic lead is left. The charcoal and the iron are reducing agents. But in defining a reducing agent as one which removes oxygen or sulphur from a metallic compound so as to set the metal free, it must be remembered that sulphur itself will reduce metallic lead from fused litharge, and that oxygen will similarly set free the metal in fused lead sulphide. There is no impropriety in describing sulphur as a reducing agent, but it is absurd to call oxygen one. Some confusion will be avoided if these substances, and those which are opposite to them in property, be classed as oxidizing and deoxidizing, sulphurizing and desulphurizing agents. Most oxidizing agents also act as desulphurizers. The deoxidizing agents most in use are the following. Charcoal. Powdered wood charcoal. It contains more or less hygroscopic moisture and about 3 or 4% of ash. The rest may be considered carbon. Carbon heated with metallic oxides takes the oxygen. At low temperatures it forms carbon dioxide, and at higher ones carbon monoxide. Other conditions besides that of temperature have an influence in producing these results, and as the quantity of charcoal required to complete a definite reaction varies with these, it should be calculated from the results of immediate experience rather than from theoretical considerations. Flour. Ordinary wheat flour is convenient in use. On being heated it gives off inflammable gases, which have a certain reducing effect, and a residue of finely divided carbon is left. It is likely to vary in the quantity of moisture it contains. 2 parts of flour should be used where 1 part of charcoal would be otherwise required. Tartar. This is crude hydric potassic tartrate. The purified salt, cream of tartar, may be used. On being heated it gives off inflammable gases, and leaves a residue formed of potassic carbonate mixed with finely divided carbon. 5 parts of tartar should be used in the place of 1 of charcoal. Anthracite or culm is a kind of coal containing 90% or more of carbon. It gives off no inflammable gas. It is denser and takes longer in burning than charcoal. Its reducing effect is little inferior to that of charcoal. Almost any organic substance can be used as a reducing agent, but it is well not to select one which melts, swells up, or gives off much water and gas when heated in the furnace. Potassic cyanide is an easily fusible and somewhat volatile salt, which when fused readily removes oxygen and sulphur from metallic compounds, and forms potassic cyanate or sulfocyanate, as the case may be. Commercial samples vary much in purity. Some contain less than 50% of the salt. For assaying, only the better qualities should be used. Iron is a desulfurizing rather than a deoxidizing agent. Iron is used in the form of rods, a ½ inch in diameter, or of nails, or of hoop iron. In the last case, it should be thin enough to be bent without difficulty. Wrought iron crucibles are very useful in the processes required for making galena assays. The chief oxidizing agents, which are also desulfurizers, are the following. Nitre, or potassic nitrate. This salt fuses very easily to a watery liquid. It oxidizes most combustible substances with deflagration, and thereby converts sulfides into sulfates, arsenides into arsenates, and most metals into oxides. In the presence of strong bases, such as soda, the whole of the sulphur is fully oxidized, but in many cases some arsenic is apt to escape, and to give rise to a peculiar garlic-like odour. The sulfates of soda and potash are thus formed, and float as a watery liquid on the surface of the slag. Red lead is an oxide of lead. About 1/4 of its oxygen is very loosely held, and hence is available for oxidizing purposes, without any separation of metallic lead. The rest of the oxygen is also available, but for each part of oxygen given off, about 13 parts of metallic lead are deposited. In silver assays, this power of readily giving up oxygen is made use of. The residual oxide, litharge, acts as a flux. Hot air is the oxidizing agent in roasting operations. The sulphur and arsenic of such minerals as mispickel and pyrites are oxidized by the hot air and pass off as sulphur dioxide and white arsenic. The metals generally remain in the form of oxide, mixed with more or less sulphate and arsenate. The residue may remain as a powdery substance, a calx, in which case the process of roasting is termed calcination, or it may be a pasty mass or liquid. In the calcination of somewhat fusible minerals, the roasting should be done at a low temperature to avoid clotting, arsenic and sulphur being with difficulty burnt off from the clotted mineral. A low temperature, however, favours the formation of sulphates, and these, if not removed, would reappear in a subsequent reduction as sulphides. These sulphates may be decomposed by a higher temperature towards the end of the operation. Their removal is rendered more certain by rubbing up the calx with some culm and re-roasting, or by strongly heating the calx after the addition of solid ammonic carbonate. In roasting operations, as large a surface of the substances as possible should be exposed to the air. If done in a crucible, the crucible should be of the Cornish type, short and open, not long and narrow. For calcinations, roasting dishes are useful. These are broad and shallow, not unlike saucers, but unglazed. In those cases in which the products of the roasting are liquid at the temperature used, a scorifier is suitable if it is desired to keep the liquid, but if the liquid is best drained off as quickly as it is formed, a cupel should be used. Reader's note: Figure 38. The scorifier illustrated is a wide, shallow, circular block tapering towards the base, with a deep circular depression in the top, perhaps 1/4 of the depth of the hole. Figure 5. A cupel is a block with a very shallow depression in the top surface. The depression in the top of the cupel is about 5 times as wide as it is deep in the centre. End reader's note. A scorifier is essentially a roasting dish, sufficiently thick to resist for a time the corrosive action of the fused metallic oxides it is to contain. The essential property of a cupel is that it is sufficiently porous to allow the fused oxide to drain into it as fast as it is formed. It should be large enough to absorb the whole of the liquid, and of course must be made of a material upon which the liquid has no corrosive action. Cupels do not bear transport well, hence the assayer generally has to make them, or to supervise their making. A quantity of bone ash is carefully mixed with water so that no lumps are formed, and the mixture is then worked up by rubbing between the hands. The bone ash is sufficiently wet when its cohesion is such that it can be pressed into a lump, and yet be easily crumbled into powder. Cupel moulds should be purchased. They are generally made of turned iron or brass. They consist of 3 parts: 1, a hollow cylinder; 2, a disc of metal; and 3, a piston for compressing the bone ash and shaping the top of the cupel. The disc forms a false bottom for the cylinder. This is put in its place, and the cylinder filled, or nearly so, with the moistened bone ash. The bone ash is then pressed into shape with the piston, and the cupel finished with the help of 3 or 4 smart blows from a mallet. Before removing the piston, turn it halfway round upon its axis, so as to loosen and smooth the face of the cupel. The cupel is got out by pressing up the disc of metal forming the false bottom. The removal is more easily effected if the mould is somewhat conical, instead of cylindrical, in form. The cupels are put in a warm place to dry for 2 or 3 days. A conveniently sized cupel is 1 1/4 inches in diameter and about 3/4 of an inch high. The cavity of the cupel is about 1/4 of an inch deep, and something of the shape shown in figure 5. There are 2 types of furnaces required, the wind and muffle furnaces. These are built of brick, fire brick of course being used for the lining. They are connected with a chimney that will provide a good draught. Figure 6 shows a section of the wind furnace, Figure 7 a section of the muffle furnace, and Figure 8 a general view of a group comprising a muffle and 2 wind furnaces, suitable for general work. Reader's note: Figure 6 is a side view of a wind furnace. At the bottom, a fire door leading into an ash pit, and above the back of the ash pit the small furnace cavity with the lid on top of it and a flue at the back, leading into a vertical chimney with a movable damper. Figure 7 is the side section of the muffle furnace. Again, ash pit at the bottom with a front door, and above it a furnace cavity. A narrow slot from the front of the oven gives access to the furnace cavity, and above it the muffle itself, again with access from the front and from the top. The flue again leads to a vertical chimney with a movable damper. Figure 8 shows a muffle furnace above a coke pit, and on each side of the muffle furnace, lower down, a wind furnace. End reader's note. When in operation, the furnaces are covered with iron-bound tiles. The opening under the door of the muffle is closed with a loosely fitting brick. The floor of the muffle is protected with a layer of bone ash, which absorbs any oxide of lead that may be accidentally spilt. The fire bars should be easily removable. Few tools are wanted. The most important are some cast iron moulds, tongs, stirrers for calcining, and light tongs of a special form for handling scorifiers and cupels. Note: see the chapter on silver. End note. The coke should be of good quality. The formation of a fused ash clinker in any quantity causes ceaseless trouble, and requires frequent removal. The coke should be broken into lumps of a uniform size, about 2 inches across, before being brought into the office. The furnace should be well packed by stirring, raising the coke and not ramming it, and it should be uniformly heated, not hot below and cold above. In lighting a furnace, a start is made with wood and charcoal. This readily ignites and sets fire to the coke, which of itself does not kindle easily. In commencing work, add, if necessary, fresh coke, and mix well. Make hollows, and into these put old crucibles. Pack around with coke so that the surface shall be concave, sloping upwards from the mouths of the crucibles to the side of the furnace. Close the furnace, and when uniformly heated, substitute for the empty crucibles those which contain the assays. It is rarely advisable to have a very hot fire at first, because with a gradual heat the gases and steam quietly escape through the unfused mass, while with too strong a heat these might make some of the matter in the crucible overflow. Moreover, if the heat should be too strong at first, the flux might melt and run to the bottom of the crucible, leaving the quartz, etc., as a pasty mass above. With a gentler heat, combination is completed, and the subsequent fiercer heat simply melts the fusible compound into homogeneous slag. The fused material may be left in the crucible and separated from it by breaking when cold. It is generally more convenient to pour it into cast iron moulds. These moulds should be dry and smooth. They act best when warmed and oiled or blackleaded. Air entering through the fire bars of a furnace and coming in contact with hot coke combines with it, forming a very hot mixture of carbonic acid and nitrogen. This, ascending, comes in contact with more coke, and the carbonic acid is reduced to carbonic oxide. At the top of the furnace, or in the flue, the carbonic oxide meeting fresh air combines with the oxygen therein and reforms carbonic acid. In the first and third of these reactions, much heat is evolved. In the second, the furnace is cooled a little. It must always be remembered that the carbonic oxide of the furnace gases is a reducing agent. When these gases are likely to exert a prejudicial effect, and a strongly oxidizing atmosphere is required, the work is best done in a muffle. End of section 2. Section 3 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 3. Wet Gravimetric Methods. In dry assays, the metal is almost always separated and weighed as metal. In wet gravimetric assays, the metal is more usually weighed in the form of a definite compound of known composition. The general methods of working resemble those of ordinary chemical analysis, and their successful working is greatly helped by a knowledge of, at any rate, those compounds of the metal which enable it to be separated, and of those which are the most convenient forms in which it can be weighed. But the work of the assayer differs from that of the analyst, inasmuch as the bulk of his estimations are made upon material of practically the same kind, varying only in richness. Consequently, in assaying it is possible and necessary to work on such a definite plan as will involve the least amount of labour in weighing and calculating. The assayer connected with mining has generally two classes of material to deal with, those comparatively rich and those comparatively poor. For example, silver in bullion and in ores, copper precipitates or regulus, and copper ores and slags, and black tin and tin ores. He is only occasionally called on to assay the intermediate products. It is indispensable that he should have an approximate knowledge of the substance to be determined. With new ores this information is best got by qualitative testing. Knowing that only certain bodies are present, it is evident that the number of separations can be reduced, and that simple methods can be devised for arriving at the results sought for. The best method is that which involves the least number of separations. The reactions must be sharp and complete, and yet not be liable to error under varying conditions. To bring the richer and poorer materials under the same conditions for the assay, a small weight, say 1 gram, of the richer, and a larger weight, 5 or 10 grams, of the poorer substance is weighed up. A method is then adopted which will concentrate the whole of the metal, either during or after solution, in a product which need not necessarily be pure. The work on this product is comparatively easy. In separating small quantities of a substance from a large bulk of impurities, the group separations must not, as a rule, be too much relied on. Very large precipitates carry down small quantities of bodies not belonging to the group, more especially when there is a tendency to form weak double compounds. The redissolving and reprecipitating of bulky precipitates should be avoided. When a large number of assays of the same kind have to be carried out, a plan something like the following is adopted. The samples, after having been dried, are placed in order on a table at the left hand of the assayer. He takes the first, marks it with a number, samples and weighs up the quantity required, and transfers it to a flask, which is similarly marked. As the weighings are finished, the samples are placed in the same order on his right hand. The assistant takes the flasks in batches of 4 or 5 at a time to the fume cupboard, where he adds a measured quantity of acid. When solution has been effected, dilution with a measured volume is generally necessary. The assayer sees to this, and, whilst the funnels and filters are being prepared, makes any separation that is necessary. The filters are arranged in order on a rack, and need not be marked unless the precipitates or residues have subsequently to be dried. The filters are washed with hot water, and if the filtrates are wanted, flasks are placed beneath. If not, the solution is drained off down the sink. Precipitation or reduction, or whatever it may be, is now made. The assistant filters the prepared samples one at a time, while the assayer is engaged with the others. The same style of work is continued until the assays are completed. If one should be spoiled, it is better to allow it to stand over for assaying along with the next batch. If one filters slowly, or is in any way less forward than the rest, it may lessen the accuracy of the other assays, owing to oxidation, etc. It should therefore be put on one side. The assays are dealt with in batches of 10 or 20, so that a large quantity of work can be quickly finished. When the assays are finished, it is the duty of the assistant to clean the apparatus, with reagents if necessary, and to put the vessels in the place set apart for them. Flasks are best kept inverted on a rack, so that they may be dry and clean by the next morning. Berlin crucibles must be cleaned and ignited. The amount of apparatus employed should be as little as is feasible. The assay should be carried out as much as possible in the same flask. The bench must be clean and altogether free from apparatus not in actual use. Crucibles and dishes in which weighings are made should be marked with numbers or letters, and their weights recorded, together with the date of weighing, in a small ledger, which is kept in the drawer of the balance. By this means a record of the wear of each piece of apparatus is obtained, and, what is more important, much weighing is saved, and increased confidence is gained. The weight of each piece of apparatus need not be taken daily. It will be seen from the record in the book, and a knowledge of the use it has been put to, how often a checking of the weight is necessary. The entries are made in black lead as follows: Dish A, February the 3rd, 9.4210 grams. February the 5th, 9.4225 grams. February the 6th, 9.4230 grams. February the 7th, 9.4200 grams. Platinum vessels and apparatus lose, and porcelain ones slightly gain, weight with continued use. The special details of the work is given under each assay. Certain general instructions will be given here. Solution. It is not always necessary to get the whole of the mineral in solution, provided the body sought for is either completely dissolved or altogether left in the residue. It is often only by a qualitative examination of the solution, or residue as the case may be, that the assayer can satisfy himself that it is free from the substance sought. But previous experience with the same kind of ore will show to what extent this testing is necessary. Solution is generally best effected in flasks, but where the resulting liquid has afterwards to be evaporated to dryness and ignited, evaporating dishes are used. With them, clock glasses are used as covers during solution to avoid loss through effervescence. Evaporating dishes are also best when an insoluble residue has to be collected, since it is difficult to wash out most residues from a flask. Bumping occurs less frequently in dishes than in flasks. After the addition of the acid, and mixing by agitation, the vessel containing the substance is heated. This is best done on the hot plate. This consists of a slab of cast iron about 1/2 or 3/4 of an inch thick, supported on loose fire bricks, and heated by 2 or 3 ring burners. The burners are connected to the gas supply by means of lead tubing, to which they are soldered. Flasks and dishes, after being put on the plate, are not further handled until solution is complete or the evaporation is carried to dryness. The hot plate is contained in a cupboard so as to be out of the reach of cold draughts. The action of the acids and other solvents is described in the chapter on reagents. Precipitation. In precipitating, add sufficient of the reagent to complete the reaction. The student must be on his guard against adding a very large excess, which is the commoner error. In some reactions, the finishing point is obvious enough. Either no more precipitate is formed, or a precipitate is completely dissolved, or some well-marked colour or odour is developed or removed. In those cases in which there is no such indication, theoretical considerations should keep the use of reagents within reasonable limits. The solutions of the reagents note, see the chapter on reagents, end note, are generally of 5 or 10% strength. A small excess over that demanded by theory should be sufficient. Filtration. Solutions are best filtered hot, whenever the assay allows of this being so done. The precipitate should be allowed to settle, and the clear liquid decanted on the filter with the aid of a glass rod if necessary. The filter paper must not be too large, but at the same time it must not be overloaded with the precipitate. There should be ample room for washing. For general use, 3 sizes of filter paper are sufficient. Common quick filtering paper, note English, end note, is best for most work in assaying. The specially prepared paper, note Swedish or Rhenish, end note, is used for collecting those precipitates which have to be weighed. The papers are folded as shown in figure 16 and should not project above the funnel. The filter paper works better if damped with hot water. In special cases, filtering is hastened by means of an air pump. The apparatus used consists of a water jet, shown in figure 17, which is connected with the tap, as also with a bottle fitted as shown in figure 18. The pump draws the air out from the bottle, and atmospheric pressure forces the liquid through the filter paper. The bottom of the funnel is provided with a platinum cone, which supports the filter paper and prevents its breaking. The pump is only used in exceptional cases. Nearly all the filtrations required by the assayer can be made without it. The usual methods of supporting the funnel during filtration are shown in figure 19. Where the filtrate is not wanted, pickle bottles make convenient supports. After the precipitate has been thrown on the filter, it is washed. In washing, several washings with a small quantity of water are more effective than a few with a larger quantity of that fluid. The upper edge of the filter paper is specially liable to escape complete washing. Excessive washing must be avoided. The point at which the washing is complete is found by collecting a little of the filtrate and testing it. The precipitate is removed from the filter paper for further treatment by opening out the paper and by washing the precipitate with a jet of water from a wash bottle into a beaker or back through the funnel into the flask. In some cases, when the precipitate has to be dissolved in anything in which it is readily soluble, solution is effected in the filter itself, allowing the liquid to run through as it is formed. Drying and igniting. Precipitates as a rule require drying before being ignited. With small precipitates, the filter paper may be opened out and placed on a warm asbestos slab till dry, or the funnel and the filter with the precipitate is placed in a warm place and supported by any convenient means. The heat must never be sufficient to char the paper. Some precipitates must be dried at a temperature not higher than 100 degrees centigrade. These are placed in the water oven, and when apparently dry, they are taken from the funnel, placed between glasses, and then left in the oven till they cease to lose weight. Such precipitates are collected on tared filters. Those precipitates which will stand a higher temperature are dried in the hot air oven at a temperature of from 120 degrees to 150 degrees. The drying is continued until they appear to be free from moisture, and until the precipitate ceases to adhere to the filter. In drying sulphides, the heat must not be raised to the melting point of sulphur, since if there is any free sulphur present, it fuses and filters through. The precipitate, having been dried, is transferred to a watch glass. The filter paper is opened out over a sheet of notepaper, and with a camel hair brush the precipitate is gently brought into the glass. Most precipitates come away easily, and the transfer can be made without apparent loss. The watch glass is covered by the funnel, and the filter paper, folded into a quadrant, held by the tweezers, and set fire to with the flame of a Bunsen burner. It is allowed to burn over the crucible, into which the black, bulky ash is allowed to drop, and 2 or 3 drops of nitric acid are then added. The crucible is placed on a pipe stem triangle, supported on a tripod. It is at first heated gently with a Bunsen burner, and afterwards more strongly, until the residue is free from carbon. It is cooled and treated with any acid necessary to convert the small amount of precipitate into the state in which it is to be weighed, heated again and cooled. The main precipitate is transferred to the crucible, and the heating repeated very gently at first, but more strongly towards the end of the operation. It is next placed in the muffle, and after 2 or 3 minutes at a red heat, it is removed and allowed to cool in the desiccator before weighing. This is for bodies that will bear a red heat. For those compounds that require a lower temperature, the heating in the muffle is omitted. The muffle used for this purpose must not be used at the same time for cupelling. A gas muffle, such as one of Fletcher's, is best. A desiccator is an airtight vessel which prevents access of moisture, etc., to the substance. Usually the air in it is kept dry by means of a basin containing sulphuric acid. The crucible is removed from the muffle with the tongs and carried to the desiccator. It is best, in an office, to have a large desiccator permanently fixed alongside the balance, into which all substances may be put before being weighed. The substance is removed from the bench or muffle in the small hand apparatus generally sold, and carried to the balance room to be transferred to the large desiccator, where it is allowed to become thoroughly cold before being weighed. 20 minutes is generally the time allowed after ignition, before it is advisable to weigh. Bodies allowed to cool in the air after they have been ignited will absorb moisture, and hot bodies placed in the balance pan will disturb the equilibrium and show false results. Compounds that absorb moisture must be weighed quickly. They should therefore be weighed in covered vessels. Such compounds are detected by their continually increasing weight. They should be ignited and weighed again in a well-covered dish. Substances that have been washed with alcohol, ether, or any readily volatile liquid are dried in the water oven. They quickly dry if there is no water present, and are generally fit for weighing in less than 1 hour. Sometimes drying for a few minutes only will be sufficient. The weight of the crucible and precipitate having been obtained, the weight of the crucible and ash is deducted. For example, crucible and precipitate 10.183 grams, crucible and ash 9.527 grams. Weight of precipitate 0.656 grams. The weight of the ash is best added to that of the crucible. The amount of ash in filter papers must not be neglected, although papers are now made almost free from ash, and the amount to be deducted is found by taking 8 or 10 papers and burning them until they become white, and then weighing the ash. The amount varies from 0.004 to 0.0005 of a gram for different papers. Having determined the ash, place in the balance drawer 3 of the filter papers pinned together, with the weights marked on them in the way shown in Figure 24, so as to be readily seen when there is occasion to refer to them. Note: Figure 24 shows 3 overlaid circles representing filter papers, small, medium and large, each with the ash weight written on it. End note. It must be remembered that the determination of small quantities of substances generally involves the use of reagents which are often contaminated as an impurity with the body sought for. Thus, in assaying silver, the oxide of lead or metallic lead used is rarely free from silver, and in the case of arsenic, the acids, zinc or ferric chloride, are sure to contain arsenic. The same observation applies to the precipitation of lead by zinc, etc. The errors caused by these impurities are more marked in the determination of material having small quantities of metal than in that of ores which contain larger quantities. Errors of this kind are counteracted or neutralized by blank or blind determinations. These consist in carrying out by the side of and during the assay a duplicate experiment with the reagents only, which are thereby subjected to the same processes of solution, evaporation, filtration, etc. The final result thus obtained is deducted from that given by the assay. The difference gives the corrected result. In some cases, where it is desired or necessary to have a tangible residue or precipitate, some pure inert material is added. End of section 3. Section 4 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 4. Volumetric Assays. These have already been described as those in which the results are got by measuring either 1. The volume of a reagent required to complete some reaction, or 2. The volume of the resulting product. For example, if a permanganate of potash solution be added to a solution containing a weighed amount of iron dissolved in sulphuric acid, the strong colour of the permanganate of potash will be removed until a certain quantity of it has been added. Repeating the experiment, it will be found that the same amount of iron decolorises the same volume of the permanganate solution within certain narrow limits of variation, known as error of experiment. This error is due to variation in the method of working, and to slight differences in the weighings and measurings. It is present in all experimental methods, although the limits of variation are wider in some than in others. Apart from this error of experiment, however, it is certain that a given volume of the permanganate of potash solution corresponds to a definite weight of iron, so that if either is known, the other may be calculated. Similarly, if a known weight of zinc, or of carbonate of lime, be dissolved in hydrochloric acid, a gas will be given off, which can be measured, and so long as the conditions of the experiment do not vary, the same weight of zinc, or of carbonate of lime, gives off the same volume of gas. The weight of one can be determined from the volume of the other. Or again, the quantity of some substances may be measured by the colour of their solutions, on the principle that, other things being equal, the colour of a solution depends upon the quantity of colouring matter present, so that if two solutions of the same substance are equally coloured, they are of equal strength. In this way an unknown may be compared with a known strength, and a fairly accurate determination may be made. These three illustrations serve as types of the three chief classes of volumetric assays: titrometric, gasometric, and colorimetric. Titrometric assays. Within the limits of the error of experiment, a definite volume of a solution or gas represents a certain weight of metal or other substance. Hence, the exact weight may be determined by experiment. The error of experiment may be reduced to insignificant dimensions by repeating the experiment and taking the mean of 3 or 4 determinations. This will at the same time show the amount of variation. Thus, if 0.5 of a gram of iron were dissolved and found to require 50.3 cubic centimetres of the solution of permanganate of potash, and if on repeating 50.4, 50.2 and 50.3 cc's were required, the experimenter would be justified in saying that 50.3 cc's of the permanganate solution represent 0.5 grams of iron, and that his results were good within 0.2 cc's of the permanganate solution. So that if in an unknown solution of iron 50.5 cc's of the permanganate solution were used up, he could state with confidence that it contained a little more than 0.5 of a gram of iron. With a larger experience, the confidence would increase, and with practice the experimental error will diminish. But supposing that the unknown solution required, say, 100.5 instead of 50.5 cc's, he would not be justified in saying that since 50.3 cc's are equivalent to 0.5 of a gram, 100.6 cc's are equivalent to twice that amount, and that consequently the unknown solution contained a little less than 1 gram of iron. Or at least he could not say it except he or someone else had determined it by experiment. But if on dissolving 1 gram of iron he found it to require 100.6 cc's of the solution, and in another experiment with 0.8 of a gram of iron that 80.5 cc's of the solution were required, he would be justified in stating that the volume of solution required is proportional to the quantity of metal present. There are a large number of volumetric assays of which this is true, but that it is true in any particular case can only be proved by experiment. Even where true, it is well not to rest too much weight upon it, and in all cases the quantity of metal taken to determine the strength of the solution used should not differ widely from that present in the assay. There are certain terms which should be explained here. When the solution of a reagent is applied under such conditions that the volume added can be correctly determined, the operation is called titrating, the solution of the reagent used, the standard solution, and the process of determining the strength of the standard solution is standardizing. The standard is the quantity of metal equivalent to 100 cc's of the standard solution. Standard solutions. In making these, the salt is accurately weighed and transferred to a litre flask, or to the graduated cylinder, and dissolved. The method of dissolving it varies in special cases, and instructions for these will be found under the respective assays. Generally it is dissolved in a small quantity of liquid and then diluted to the mark. For those substances that require the aid of heat, the solution is made in a pint flask, cooled and transferred, after which the flask is well washed out. After dilution, the liquids in the measuring vessel must be thoroughly mixed by shaking. This is more easily and better done in the cylinder than in the litre flask. The solution is next transferred to a dry Winchester bottle and labelled. The label may be rendered permanent by waxing it. Standard solutions should not be kept in a place exposed to direct sunlight. Oxidizing and reducing solutions, such as those of permanganate of potash, ferrous sulfate, iodine, hyposulfite of soda, etc., gradually weaken in strength. The solutions of other salts are more stable, while those of potassium bichromate and baric chloride are almost permanent. Solutions of potassium permanganate may be kept for a month or so without much change. The solutions of hyposulfite of soda and of iodine should be examined weekly. Ferrous sulfate solutions, if acidulated with sulfuric acid, may be depended on for 2 or 3 weeks without fresh standardizing. Before filling the burette, the Winchester bottle should be well shaken, and a portion of about 50 or 100 cc's poured into a dry beaker or test glass. Besides the standard solutions, which are required for titrating an assay, permanent solutions of the metal, or acid of equivalent strength, are very useful. When the finishing point of a titration has been overstepped, i.e. the assay has been overdone, a measured volume, say 5 or 10 cc's, of a solution containing the same metal may be added. The titration can then be continued, but more cautiously, and the value in cc's for the quantity added be deducted from the final reading. Standardizing. Suppose the object is to standardize a solution of permanganate, similar to that referred to above. A convenient quantity of iron, say 0.5 gram, would be weighed out, dissolved in dilute sulphuric acid, and the solution titrated. Suppose 49.6 c.c. of the permanganate solution are required. Then 49.6 to 0.5 is equivalent to 100 to X. Therefore, X equals 1.008 of a gram. This result, 1.008 of a gram, is the standard. When a gas is measured, the standard may be calculated in the same way. For example, with 0.224 of a gram of zinc, 75.8 c.c. of gas were obtained. Then the quantity of zinc equivalent to 100 c.c. of the gas is got by the proportion 75.8 to 0.224 is equivalent to 100 to X. Therefore, X equals 0.2955 of a gram. Using the term standard in this sense, the following rules hold good. To find the weight of metal in a given substance, multiply the standard by the number of cc's used and divide by 100. For example, a piece of zinc was dissolved and the gas evolved measured 73.9 cc's. Then, by the rule, 0.2955 times 73.9 divided by 100 should give the weight of the piece of zinc. This gives 0.2184 of a gram. To find the percentage of metal in a given substance, multiply the standard by the number of cc's used and divide by the weight of substance taken. For example, if 2 grams of a mineral were taken, and if on titrating with the permanganate solution, standard 1.008, 60.4 cc's were required, then 1.008 times 60.4 divided by 2 equals 30.44. This is the percentage. If the standard is exactly 1 gram, and 1 gram of ore is always taken, these calculations become very simple. The cc's used give at once the percentage, or divided by 100, give the weight of metal. If it is desired to have a solution with a standard exactly 1.0 grams, it is best first to make one rather stronger than this, and then to standardize carefully. Divide 1000 by the standard thus obtained, and the result will be the number of cc's which must be taken and be diluted with water to 1 litre. For example, suppose the standard is 1.008, then 1000 divided by 1.008 gives 992. And if 992 cc's be taken and diluted with water to 1000 cc's, a solution of the desired strength will be obtained. The standard of this should be confirmed. A simpler calculation for the same purpose is to multiply the standard by 1000. This will give the number of cc's to which 1 litre of the solution should be diluted. In the above example, a litre should be diluted to 1008 cc's. It has been assumed in these rules that the titration has yielded proportional results, but these are not always obtained. There can be no doubt that in any actual reaction the proportion between any 2 reagents is a fixed one, and that if we double one of these, then exactly twice as much of the other will enter into the reaction. But in the working it may very well be that no reaction at all will take place until after a certain excess of one or both of the reagents is present. In titrating lead with a chromate of potash solution, for example, it is possible that at the end of the titration a small quantity of the lead may remain unacted on, and it is certain that a small excess of the chromate is present in the solution. So too, in precipitating a solution of silver with a standard solution of common salt, a point is reached at which a small quantity of each remains in solution. A further addition either of silver or of salt will cause a precipitate, and a similar phenomenon has been observed in precipitating a hydrochloric acid solution of a sulphate with baric chloride. The excess of one or other of the reagents may be large or small, or in some cases they may neutralize each other. Considerations like these emphasize the necessity for uniformity in the mode of working. Whether a process yields proportional results or not will be seen from a series of standardizings. Having obtained these, the results should be arranged as in the table, placing the quantities of metal used in the order of weight in the first column, the volumes measured in the second, and the standards calculated in the third. If the results are proportional, these standards will vary more or less according to the delicacy of the process, but there will be no apparent order in the variation. The average of the standards should then be taken. Note the example given consists of 5 sets of figures for the weight, volume found, and standard. The first 4 standards range between 0.2957 and 0.2964, but the fifth is 0.2974. End note. Any inclination that may be felt for obtaining an appearance of greater accuracy by ignoring the last result must be resisted. For although it would make no practical difference whether the mean standard is taken as 0.2961 or 0.2963, it is well not to ignore the possibility that an error of 0.4 of a cc may arise. Reader's note. This corresponds in the previous table to volumes between 72.9 cc's and 82.3 cc's for the first 4 volumes and 85.9 cc's for the fifth. End reader's note. A result should only be ignored when the cause of its variation is known. In this series the results are proportional, but the range of weights 0.216 to 0.2555 grams is small. All processes yield fairly proportional results if the quantities vary within narrow limits. As to results which are not proportional, it is best to take some imaginary examples and then to apply the lesson to an actual one. A series of titrations of a copper solution by means of a solution of potassic cyanide gave the following results. Reader's note. The table consists of 4 rows of 3 columns, copper taken, cyanide used, and standard. The 4 rows correspond to 0.1, 0.2, 0.3 and 0.4 of a gram of copper. Cyanide used 11.9 cc's, 23.7 cc's, 35.6 cc's and 47.6 cc's, giving standards which vary between 0.8403 and 0.8438. End reader's note. These are proportional, but by using a larger quantity of acid and ammonia in the work preliminary to titration, we might have had to use 1 cc of cyanide solution more in each case before the finishing point was reached. The results would then have been, reader's note, 4 rows, again, of copper 0.1 through to 0.4 of a gram, cyanide used 12.9 through to 48.6, and the standards varying progressively from 0.7752 up to 0.8230, compared to a range of 0.8403 to 0.8438 for the earlier table. End reader's note. It will be noted that the value of the standard increases with the weight of metal used, and calculations from the mean standard will be incorrect. By subtracting the lower standardizing from the highest, a third result is got, free from any error common to the other 2. Thus, reader's note. The following data is taken from the previous table. The weight quoted is of copper. End reader's note. 0.4 of a gram equals 48.6 cc's of cyanide, and 0.1 of a gram equals 12.9 cc's of cyanide. Subtracting the second from the first, 0.3 of a gram equals 35.7 cc's of cyanide. And the standard calculated from this corrected result is 0.8404. Further, if 0.3 of a gram requires 35.7 cc's, then 0.1 of a gram should require 11.9 cc's, or 1 cc less than that actually found. We may therefore use the following rules for working processes which do not yield proportional results. Make a series of 2 or 3 titrations, using very different quantities of metal in each. Subtract the lowest of these from the highest, and calculate the standard with the remainder. Calculate the volume required by this standard in any case, and find the excess or deficit, as the case may be. If an excess, subtract it from the result of each titration. If a deficit, add it, and use the standard in the usual way. The following table shows an actual example. Reader's note. The table can be summarized as follows. 6 values of chalk taken from 0.0873 of a gram to 0.3000 of a gram. Gas obtained 17.8 cc's to 64.0 cc's. And standard 0.4904 to 0.4687. End reader's note. It will be seen that the standard decreases as the quantity of chalk increases. This points to a deficiency in the quantity of gas evolved. Then, reader's note, taking the highest and lowest values from the table, end reader's note, 0.300 equals 64.0 cc's, 0.0873 equals 17.8 cc's, therefore subtracting 0.2127 equals 46.2 cc's, and 0.2127 times 100 divided by 46.2 equals 0.4604. Then multiplying the weight of chalk taken by 100 and dividing by 0.4604, we get the calculated results of the following table. Reader's note, table omitted. But for the 6 values of chalk taken, a value of the gas calculated is given corresponding to the gas actually found. The difference between the gas calculated and the gas found varies between minus 0.9 to minus 1.1 cc's. End reader's note. By adding 1 cc to the quantity of gas obtained and taking 0.4604 as the standard, the calculated results will agree with those found, with a variation of 0.1 cc. When a large number of assays of the same kind are being made, this method of calculation is convenient. When, however, only 1 or 2 determinations are in question, it is easier to make a couple of standardizings, taking quantities as nearly as possible the same as those present in the assays. Sometimes it is necessary to draw up a table which will show without calculation the weight of substance equivalent to a given volume of gas or of solution. The substance used for standardizing should be, whenever possible, a pure sample of the substance to be determined. That is, for copper assays, pure copper should be used; for iron assays, pure iron, and so on. But when this cannot be got, an impure substance may be used, provided it contains a known percentage of the metal, and that the impurities present are not such as will interfere with the accuracy of the assay. Including compounds with these, the standard may be calculated by multiplying the standard got in the usual way by the percentage of metal in the compound or impure substance, and dividing by 100. If, for example, the standard 1.008 of a gram was obtained by using a sample of iron containing 99.7% of metal, the corrected standard would be 1.008 times 99.7 divided by 100 equals 1.005. In volumetric analysis, the change brought about must be one in which the end of the reaction is rendered prominent, either by a change of colour or by the presence or absence of a precipitate. If the end of the reaction or finishing point is not of itself visible, then it must be rendered visible by the use of a third reagent, called an indicator. For example, the action of sulphuric acid upon soda results in nothing which makes that action conspicuous. If, however, litmus or phenolphthalein be added, the change from blue to red in the first case, or from red to colourless in the second, renders the finishing point evident. Some indicators cannot be added to the assay solution without spoiling the result, in which case portions of the assay solution must be withdrawn from time to time and tested. This withdrawal of portions of the assay solution, if rashly done, must result in loss. If, however, the solution is not concentrated, and if the portions are only withdrawn towards the end of the titration, the loss is very trifling and will not show up on the result. The usual plan adopted is to have a solution of the indicator placed in drops at fairly equal intervals, distributed over a clean and dry white porcelain plate. A drop or two of the solution to be tested is then brought in contact with one of these, and the effect noted. Another plan is to have thin blotting paper moistened with a solution of the indicator and dried. A drop of the solution to be tested placed on this shows the characteristic change. When the assay solution contains a suspended solid which interferes with the test, a prepared paper covered with an ordinary filter paper answers very well. A drop of the solution to be tested is placed on the filter paper, and sinking through shows its effect on the paper below. Except when otherwise stated, all titrations should be made at the ordinary temperature, cooling, if necessary, by holding the flask under the tap. When a titration is directed to be made in a boiling solution, it must be remembered that the standard solution is cold, and that every addition lowers the temperature of the assay. On running the solution from the burette into the assay, do not let it run down the side of the flask. If a portion of the assay has to be withdrawn for testing, shake the flask to ensure mixing, and then take out a drop with the test rod. The neglect of these precautions may give a finishing point too early. This is generally indicated by a sudden finish, in which case on shaking the flask and again testing, no reaction is got. Do not remove the drop on the point of the burette with the test rod. Let it remain where it is, or drop it into the solution by carefully opening the clip. Generally, the methods of working are as follows. 1. When the finishing point depends on a change of colour in the solution. Increase the bulk of the assay up to from 100 to 150 cc with water. Boil or cool as the case may be. Run in the standard solution from a burette speedily until the reagent appears to have a slower action, and shake or stir all the time. Then run 1 cc or so at a time, still stirring, and finally add drops until the colour change is got. 2. When an outside indicator is used. Pour the standard solution from a burette into the assay until 5 or 6 cc from the finishing point. Then run in 1 cc at a time, stirring and testing on the plate between each, until the indicator shows the change wanted, and deduct 0.5 of a cc for excess. When greater accuracy is sought for, a duplicate assay is made. In this case, the standard solution is run in close up to the end, and the operation is finished off with a few drops at a time. 3. When the finishing point depends upon the absence of a precipitate and no outside indicator is used. As in the last case, run in the standard solution up to within a few cc's of the end, then run in 1 cc at a time until a precipitate is no longer formed, but here 1.5 cc's must be deducted for excess, since it is evident that the whole of the last cc must have been, and a portion of the previous one may have been, in excess. Indirect titration. The action of permanganate of potash upon a ferrous solution is one of oxidation. Hence it is evident that if any other oxidizing agent is present, it will count as permanganate. In such a case, the titration can be used indirectly to estimate the quantity of such oxidizing agent by determining how much less of the permanganate is used. For example, suppose that 1 gram of iron dissolved in sulphuric acid requires 100 cc of standard permanganate to fully oxidize it, but that the same amount of iron only requires 35.6 cc of the same standard permanganate if it has been previously heated with 0.5 of a gram of black oxide of manganese. Here it is evident that 0.5 of a gram of black oxide does the work of 64.4 cc of the permanganate solution. Note: 100 minus 35.6 equals 64.4. End note. And that these quantities are equivalent. Moreover, if 64.4 cc correspond with 0.5 of a gram, then 100 cc correspond with 0.7764, which is the standard. On theoretical grounds, and by a method of calculation which will be explained further on, note, under the heading Calculations from Formulae, end note, it can be found that if the standard for iron is 1 gram, that for the black oxide will be 0.7764 of a gram. The principles of these indirect titrations become clearer when expressed in a condensed form. Thus, in the example selected, and using the formula Fe equals iron, KMnO4 equals permanganate of potash, and MnO2 equals oxide of manganese, we have 1 gram of Fe equals 100 cc KMnO4. 2. 1 gram of Fe equals 35.6 cc KMnO4 plus 0.5 of a gram MnO2. Therefore, 100 cc of KMnO4 equals 35.6 cc of KMnO4 plus 0.5 of a gram of MnO2. 100 minus 35.6 cc of KMnO4 equals 0.5 of a gram of MnO2. And 64.4 cc KMnO4 equals 0.5 of a gram MnO2. The iron does not enter into the calculation if the same quantity is present in the two experiments. An indirect titration thus requires 3 determinations, but if more than one assay is to be carried on, 2 of these need not be repeated. The standard is calculated in the usual way. Colorimetric assays. These are assays in which the colour imparted to a solution by some compound of the metal to be determined is taken advantage of, the depth of colour depending on the quantity of metal present. They are generally used for the determination of such small quantities as are too minute to be weighed. The method of working is as follows: a measured portion of the assay solution, generally 2/3, a half, a third or a quarter of the whole, coloured by the substance to be estimated, is placed in a white glass cylinder standing on a sheet of white paper or glazed porcelain. Into an exactly similar cylinder is placed the same amount of reagents, etc., as the portion of the assay solution contains, and then water is added until the solutions are of nearly equal bulk. Next, a standard solution of the metal being estimated is run in from a burette, the mixture being stirred after each addition until the colour approaches that of the assay. The bulk of the 2 solutions is equalised by adding water. Then more standard solution is added until the tints are very nearly alike. Next, the amount added is read off from the burette. Still more is poured in until the colour is slightly darker than that of the assay, and the burette read off again. The mean of the readings is taken and gives the quantity of metal added. It equals the quantity of metal in the portion of the assay. If this portion was 1/2 of the whole, multiply by 2. If 1/3, multiply by 3, and so on. When the quantity of metal in very dilute solutions is to be determined, it is sometimes necessary to concentrate the solutions by boiling them down before applying the reagent which produces the coloured compound. Such concentration does not affect the calculations. Gasometric assays. Gasometric methods are not much used by assayers, and therefore those students who wish to study them more fully than the limits of this work will permit are recommended to consult Winkler and Lunge's textbook on the subject. The methods are, without doubt, capable of a more extended application. In measuring liquids, ordinary variations of temperature have but little effect, and variations of atmospheric pressure have none at all, whereas with gases it is different. Thus, 100 cc of an ordinary aqueous solution would, if heated from 10 degrees centigrade to 20 degrees centigrade, expand to about 100.15 cc. 100 cc of a gas, similarly warmed, would expand to about 103.5 cc, and a fall of an inch in the barometer would have a very similar effect. And in measuring gases, we have not only to take into account variations in volume due to changes in temperature and atmospheric pressure, but also that which is observed when a gas is measured wet and dry. Water gives off vapour at all temperatures, but the amount of vapour is larger as the temperature increases. By ignoring these considerations, errors of 3 or 4% are easily made, but fortunately the corrections are simple, and it is easy to construct a piece of apparatus by means of which they may be reduced to a simple calculation by the rule of 3. The volume of a gas is, in practice, usually reduced to that which it would be at a temperature of 0°C, when the column of mercury in the barometer is 760 mm high. But although convenient, this practice is not always necessary. The only thing required is some way of checking the variations in volume, and of calculating what the corrected volume would be under certain fixed conditions. Suppose that at the time a series of standardizings is being made, 100 c.c. of air were confined in a graduated tube over moist mercury. These 100 c.c. would vary in volume from day to day, but it would always be true of them that they would measure 100 c.c. under the same conditions as those under which the standardizings were made. If, then, in making an actual assay, 35.4 c.c. of gas were obtained, and the air in the tube measured 105 c.c., we should be justified in saying that, if the conditions had been those of the standardizing, the 105 c.c. would have measured 100 c.c., and the 35.4 c.c. would have been 33.7, for 105 to 100 is equivalent to 35.4 to 33.7. The rule for using such a piece of apparatus for correcting volumes is multiply the cc's of gas obtained by 100 and divide by the number of cc's of air in the apparatus. If it is desired to calculate the volumes under standard conditions, that is, the gas dry at 0°C and 760 mm barometric pressure, the calculations are easily performed, but the temperature and pressure must be known. Correction for moisture. The vapour tension of water has been accurately determined for various temperatures, and it may be looked upon as counteracting the barometric pressure. For example, at 15°C, the vapour tension equals 12.7 mm of mercury. If the barometer stood at 750 mm, the correction for moisture would be made by subtracting 12.7 from 750, and taking 737.3 mm to be the true barometric pressure. The vapour tension for temperatures from 0°C to 20°C are as follows. Reader's note. This table has been omitted. End reader's note. The correction for pressure is multiply the volume by the actual pressure and divide by 760. The correction for temperature, multiply the volume by 273 and divide by the temperature in degrees centigrade added to 273. For all three corrections the following rules hold good. To reduce to 0°C and 760 mm dry, the corrected volume equals the volume times 0.3592 times, open brackets, pressure minus tension, close brackets, all divided by temperature plus 273. To find the volume which a given volume under standard conditions would assume if those conditions are altered, resulting volume equals volume times 2.784 times, open brackets, temperature plus 273, close brackets, all divided by, open brackets, pressure minus tension, close brackets. As an example, we will suppose that it is desired to enclose in the apparatus referred to on page 45, reader's note, this consisted of 100 cc's of air confined in a graduated tube over moist mercury, end reader's note, a volume of air which, when dry at 0°C and 760 mm, shall measure 100 cc's, while the actual temperature is 15°C and the pressure 750 mm. The second formula is the one to be used, and we get 108.7 cc's. Required volume equals 100 cc's times 2.784 times 288, all divided by open bracket 750 minus 12.7 close brackets, equals 108.7 cc's. End of section 4. Section 5 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 5. Weighing and Measuring. Weighing. The system of weights and measures which we have adopted is the French or metric system. In this, the gram, 15.43 grains, is the unit of weight. The only other weight frequently referred to is the milligram, which is 0.001 or 1,000th of a gram. The unit of volume is the cubic centimetre, which is approximately the volume of 1 gram of water, and which thus bears to the gram the same relation as grain measures bear to grains. It is usual to write and even pronounce cubic centimetre shortly as cc, and the only other denomination of volume we shall have occasion to use is the litre, which measures 1000 cc and is roughly 1 3/4 pints. The weights used are kept in boxes in a definite order, so that the weights on the balance can be counted as well by noting those which are absent from the box as by counting those present on the scale pan. The weights run 50, 20, 10, 10, 5, 2, 1, 1 and 1 grams, and are formed of brass. The fractions of the gram are generally made of platinum or of aluminium, and are arranged in the following order: 0.5, 0.2, 0.1, 0.1, and 0.05, 0.02, 0.01, 0.01. These may be marked in this way, or they may be marked 500, 200, 100, 100, 50, 20, 10, 10, the 500 meaning 500 milligrams. Some makers send out weights in the series 50, 20, 20, 10, etc. Weights of less than 0.01 of a gram are generally present in a box, but it is much more convenient to work with a rider. This is a piece of wire which in the pan weighs 0.01 of a gram. It is made in such a form that it will ride on the beam, and its effective weight decreases as it approaches the centre. If the arm of the beam is divided into tenths, then each tenth, counting from the centre outward, equals 0.001 of a gram, or 1 milligram, and if these tenths be further subdivided, the fractions of a milligram are obtained, and these give figures in the 4th place of decimals. A fairly good balance should be sensitive to 0.0001 of a gram. The weights must never be touched with the fingers, and the forceps for moving them is used for no other purpose. When not in actual use, the box is kept closed. The weights must not be allowed to remain on the pan of the balance. The balance case must not be open without some reason. It must be fixed level, and once fixed, must not be needlessly moved. The bench on which it stands should be used for no other purpose, and no one should be allowed to lean upon it. When using a balance, sit directly in front of it. Ordinarily, the substance to be weighed is best put on the pan to the user's left. The weights and the rider are then easily manipulated. Powders, etc. should not be weighed directly on the balance. A counterpoised watch glass or metal scoop should be used. In some cases it is advisable to use a weighing bottle. This is a light, well-stoppered bottle containing the powdered ore. It is first filled and weighed, then some of the substance is carefully poured from it into a beaker or other vessel, and it is weighed again. The difference in the two weighings gives the weight of substance taken. A substance must always be cold when weighed, and large glass vessels should be allowed to stand in the balance box a little while before being weighed. Always have the balance at rest when putting on or taking off anything from the pans. Put the weights on systematically. In using the rider, except you have a reason to the contrary, put it on at the 5. If this is too much, then try it at the 3. If then the weights are too little, try it at the 4. If still not enough, the correct weight must be between the 4 and 5. Try halfway between. It is best to work with the balance vibrating. Equilibrium is established when the vibration to the left is the mean of the preceding and succeeding vibrations to the right. For example, if it vibrates 6 divisions to the right on one swing and 5 divisions on the next, the intermediate vibration to the left should have been 5.5. Note whether the substance increases in weight whilst on the balance. If it does, it may be because it was put on warm and is cooling, or it may be because it is taking up moisture from the air. Substances which take up moisture rapidly should be weighed in clipped watch glasses or in light weighing bottles or tubes. Students, in recording the weights, should first read off those missing from the box, writing down each order of figures as determined, first tens, then units, and so on. Remember that the first 4 platinum weights give the figures of the first place of decimals, the second 4 give the second place, and that the third and fourth places are given by the rider. Having taken down the figures, confirm them by reading off the weights as you put them back into the box. Do not rest a weight on the palm of your hand for convenience in reading the mark upon it. Remember, 1 weight lost from a box spoils the set. Do not take it for granted that the balance is in equilibrium before you start weighing. Try it. Measuring liquids. For coursework, such as measuring acids for dissolving ores, graduated glasses similar to those used by druggists may be used. It is well to have 2 sizes, a smaller graduated into divisions of 5 cc, and a larger with divisions equal to 10 cc. No measurement of importance should be made in a vessel of this kind, as a slight variation in level causes a serious error. Reader's note. This section is illustrated by a picture of a glass measuring cylinder. End reader's note. Graduated flasks must be used when anything has to be made up to a definite bulk, or when a fixed volume has to be collected. If, for example, a certain weight of substance has to be dissolved and diluted to a litre, or if the first 50 cc of a distillate has to be collected, a flask should be used. Each flask is graduated for one particular quantity. The most useful sizes are 1000 cc, 500 cc, 200 cc, 100 cc, and 50 cc. The mark should be in the narrowest part of the neck, and should be tangential to the curved surface of the liquid when the flask contains the exact volume specified. The level of a curved surface of liquid is at first somewhat difficult to read. The beginner is in doubt whether the surface should be taken at A, B, or C in figure 27. Reader's note. Figure 27 shows a curved meniscus within the graduated neck of a measuring flask. The meniscus consists of a downward crescent with another crescent just within it. The upper limits where the meniscus joins the walls of the tube is A, the surface of the inner crescent is B, and the surface of the lower crescent of the meniscus is C. End reader's note. It is best to take the lowest reading, C. In some lights it is difficult to find this. In such cases a piece of white paper or card held behind and a little below, so as to throw light up and against the curved surface, will render it clear. In reading, one should look neither up nor down upon the surface, but the eye should be on the same level with it. It must be kept in mind that flasks contain the quantity specified, but deliver less than this by the amount remaining in them and damping the sides. If it is desired to transfer the contents, say, of a 100 cc flask to a beaker, it will be necessary to complete the transfer by rinsing out the flask and adding the washings, otherwise there will be a sensible loss. Graduated cylinders are convenient for preparing standard solutions. Reader's note: the graduated cylinder illustrated resembles a measuring cylinder except with a narrow neck at the top sealed with a glass stopper. End reader's note. Pipettes and burettes are graduated to deliver the quantities specified. The principle of the pipette and the advantages and disadvantages of its various forms may be understood by considering the first form shown in figure 29. It is essentially a bulbed tube drawn out to a jet at its lower end, and having on each side of the bulb a mark so placed that when the surface of the liquid falls from the upper to the lower mark, the instrument shall deliver exactly 100 cc. The bore of the jet should be of such a size as will allow the level of the liquid to fall at the rate of about 1 foot in 2 minutes. If it runs more quickly than this, an appreciable error arises from the varying amount of liquid remaining and damping the sides of the bulb. The flow of liquid from a pipette must not be hastened by blowing into it. The lower tube or nose of the pipette should be long enough to reach into the bottle or flask containing the liquid about to be measured. The pipette is filled by sucking at the open end with the mouth. This method of filling renders the use of the instrument dangerous for such liquids as strong acids, ammonia, and such poisonous solutions as that of potassic cyanide. One attempt with a fairly strong solution of ammonia will teach the beginner a very useful lesson. As soon as the liquid rises above the upper mark in the pipette, the mouth is withdrawn and the pipette quickly closed by pressing the upper aperture with the index finger of the right hand. It is well to have the finger slightly moist, but not damp. The neck of the pipette should be long enough to allow its being firmly grasped by the fingers and thumb of the right hand without inconvenience. The pipette is first held in a vertical position long enough to allow any moisture outside the tube to run down, and then the liquid is allowed to run out to the level of the upper mark. This is easily effected by lessening the pressure. If the finger is wet, the flow will be jerky and good work impossible. The pipette is next held over the vessel into which the 100 cc are to be put, and the liquid allowed to run out. When the bulb is nearly empty, the flow should be checked by replacing the finger, and the liquid allowed to escape slowly until the lower mark is reached. The pipette is then withdrawn. It is in the withdrawing that the disadvantage of this particular form makes itself felt. Note: it is best to use this form with a glass stopcock or with an india rubber tube and clip, after the manner of a Mohr's burette. End note. Reader's note: the stopcock is in the lower tube just below the bulb. End reader's note. It must be withdrawn very steadily, as the slightest shock causes the remaining column of liquid to vibrate, whereby air is drawn in and the liquid is forced out. This disadvantage is got rid of by making the mouth of the jet the lower limit, or, in other words, allowing the instrument to empty itself. There are two forms of such pipettes. In the one generally recommended in Gay-Lussac's silver assay, the nose is replaced by a jet. This is most conveniently filled by stopping the jet with the finger and allowing the liquid to flow in a fine stream into the neck until the pipette is filled. Reader's note: this pipette consists of a bulb with the jet at its immediate bottom end, with the narrow filling tube from its top end. End reader's note. And then working as just described. The other form is the one in general use. Reader's note: this consists of a bulb with a long tube at the upper end and a long tube with a nozzle at the bottom end. End reader's note. In fact, a long nose to a pipette is so convenient that it may almost be said to be necessary, but the accuracy is slightly diminished. A long narrow tube makes a poor measuring instrument because of the amount of liquid it finally retains. A defect possessed by both forms is the retention of a drop of varying size in the nozzle. Whatever method is adopted for removing this drop must always be adhered to. The most convenient form is the one last described, and the most useful sizes are 100 cc, 50 cc, 20 cc, 10 cc and 5 cc. 10 cc pipettes graduated into tenths of a cubic centimetre are very useful. Those are best in which the graduation stops short of the bottom. All measurements should be made at the ordinary temperature, and before being used the pipette should be rinsed out with a cubic centimetre or so of the solution to be measured. After using, it should be washed out with water. Burettes differ mainly from pipettes in having the flow of liquid controlled from below instead of from above. The best form is that known as Moore's, one kind of which is provided with a glass stopcock, while the other has a piece of india rubber tube compressed by a clip. The latter cannot be used for solutions of permanganate of potash or of iodine, or of any substance which acts on india rubber, but in other respects there is little to choose between the two kinds. A burette delivering 100 cc and graduated into fifths, i.e. each division equalling 0.2 of a cc, is a very convenient size. For some kinds of work, 50 cc divided into tenths, i.e. each division equalling 0.1 of a cc, may be selected. Burettes may be fixed in any convenient stand. They must be vertical and should be so placed that the assayer can read any part of the graduated scale without straining. When not in use they should be kept full of water. When using a burette the water must be run out. The burette is next rinsed with some of the solution to be used and drained, and then it is filled with the solution. Next, squeeze the india rubber tube so as to disentangle air bubbles, and by smartly opening the clip, allow the tube and jet to be filled. See that no bubbles of air are left. Then run out cautiously until the level of the liquid in the burette stands at 0. In reading the level with very dark coloured liquids, it is convenient to read from the level A in figure 27. Reader's note, where the curve of the liquid meets the glass rather than the lower edge of the meniscus. End reader's note. And provided it is done in each reading, there is no objection to this. The accuracy of the reading of a burette is sensibly increased by the use of an Erdmann float. This is an elongated bulb weighted with mercury and fitting somewhat loosely the tube of the burette. It floats in the solution and is marked with a horizontal line. This line is taken as the level of the liquid. If the burette is filled from the top, the float rises with aggravating slowness, and this is its chief disadvantage. The float must come to rest before any reading is made. A convenient plan for filling a burette from below is shown in figure 30. The diagram explains itself. Reader's note. Figure 30 shows a burette on a stand with its mouth over the open neck of a round-bottomed flask. There is a reservoir bottle on a shelf above the top of the burette, and a tube leading from the reservoir down to join the neck of the burette just above its stopcock. There is a clip on the tube connecting the reservoir to the burette. End reader's note. The bottle containing the standard solution is connected with the burette by a siphon arrangement through the glass tube and T-piece. The flow of liquid into the burette is controlled by the clip. When this clip is opened, the burette fills, and when it is closed, the burette is ready for use in the ordinary way. Measuring gases. Lunge's nitrometer is a very convenient instrument for many gasometric methods. It requires the use of a fair quantity of mercury. In figure 31 there is a representation of a piece of apparatus easily fitted up from the ordinary material of a laboratory. It is one which will serve some useful purposes. It consists of a wide-mouthed bottle fitted, by preference, with a rubber cork. The cork is perforated, and in the perforation is placed a glass tube which communicates with the burette. The burette is connected by a rubber tube and a Y-piece, either with another burette or with a piece of ordinary combustion tube of about the same size. The wide-mouthed bottle contains either a short test tube or an ordinary phial with its neck cut off. Reader's note: so the apparatus consists of two parallel burettes standing in clamps, joined at their bottom ends by a Y-tube with a clip in the open neck of the tube beneath them. The top of one burette is connected to the small bottle with the phial in it. End reader's note. In working the apparatus, the weighed substance is put in the bottle and the reagent which is to act on it in the test tube. The cork is then inserted. The liquid in the two burettes is next brought to the same level, either by pouring it in at A or running it out at B. Reader's note: A is the open top of the second burette, and B the neck of the Y connector at the bottom of the burettes beneath the clip. End reader's note. The level of the liquid in the apparatus for correcting variations in volume is then read and noted. Next, after seeing that the level of the liquid in the burette has not changed, turn the bottle over on its side so that the reagent in the test tube shall be upset into the bottle. Then, as the volume of gas increases, lower the liquid in the burette by running it out at B, and at the same time keep the level in A half an inch or so lower than that in the burette. When the action has finished, bring the liquid in the two vessels to the same level and read off the burette. This part of the work must always be done in the same manner. The volume corrector for gas analysis is a graduated glass tube of 120 cc capacity inverted over a narrow glass cylinder of mercury. It contains 0.2 or 0.3 cc of water and a volume of air, which, if dry and under standard conditions, would measure 100 cc. The actual volume varies from day to day and is read off at any time by bringing the mercury inside and outside to the same level. This is done by raising or lowering the tube, as may be required. Any volume of gas obtained in an assay can be corrected to standard temperature and pressure by multiplying by 100 and dividing by the number of cc's in the corrector at the time the assay is made. End of section 5. Section 6 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 6. Reagents, Acids, etc. Acetic acid, HAC bar, or C2H4O2, specific gravity 1.044, containing 33% real acid. An organic acid forming a class of salts, acetates, which are for the most part soluble in water, and which on ignition leave the oxide or carbonate of the metal. It is almost always used in those cases where mineral acids are objectionable. To convert, for example, a solution of a substance in hydrochloric acid into a solution of the same in acetic acid, alkali should be added in excess and then acetic acid. Many compounds are insoluble in acetic acid which are soluble in mineral acids, such as ferric phosphate, ferric arsenate, zinc sulfide, calcium oxalate, and so on, so that the use of acetic acid is valuable in some separations. The commercial acid is strong enough for most purposes and is used without dilution. Aqua regia is a mixture of 1 part by measure of nitric acid and 3 parts of hydrochloric acid. The acids react, forming what is practically a solution of chlorine. Note: 3HCl plus HNO3 equals Cl2 plus NOCl plus 2H2O. End note. The mixture is best made when wanted and is chiefly used for the solution of gold and platinum and for opening up sulfides. When solutions in aqua regia are evaporated, chlorides are left. Bromine, Br, specific gravity 3.0. Practically pure bromine. It is a heavy reddish-brown liquid and very volatile. It boils at 60 degrees centigrade and consequently must be kept in a cool place. It gives off brown irritating vapours, which render its use very objectionable. Generally it answers the same purpose as aqua regia, and is employed where the addition of nitric acid to a solution has to be specially avoided. It is also used for dissolving metals only from ores which contain metallic oxides not desired in the solution. Bromine water is simply bromine shaken up with water till no more is dissolved. Carbonic acid, CO2. A heavy gas somewhat soluble in water. It is mainly used for providing an atmosphere in which substances may be dissolved, titrated, etc. without fear of oxidation. It is also used in titrating arsenic assays with iodine, when a feeble acid is required to prevent the absorption of iodine by the alkaline carbonate. It is prepared, when wanted in solution, by adding a gram or so of bicarbonate of soda, and then as much acid as will decompose the bicarbonate mentioned. When a quantity of the gas is wanted, it is prepared in an apparatus like that used for sulphuretted hydrogen, by acting on fragments of marble or limestone with dilute hydrochloric acid. Citric acid, H3Ci bar, or C6H8O7.H2O, is an organic acid which occurs in colourless crystals, soluble in less than their weight of water. The solution must be freshly prepared, as it gets mouldy when kept. It forms a comparatively unimportant class of salts, citrates. It is used in the determination of phosphoric acid, chiefly for the purpose of preventing the precipitation of phosphates of iron and alumina by ammonia, and in a few similar cases. The commercial crystals are used. They should be free from sulfuric acid and leave no ash on ignition. Hydrochloric acid, HCl in water. Specific gravity 1.16. It contains 32% of hydrogen chloride. It is sometimes called muriatic acid, and when impure, spirit of salt. The acid solution should be colourless and free from arsenic, iron, and sulfuric acid. It forms an important family of salts, the chlorides. It is the best acid for dissolving metallic oxides and carbonates, and is always used by the assayer when oxidizing agents are to be avoided. The acid is used without dilution when no directions are expressly given to dilute it. It has no action on the following metals: gold, platinum, arsenic, and mercury. It very slightly attacks antimony, bismuth, lead, silver, and copper. Tin is more soluble in it, but with difficulty, whilst iron, zinc, nickel, cobalt, cadmium, and aluminium readily dissolve with evolution of hydrogen and the formation of the lower chloride if the metal forms more than one class of salts. All the metallic oxides, except a few of the native and rarer oxides, are dissolved by it with the formation of chlorides of the metal and water. Dilute hydrochloric acid is made by diluting the strong acid with an equal volume of water. This is used for dissolving precipitates obtained in the general course of analysis and the more easily soluble metals. Hydrofluoric acid, HF. A solution in water may be purchased in gutta percha or lead bottles. It is of variable strength and doubtful purity. It must always be examined quantitatively for the residue left on evaporation. It is used occasionally for the examination of silicates. It attacks silica, forming fluoride of silicon, which is a gas. When the introduction of another base will not interfere with the assay, the substance may be mixed in the platinum dish with fluoride of ammonium, or of potassium, or of calcium, and hydrochloric acid, instead of treating it with the commercial acid. It is only required in special work. The fumes and acid are dangerous, and, of course, glass or porcelain vessels cannot be used with it. Iodine, I. This can be obtained in commerce quite pure, and is often used for standardizing. It is very slightly soluble in water, but readily dissolves in potassium iodide solution. It closely resembles chlorine and bromine in its properties, and can be used for dissolving metals without at the same time attacking any oxide which may be present. It is chiefly used as an oxidizing agent in volumetric work, being sharp in its reactions and easily detected in minute quantities. It cannot be used in alkaline solutions, since it reacts with the hydrates and even with the carbonates to form iodides and iodates. Iodine is soluble in alcohol. Nitric acid, HNO3. Specific gravity 1.42. Boiling point 121 degrees centigrade. Contains 70% by weight of hydrogen nitrate. It is convenient to remember that 1 cc of this contains 1 gram of real acid. It combines the properties of an acid and of an oxidizing agent. 1 cc contains 0.76 of a gram of oxygen, most of which is very loosely held and easily given up to metals and other oxidizable substances. Consequently, it will dissolve many metals, etc., upon which hydrochloric acid has no action. All sulfides, that of mercury excepted, are attacked by it, and for the most part rendered soluble. It has no action on gold or platinum, and very little on aluminium. The strong acid at the ordinary temperature does not act on iron or tin, and in most cases it acts better when diluted. Some nitrates, being insoluble in nitric acid, form a protecting coat to the metal, which hinders further action. Where the strong acid does act, the action is very violent, so that generally it is better to use the dilute acid. When iron has been immersed in strong nitric acid, it not only remains unacted on, but assumes a passive state, so that if, after being wiped, it is then placed in the dilute acid, it will not dissolve. Tin and antimony are converted into insoluble oxides, while the other metals, with the exception of those already mentioned, dissolve as nitrates. During the solution of the metal, red fumes are given off, which mainly consist of nitrogen peroxide. The solution is often coloured brown or green because of dissolved oxides of nitrogen, which must be got rid of by boiling. Generally, some ammonium nitrate is formed, especially in the cases of zinc, iron and tin, when these are acted on by cold dilute acid. Sulphur, phosphorus and arsenic are converted into sulphuric, phosphoric and arsenic acids, respectively, when boiled with the strong acid. Dilute nitric acid. Dilute 1 volume of the strong acid with 2 of water. Oxalic acid, H2O bar, or H2C2O4.2H2O. This is an organic acid in colourless crystals. It forms a family of salts, the oxalates. It is used in standardizing. Being a crystallized and permanent acid, it can be readily weighed. It is also used in separations, many of the oxalates being insoluble. For general use, make a 10% solution. Use the commercially pure acid. On ignition, the acid should leave no residue. Sulphuretted hydrogen. Hydrosulfuric acid, SH2. A gas largely used in assaying, since by its action it allows of the metals being conveniently classed into groups. It is soluble in water, this liquid dissolving at the ordinary temperature about 3 times its volume of the gas. The solution is only useful for testing. In separations, a current of the gas must always be used. It is best prepared in an apparatus like that shown in Figure 32, by acting on ferrous sulfide with dilute hydrochloric acid. Reader's note: Figure 32 consists of a large container with 2 stoppers, and in the bottom acid plus ferrous sulfide. One of the stoppers has a glass tube which is connected to a smaller bottle. Its extension into the bottle passes under the surface of a layer of liquid in the bottle, and out of the other side of the smaller bottle comes another tube. So hydrogen sulfide is released from the reaction in the larger vessel, passes through into the smaller vessel, where any acid carried over in the vapour is dissolved in water in the smaller bottle, and the hydrogen sulfide carries on and passes out of the other tube. End reader's note. When iron has to be subsequently determined in the assay solution, the gas should be washed by bubbling it through water in the smaller bottle, but for most purposes washing can be dispensed with. The gas is very objectionable, and operations with it must be carried out in a cupboard with a good draught. When the precipitation has been completed, the apparatus should always be washed out. The effect of this acid on solutions of the metals is to form sulfides. All the metallic sulfides are insoluble in water, but some are soluble in alkaline and some in acid solutions. If sulphuretted hydrogen is passed through an acid solution containing the metals till no further precipitation takes place, a precipitate will be formed containing sulfides insoluble in the acid. On filtering, adding ammonia to render the filtrate alkaline, and again passing the gas, a further precipitate will be obtained, consisting of sulfides insoluble in an alkaline solution, but not precipitable in an acid one. The filtrate may also contain sulfides not precipitable in an acid solution, which are soluble in an alkaline one. These will be thrown down on neutralizing. Again, the metals precipitated in the acid solution form sulfides, which may be divided into groups, the one consisting of those which are soluble, and the other of those which are not soluble, in alkalis. The classification is shown in the following summary. 1. Precipitable in an acid solution. A. Soluble in alkalis. Sulfides of arsenic, antimony, tin, gold, platinum, iridium, molybdenum, tellurium and selenium. B. Insoluble in alkalis. Sulfides of silver, lead, mercury, bismuth, copper, cadmium, palladium, rhodium, osmium and ruthenium. 2. Not precipitated in an acid solution, but thrown down in an alkaline one. Sulfides of manganese, zinc, iron, nickel, cobalt, indium, thallium and gallium. These can again be divided into those which are dissolved by dilute acids and those which are not. 3. Not precipitated in an acid or alkaline solution, but thrown down on neutralizing the latter. Sulfides of vanadium and tungsten. Sulphuretted hydrogen is a strong reducing agent. Ferric salts are thereby quickly reduced to ferrous. In hot solutions, nitric acid is decomposed. These changes are marked by a precipitation of sulphur, and the student must be careful to pass the gas sufficiently long and not be too hasty in concluding that no sulfide will form because it does not at once make its appearance. The best indication that it has been passed long enough is the smell of the gas in the solution after shaking. Sulphurous acid, H2SO3. The reagent used may be regarded as a saturated solution of sulphur dioxide in water. It may be purchased and keeps for a long time. It may be made by heating copper with sulphuric acid and passing the gas formed into water. The heat should be withdrawn when the gas is coming off freely. It is used as a reducing agent and should not be diluted. Sulphuric acid, H2SO4. Note specific gravity 1.84, containing 96% of real acid, H2SO4. End note. This acid forms insoluble sulfates with salts of lead, strontium and barium. It has a high boiling point, 290 degrees centigrade, and when evaporated with salts of the more volatile acids converts them into sulfates. When nitrates or chlorides are objectionable in a solution, evaporation with sulphuric acid removes them. In working with this acid, caution is necessary, since on mixing with water great heat is evolved, and if either the acid or water has been previously heated, a serious accident may result. In diluting the acid, it should be poured into cold water. Glass vessels containing boiling sulphuric acid should be handled as little as possible and should not be cooled under the tap. The action of diluted sulphuric acid on metals closely resembles that of dilute hydrochloric acid. Magnesium, aluminium, iron, zinc, nickel, cobalt, manganese and cadmium dissolve, with evolution of hydrogen, in the cold acid, or when warmed. The action of hot and strong sulphuric acid is altogether different. It acts as an oxidizing agent and is itself reduced to sulfur dioxide or even to sulfur. The following metals are attacked in this way: copper, bismuth, mercury, silver, antimony, tin, and lead. Gold, platinum, and arsenic are not affected. This property is made use of in parting silver from gold and platinum. Metallic sulfides are similarly attacked, but this method of opening up minerals has the disadvantage of giving rise to the formation of anhydrous sulfates of iron, etc., which are not readily dissolved when afterwards diluted. The use of sulfuric acid in assaying is, for these reasons, to be avoided. Its chief use is as a drying agent, since it has a strong affinity for water. Air under a bell jar may be kept dry by means of a basin of sulfuric acid, and gases bubbled through it are freed from water vapour. Dilute sulfuric acid. This is made by diluting 1 volume of the strong acid with 4 of water. Tartaric acid, H2T bar, or C4H6O6. A crystallized organic acid, soluble in less than its own weight of water, or in less than 3 parts of alcohol. It is used for the same purpose as citric acid is. The solution is made when required. Bases, salts, etc. Alcohol, C2H6O. Note: commercial alcohol of specific gravity 0.838. It contains 84% by weight of alcohol. End note. It should burn with a non-luminous flame and leave no residue. It is used for washing precipitates where water is inapplicable, and for facilitating drying. Ammonia, NH3. Note: commercial ammonia, a solution having a specific gravity of 0.88 to 0.89 and containing about 33% of ammonia. End note. It is used as an alkali, more commonly than soda or potash, since an excess of it is easily removed by boiling. The salts of ammonium formed by it may be removed by igniting or by evaporating in a porcelain dish with an excess of nitric acid. It differs in a marked way from soda or potash in its solvent action on the oxides or hydrates of the metals. Salts of the following metals are soluble in an ammoniacal solution in the presence of ammonic chloride: copper, cadmium, silver, nickel, cobalt, manganese, zinc, magnesium, sodium, potassium, and the alkaline earths. Dilute ammonia is made by diluting 1 volume of commercial ammonia with 2 of water. The dilute ammonia is always used, but in assays for copper a stronger solution, 1 of strong ammonia to 1 of water, is required. Ammonic carbonate, Am2CO3, is prepared by dissolving 1 part of the commercial sesquicarbonate of ammonia in 4 parts of water and adding 1 part of strong ammonia. Ammonic bicarbonate, HAmCO3, is prepared by saturating a solution of the sesquicarbonate of ammonia with carbon dioxide. Ammonic chloride, AmCl. Use the commercial salt in a 20% solution in water. The salt should leave no residue on ignition. Ammonic molybdate. The solution is prepared as follows: dissolve 100 grams of the powdered commercial salt in 200 c.c. of dilute ammonia, and pour the solution in a slow stream into 750 c.c. of dilute nitric acid. Make up to 1 litre and allow the mixture to settle before using. It is used for the purpose of separating phosphoric oxide from bases and from other acids, and also as a test for phosphates and arsenates. In using this solution, the substance must be dissolved in nitric acid and a considerable excess of the reagent added. Note: 50 c.c. is sufficient to precipitate 0.1 gram P2O5. Reader's note: phosphorus pentoxide. End reader's note. When the phosphate is in excess, no precipitate will be got. The precipitate is phosphomolybdate of ammonia. Ammonic nitrate, AmNO3, is used in the separation of phosphoric oxide by the molybdate method, and occasionally for destroying organic matter. It is soluble in less than its own weight of water. The solution is made when wanted. Ammonic oxalate, Am2C2O4.2H2O, is used chiefly for the separation of lime. The solution is made by dissolving 15 grams of the salt in 100 c.c. of water. Ammonic sulphide may be purchased in the state of a strong solution. It is yellow and contains the disulphide S2Am2. It serves the same purpose as is obtained by passing a current of sulphuretted hydrogen through an ammoniacal solution, but has the disadvantage of loading the solution with sulphur, which is precipitated when the solution is subsequently acidified. It is useful for dissolving the lower sulphide of tin, SNS. Baric carbonate, BaCO3, is sometimes used for precipitating the weaker bases. It should be prepared when wanted by precipitating a solution of baric chloride with ammonic carbonate and washing. The moist precipitate is used without drying. Baric chloride, BaCl2.2H2O. A crystallized salt, soluble in 2½ parts of water. It is used for the detection and separation of sulfates. Make a 10% solution. Black flux. A mixture of finely divided carbon with carbonate of potash, or with carbonates of potash and soda. It is prepared by heating tartar, or Rochelle salt, until no more combustible gas is given off. 1 gram will reduce about 2 grams of lead from litharge. Borax, Na2B4O7.10H2O. It is chiefly used as a flux in dry assaying, as already described. It is also used in testing before the blowpipe. Many metallic oxides impart a characteristic colour to a bead of borax in which they have been fused. Calcium chloride. The crystallized salt is CaCl2.6H2O. Dried at 200 degrees centigrade it becomes CaCl2.2H2O, and when fused it becomes dehydrated. The fused salt, broken into small lumps, is used for drying gases. It combines with water, giving off much heat, and dissolves in a little more than its own weight of water. Strong solutions may be used in baths in which temperatures above the boiling point of water are required. 1 part of the salt and 2 of water gives a solution boiling at 112 degrees, and a solution of 2 parts of the salt in 1 of water boils at 158 degrees. The salt is very little used as a reagent. Calcium fluoride, or fluorspar, CaF2. The mineral is used as a flux in dry assaying. It renders slags which are thick from the presence of phosphates, etc., very fluid. Mixed with hydrochloric acid, it may sometimes be used instead of hydrofluoric acid. Calcium carbonate, CaCO3. It is precipitated in a pure state by ammonic carbonate from a solution of calcium chloride. It is used for standardizing. In the impure state, as marble or limestone, it is used in the preparation of carbonic acid. Calcium hydrate, or lime water. This is used in testing for carbon dioxide and in estimating the amount of that gas present in air. It may be made by slaking quicklime and digesting the slaked lime with water. 100 c.c. of water at 15 degrees centigrade dissolves 0.1368 grams of the hydrate, CaH2O2, and hot water dissolves still less. Milk of lime is slaked lime suspended in water. Cobalt nitrate, CO (NO3) twice, .6H2O, is used in a 10% solution for the detection of oxides of zinc, aluminium, etc., on ignition with which it forms characteristically coloured compounds. Copper, Cu. Pure copper, as obtained by electrolysis, can be purchased. This only should be used. Copper oxide, CuO. It occurs as a black, heavy and gritty powder, and is used for the oxidation of carbon and hydrogen in organic substances. It should be ignited and cooled out of contact with air just before using, since it is hygroscopic. Oxide of copper which has been used may be again utilized after calcination. Copper sulfate, CuSO4.5H2O, contains 25.4% of copper. It is used in the outer cell of a Daniell battery. The commercial salt is used for this purpose. The recrystallized and pure salt is used for preparing the anhydrous sulfate, which is used for detecting moisture in gases. For this purpose it is dried at 200 degrees centigrade till no trace of green or blue colour remains. It must be prepared when wanted. It may be conveniently used in the form of pumice stone, saturated with a solution of the salt and dried. Traces of moisture develop a green colour. Ferric chloride, Fe2Cl6. Note, when crystallized, Fe2Cl6.6H2O. End note. The solution is prepared as described under iron. The commercial salt contains arsenic, and since the chief use of ferric chloride is for the determination of this substance, it must be purified. Note, see under arsenic. End note. Ferric sulfate, Fe2(SO4) 3 times. End note. Is a yellowish-white deliquescent salt. It is used as an indicator in volumetric silver assaying, and for the separation of iodine from bromine. It may be purchased as iron alum, Am2Fe2(SO4) times 4. 24H2O, but it is best prepared by adding strong sulfuric acid to ferric hydrate in equivalent proportions. Use it as a solution containing 2 or 3% of iron. Ferrous sulfate, FeSO4.7H2O. The granulated form is best and can be purchased pure. It is used for standardizing. It keeps better in crystals than in solution. It is readily soluble in water, but the solution is best made with the help of a little free acid. As a reagent, use a 10% solution. The crystals should be clear bluish green. If their colour is dark green, brown, or blue, they should be rejected. Ferrous sulfide, FeS, is used for the preparation of sulphuretted hydrogen. It may be purchased and broken in small lumps, nut size, for use. Fusion mixture, K2CO3.Na2CO3, is a mixture of potassic and sodic carbonates in the proportions of 13 of the former to 10 of the latter by weight. It is hygroscopic. A mixture of the bicarbonates is better, being purer and less apt to get damp. Gallic acid, C7H6O5.H2O, is an organic acid occurring as a pale fawn-coloured crystalline powder, soluble in 100 parts of cold water or in 3 parts of boiling water. It is used for the determination of antimony. A 10% solution in warm water is made when required. Hydrogen, H, is a gas. It is obtained by acting on zinc with dilute hydrochloric or sulfuric acid. It is used as a reducing agent and for providing an atmosphere free from oxygen. It reduces metallic oxides at a high temperature. It must be freed from water, and special precautions should be taken to prevent an admixture with air. It is generally required in a current which can be continued for an hour or more without interruption. The preparation can be conveniently carried out in the apparatus shown. A quart bottle is half filled with sheet zinc and connected with bulbs filled with sulfuric acid and with a calcium chloride tube. The last is connected with the apparatus through which the gas has to be passed. Dilute hydrochloric acid mixed with a few cubic centimetres (20 cc to 1 pint) of stannous chloride solution to fix any dissolved oxygen is placed in the funnel and let into the bottle by opening the stopcock when required. Care must be taken to let the hydrogen escape for some time before starting the reduction. Gold, Au. Gold, obtained by cupelling and parting, is for most purposes sufficiently pure. It is best kept in the shape of foil. When the purer metal is required, gold should be dissolved in aqua regia, the solution evaporated to a paste, diluted, allowed to stand, and filtered. The filtered solution is acidified with hydrochloric acid, warmed, and precipitated with sodium sulphite. The precipitate is collected, washed, and fused on charcoal. Iron, Fe. The soft wire, thin, is used for standardizing. Rods are used in dry assays as a desulfurizing agent. Steel must not be used, since it is not pure and contains a variable amount of iron. Lead, Pb. Granulated lead or lead foil is used in the dry assay for silver and gold, and in the preparation of lead salts. It can be obtained very pure, but always contains more or less silver, 1 or 2 milligrams in 100 grams. The amount of silver it contains must be determined and recorded. Lead acetate, Pb Ac bar 2.3H2O, or Pb bracket C2H3O2 close bracket 2 times .3H2O, is used as a test, especially for the detection and estimation of sulphuretted hydrogen. Prepare a 10% solution for use. Lead nitrate, Pb bracket NO3 bracket twice, can be purchased pure. It is used for standardizing. Lead dioxide, PbO2, occurs as a dark brown powder. It is used as an oxidizing agent and for absorbing sulphurous oxide. It can be prepared by digesting red lead with warm dilute nitric acid, washing and drying the residue. Litharge, PbO. It can be purchased as a yellow heavy powder. It is used in dry assaying as a flux, as a desulfurizing agent, and also as a source of lead. It always contains some silver, the amount of which must be determined. Litmus. This is an organic colouring matter which is turned red by acids and blue by alkalis. For ordinary purposes it is best used as litmus paper, which may be purchased in small books. A solution is prepared by digesting 15 or 20 grams of the commercial litmus in 100 c.c. of water on the water bath. After being allowed to settle, it is filtered and made just faintly red with acetic acid. Then there is added a drop or two of a solution of soda and 10 c.c. of alcohol. It should be kept in a loosely covered bottle. Magnesia, MgO. It may be purchased as calcined magnesia. It is used for making magnesia mixture and should be kept in a corked, wide-mouthed bottle. Magnesia mixture. Dissolve 22 grams of magnesia in about 1/4 litre of dilute hydrochloric acid, avoiding excess. Add 5 grams of magnesia, boil and filter. Add 300 grams of ammonic chloride and 250 c.c. of strong ammonia, and dilute with water to 2 litres. It should be kept in a stoppered Winchester. Magnesium sulfate, MgSO4.7H2O. It can be purchased very pure and is occasionally used as a standard salt. Manganese dioxide, MnO2. It is used in the preparation of chlorine. The commercial article is not pure, but is sufficiently so for this purpose. Marble, CaCO3. Fragments of the white crystalline variety only should be used. It is used as a source of lime and of carbon dioxide. Mercury, Hg. This can be purchased pure. It should have a bright surface, flow without a tail, and leave no residue on ignition. It is used as a standard, for amalgamation, and as a confining liquid in gas analysis. Mercuric chloride, HgCl2. May be purchased pure. Make a 5% solution in water. It is used for destroying an excess of stannous chloride, for removing sulphuretted hydrogen from solution, and as a test for stannous salts. Microcosmic salt, HAmNaPO4.8H2O. When fused, NaPO3 is formed. It is used in testing for metallic oxides and silica before the blowpipe. The crystals are sometimes used as a standard for phosphoric acid. Nessler's solution. Mode of preparation. Dissolve 35 grams of potassium iodide in 100 c.c. of water. Dissolve 17 grams of mercuric chloride in 300 c.c. of water, and pour this solution into that of the iodide till a permanent precipitate is produced. Make up to 1 litre with a 20% solution of potash. Add mercuric chloride till a precipitate is again formed. Allow to settle and decant. It is used for detecting ammonia. Niter. This is potassium nitrate. Platinum chloride. 2HCl.PtCl4. Note, in the crystallized form it has 6H2O. End note. It may be made as follows. Take 5 grams of clean platinum scrap and dissolve in a flask at a gentle heat in 50 c.c. of hydrochloric acid, with the occasional addition of some nitric acid. Evaporate to a paste, and then dissolve in 100 c.c. of water. It is used for separating and determining potassium. Phenolphthalein is an organic compound used as an indicator, more especially in determining the weaker acids. It cannot be used in the presence of ammonia. Dissolve half a gram in 100 c.c. of dilute alcohol. Potassium bicarbonate, KHCO3. It may be purchased pure. On ignition it leaves the carbonate, K2CO3, which may be used as a standard. Potassium cyanide, KCN. It is used in the dry assay as a reducing agent. The commercial salt is very impure. Purchase that sold as potassic cyanide, gold, which contains about 95% of KCN. It is used for copper assaying and occasionally in separation. Make a 10% solution when wanted. Potassium bichromate, K2Cr2O7. It may be purchased nearly pure. It is used as an oxidizing agent for determining iron and as a test solution. For this last purpose a 10% solution is prepared. Potassium chlorate, KClO3, can be purchased pure. It is used with hydrochloric acid as a substitute for aqua regia. Potassium ferrocyanide, K4Fe (Cn) times 6.3H2O, or yellow prussiate of potash, is used as a test, as an indicator, and for the determination of zinc. Make a 5% solution. Potassium ferricyanide, K6Fe2 (Cn) 12, or red prussiate of potash, is used for testing and as an indicator. Make a 5% solution when wanted, as it decomposes on keeping. Potassium hydrate, KHO. Purchase that purified with alcohol. It is an alkali and is used for absorbing carbonic acid, etc. Potassium iodide, Ki. It may be purchased nearly pure. It is used as a test and for dissolving iodine. It should be used in a 10% solution, freshly made. The solution decomposes on exposure to light, with separation of iodine. Potassium nitrate, KNO3, can be purchased pure. It is used in the dry way as an oxidizing agent. It is very fusible. It decomposes at a low temperature into potassium nitrite, KNO2, and free oxygen, and at a higher temperature leaves potash, K2O. It oxidizes sulfur and carbon with explosive violence. This action may be moderated by mixing the niter with carbonate of soda, common salt, or some other inert body. Potassium nitrite, KNO2. The commercial article is not pure, but is sufficiently so for the purpose required. A saturated solution is used in the separation of cobalt. The solution is made when wanted. Potassium permanganate, KMnO4. This salt can be purchased sufficiently pure. It is much used as an oxidizing agent. Potassium bisulfate, KHSO4, is used as a dry reagent for opening up minerals. It fuses, and at a much higher temperature is converted into potassium sulfate with loss of sulfuric acid. Potassium sulfocyanate, KCNS, is used for the detection and determination of traces of ferric iron, as also in the separation of silver and copper from some of the other metals. Make a 10% solution. It should show no colour on the addition of hydrochloric acid. Red lead, Pb3O4, is used in the dry assay as a flux instead of litharge, from which it differs in containing a little more oxygen. When acted on by nitric acid, a brown residue of lead dioxide is left, nitrate of lead going into solution. Like litharge, it always carries silver, about 2 mg in 100 grams. Silver, Ag, pure silver in foil, is required as a standard. It may be prepared as follows. Dissolve scrap silver in dilute nitric acid and decant off from any residue. Dilute the solution with hot water and add hydrochloric acid until there is no further precipitate. Stir, allow the precipitate to settle, decant and wash. Dry the precipitate, mix it with twice its bulk of carbonate of soda, and fuse the mixture in a crucible until tranquil. Clean the button and roll or hammer it into foil. Sodium acetate, NaC2H3O2.3H2O. The crystals may be purchased sufficiently pure. Make a 20% solution in water. It is used for replacing mineral acids by acetic acid. Note: NaC2H3O2 plus HCl yields H4C2O2 plus NaCl. End note. Sodium acetate and acetic acid. A solution is used in the determination of phosphates and arsenates. 100 grams of the salt is dissolved in 500 c.c. of acetic acid and diluted with water to 1 litre. Sodium bicarbonate, NaHCO3, is used as a flux in dry methods. On ignition, it leaves the carbonate, Na2CO3, which is used as a standard reagent. Make a 20% solution of the carbonate for use. It should be free from chlorides or sulfates, or if impure, the amount of impurities must be determined. Sodium hydrate, NaHO. It may be purchased in sticks, which should be kept in a well-corked bottle. It is sometimes called caustic soda. It is a strong alkali. It is used for neutralizing acid solutions and for separations where ammonia is unsuitable. Make a 5% solution for use. Sodium hyposulfite, Na2S2O8.5H2O. It may be purchased pure. It is generally known as hypo. It is used as a standard. Sodium sulfite, Na2SO3.7H2O, is used as a reducing agent. Sodium phosphate, Na2HPO4.12H2O. The crystals may be purchased pure, but they effloresce in dry air with loss of water. It is used as a standard and for precipitating magnesia, etc. Make a 10% solution. Stannous chloride, SnCl2.2H2O. The crystals are best purchased. If kept dry and free from air, they are fairly permanent. A solution is made by dissolving 20 grams in 10 c.c. of hydrochloric acid and diluting to 1 litre. The solution is not permanent. It is a strong reducing agent and is chiefly used in solution for this purpose. Tin, Sn, grain tin, should be purchased. It is not pure, but contains 99.5% of the metal. The chief impurity is copper. It can be used as a standard. When acted on with hot hydrochloric acid, it slowly dissolves, more rapidly in contact with platinum, and forms stannous chloride. Uranium acetate, UO2, open brackets, C2H3O2, close brackets, 2 times, .H2O. It is best purchased in crystals. The solution is used for the determination of phosphates and arsenates. A solution of 3% strength is occasionally used as an indicator. Uranium nitrate, UO2, open brackets, NO3, close brackets, 2 times, .6H2O. This salt is very soluble in water and is sometimes used instead of the acetate, which is somewhat difficult to dissolve. Water, H2O. Spring or well water is sufficiently pure for most purposes. 100 c.c. will leave a residue of from 10 to 30 milligrams, so that where a salt has to be dissolved out, evaporated and weighed, it should be replaced by distilled water. Rainwater, melted snow, etc. always leave less residue than spring water. but in other respects they are often dirtier. Distilled water is best prepared in the office, a glass or tin condenser being used. Zinc, Zn. It is sold in a granulated form or in sticks. It generally contains over 1% of lead with a little iron and arsenic. It is used for separating metals from their solutions, and generally as a reducing agent, for the preparation of hydrogen, and in most other cases scrap sheet zinc may be used. Zinc oxide, ZnO. The commercial oxide sometimes contains carbonate. Zinc sulfate, ZnSO4.7H2O. It is occasionally used as a standard and can be purchased nearly pure. End of section 6. Section 7 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 7. Formulae, equations, etc. Formulae and equations are a kind of shorthand for expressing briefly and in the language of the atomic theory the facts of chemical composition and reaction. The convenience of this method of expressing the facts justifies a short description of it here. On comparing the percentage compositions of a series of compounds, the proportions in which the elements combine appear to be regulated by no simple law. For example, in realgar, arsenic 71.4%, sulfur 28.6%, iron none, total 100%, orpiment, arsenic 60.9%, sulfur 39.1%, iron none, total 100%. Mispickle, arsenic 46%, sulfur 19.6%, iron 34.4%, total 100%. And pyrites, arsenic none, sulfur 53.3%, iron 46.7%, total 100%. But if in these examples the composition is calculated not on 100 parts, but on 107, 246, 163 and 120 parts respectively, evidence of a simple law becomes apparent. Realgar, arsenic 75.0, sulfur 32.0, iron none, total 107.0. Orpiment, arsenic 150.0, sulfur 96.0, iron none, total 246.0. Mispickle, arsenic 75.0, sulfur 32.0, iron 56.0, total 163.0. Pyrites, arsenic none, sulfur 64.0, iron 56.0, total 120.0. It will be seen that the proportion of arsenic is 75, or twice 75, that of iron is 56, and that of sulfur 32, or some simple multiple of 32. The series of examples might be extended indefinitely, and it would still be found that the combining proportions held good. The number 75 is spoken of as the combining weight, or more frequently as the atomic weight, of arsenic. Similarly, 56 is the atomic weight of iron and 32 the atomic weight of sulfur. The importance of this law of chemical combination is altogether independent of the atomic theory, but this theory furnishes the simplest explanation of the facts. According to it, a chemical compound is made up of exactly similar groups of particles. The particles of each elementary substance are all alike, but differ from those of other elements in weight. Ultimate particles are called atoms, and the groups of atoms are called molecules. The atomic weight of any particular element is the weight of its atom compared with the weight of an atom of hydrogen. The atom of sulfur, for instance, is 32 times as heavy as the atom of hydrogen, and the atomic weight of sulfur is 32. The molecular weight is the sum of the atomic weights of the group. The molecule of pyrites contains 2 atoms of sulfur and 1 of iron. On referring to the table of atomic weights, it will be seen that the atomic weights are sulfur 32 and iron 56. The molecular weight, therefore, is 32 plus 32 plus 56, that is 120. The meaning of this is 120 parts by weight of iron pyrites contain 64 parts of sulphur and 56 parts of iron, and this is true whether the parts by weight be grains or tons. The symbol or formula of an atom is generally the initial letter or letters of the Latin or English name of the substance. The atom of hydrogen is written H, that of oxygen O, of sulphur S, of iron ferrum Fe, and so on. A list of these symbols is given in the table of atomic weights. The formula of a molecule is obtained by placing together the symbols of the contained atoms. Thus, Fe represents an atom of iron, S an atom of sulphur, while FeS represents the molecule of sulphide of iron as containing one atom of each element. When more than one atom of an element is present, this is shown by writing a figure under and after the symbol. Thus, FeS2 represents a molecule with one atom of iron and two atoms of sulphur. Fe2S3 similarly shows one with two atoms of iron and three of sulphur. When a group of atoms is enclosed in brackets, a figure after and under the bracket multiplies all within it. For example, Pb open bracket NO3 close bracket times 2 is another way of writing Pb N2O6. Sometimes it is convenient to represent the atoms of a molecule as divided into two or more groups. This may be done by writing the formulae of the groups and separating each simple formula by a full stop. Slaked lime, for instance, has the formula CaH2O2, or, as already explained, we may write it Ca open brackets HO close bracket times 2. Or, if for purposes of explanation we wished to look on it as lime, CaO, and water, H2O, we could write it CaO.H2O. A plus sign has a different meaning. CaO plus H2O indicates quantities of two substances, water and lime, which are separate from each other. The sign of equality is generally used to separate a statement of the reagents used from another statement of the products of the reaction. It may be translated into the word yields or becomes. The two statements form an equation. Ignoring the quantitative relation, the meaning of the equation CaO plus H2O becomes CaO.H2O is lime and water yield slaked lime. By referring to a table of atomic weights, we can elicit the quantitative relations thus. CaO plus H2O yields CaH2O2. CaO comprises Ca 40, O 16, total 56. H2O comprises H2, 2 from 1 times 2, O 16, total 18. CaH2O2 comprises Ca 40, H2, 2, O2, 32, 16 times 2, total 74. Or putting it in words, 56 parts of lime combine with 18 parts of water to form 74 parts of slaked lime. This equation enables one to answer such a question as this: how much lime must be used to produce 1 hundredweight of slaked lime? For if 74 pounds of slaked lime requires 56 pounds of lime, 112 pounds will require 56 times 112 divided by 74, or about 84 3/4 pounds. As another example, having a closer bearing on assaying, take the following question. In order to assay 5 grams of black tin, SnO2, by the cyanide process, how much potassic cyanide, KCN, will be required? The reaction is SnO2 plus 2KCN yields Sn plus 2KCNO. SnO2 comprises Sn, 118, O2, 32, total 150. KCN comprises K, 39, C, 12, N, 14, 65, times 2 equals 130. What is sought for here is the relation between the quantities of SnO2 and KCN. Note that a figure before a formula multiplies all that follows up to the next stop, or plus or equality sign. The question is now resolved to this: if 150 grams of oxide of tin require 130 grams of cyanide, how much will 5 grams require? 150 to 130 is equivalent to 5 to X. Therefore X equals 4.33 grams. A problem of frequent occurrence is to find the percentage composition of a substance when its formula has been given. For example, what percentage of iron is contained in a mineral having the formula 2Fe2O3.3H2O? Bringing this formula together, we have Fe4H6O9. Find the molecular weight. Fe4 equals 224 from 56 times 4. H6 equals 6 from 1 times 6. O9 equals 144 from 16 times 9. Overall total 374. Then we get 374 parts of the mineral contain 224 of iron. How much will 100 contain? 374 to 224 is equivalent to 100 to X. Therefore, X equals 59.89, and the answer to the question is 59.89%. Again, suppose the question is of this kind: how much crystallized copper sulfate, CuSO4.5H2O, will be required to make 2 litres of a solution, 1 cc of which shall contain 0.0010 of a gram of copper? A litre is 1000 cc's, so therefore 2 litres of the solution must contain 0.001 of a gram times 2000, or 2 grams. How much crystallized copper sulfate will contain this amount of metal? Cu equals 63.3, S equals 32.0, O4 equals 64.0 from 16 times 4. 5H2O equals 90.0 from 18 times 5. Overall total 249.3. If 63.3 grams of copper are contained in 249.3 grams of sulfate, in how much is 2 grams contained? 63.3 to 249.3 is equivalent to 2 grams to X. Therefore, X equals 7.8769 grams. The answer is 7.8769 grams must be taken. As a sample of another class of problem similar in nature to the last, but a little more complicated, take the following. What weight of permanganate of potash must be taken to make 2 litres of a solution, 100 cc's of which shall be equivalent to 1 gram of iron? In the first place, the 2 litres must be equivalent to 20 grams of iron, for there are 20 times 100 cc's in 2 litres. In the titration of iron by permanganate solution there are 2 reactions. First, in dissolving the iron, Fe plus H2SO4 yields FeSO4 plus H2, where the atomic weight of Fe is 56. And second, in the actual titration, 10 FeSO4 plus 2 KMnO4 plus 9 H2SO4 yields 2 MnSO4 plus 5 Fe2 open brackets SO4 close brackets times 3 plus 2 KHSO4 plus 8 H2O, where KMnO4 consists of potassium 39, manganese 55, O4 64, total 158, and total for 2 molecules 316. As before, attention is confined to the 2 substances under consideration, that is, Fe and KMnO4. In the second equation we find 316 parts of the permanganate are required for 10 molecules of FeSO4, and in the first equation 56 parts of iron are equivalent to 1 molecule of FeSO4. Therefore 560 of iron are equivalent to 316 of permanganate, and the question is how much of the permanganate will be equivalent to 20 grams of iron. 560 to 316 is equivalent to 20 grams to X. Therefore X equals 11.286 grams. The answer is 11.286 grams. Very similar to this last problem is the question suggested under the head Indirect Titration. Reader's note: in Chapter 4, Volumetric Assays. End note. If 100 cc's of the standard permanganate solution are equivalent to 1 gram of iron, how much peroxide of manganese will they be equivalent to? The equation for dissolving the iron is already given. The second equation is 2FeSO4 plus MnO2 plus 2H2SO4 yields Fe2 open brackets SO4 close brackets 2 times plus MnSO4 plus 2H2O. MnO2 consisting of Mn 55, O2 32, molecular weight 87. It will be seen that 87 grams of peroxide of manganese are equivalent to 112 grams of iron. How much then is equivalent to 1 gram of iron? 112 to 87 is equivalent to 1 gram to X. Therefore X equals 0.7767 of a gram. It is sometimes convenient to calculate the formula of a substance from its analysis. The method of calculating is shown by the following example. Required, the formula of a mineral which gave the following figures on analysis. Cupric oxide, CuO, 10.58, ferrous oxide, FeO, 15.69, zinc oxide, ZnO, 0.35, sulfuric oxide, SO2, 28.82, water, H2O, 44.71, total 100.15. First, find the molecular weights of CuO, FeO, etc., and divide the corresponding percentages by these figures. Thus, CuO equals 63.3 plus 16 equals 79.3, and 10.58 divided by 79.3 gives 0.1334. Similarly, FeO equals 56 plus 16 equals 72, and 15.69 divided by 72 gives 0.2179. Treated in the same way, the oxide of zinc, sulfuric oxide, and water give as results 0.0043, 0.3602, and 2.484. Classify the results as follows. Bases: CuO 0.1334, FeO 0.2179, ZnO 0.0043, total RO 0.3556. Acids: SO3 0.3602, total RO3 0.3602. Water H2O 2.484 equals R2O 2.484. The figures 0.3556, 0.3602 and 2.484 should be then divided by the lowest of them, that is 0.3556, or where, as in this case, two of the figures are very near each other, the mean of these may be taken, that is 0.3579. Whichever is taken, the figures got will be approximately 1, 1 and 7. The formula is then RO.SO3.7H2O, in which R is nearly 2/5 copper, 3/5 iron, and a little zinc. This formula requires the following percentage composition, which for the sake of comparison is placed side by side with the actual results. Cupric oxide, calculated 11.29, found 10.58. Ferrous oxide, 15.37, found 15.69. Zinc oxide, calculated nil, found 0.35. Sulfuric oxide, calculated 28.47, found 28.82. Water 44.84, found 44.71. Calculated total 99.97, found total 100.15. Trimming the results of an analysis to make them fit in more closely with the calculations from the formula would be foolish as well as dishonest. There can be no doubt that the actual analytical results represent the composition of the specimen much more closely than the formula does, although perhaps other specimens of the same mineral would yield results which would group themselves better around the calculated results than around those of the first specimen analysed. It must be remembered that substances are rarely found pure, either in nature or in the arts, so that in most cases the formula only gives an approximation to the truth. in the case of hydrated salts, there is generally a difficulty in getting the salt with exactly the right proportion of water. Practical exercises. The following calculations may be made. 1. Calculate standards in the following cases. A. Silver taken 1.003 of a gram. Standard salt used 100.15 cc's. B. Iron taken 0.7 of a gram. Bichromate used 69.6 cc's. 2. Calculate percentages. A. Ore taken 1 gram. Solution used 65.2 cc's. Standard 0.987 of a gram. B. Ore taken 1 gram. Barium sulfate got 1.432 of a gram. Barium sulfate contains 13.73% of sulfur, and the percentage of sulfur in the ore is wanted. C. Barium sulfate is BaSO4. Calculate the percentage of sulfur it contains for use in the preceding question. 3. A method of estimating the quantity of peroxide in a manganese ore is based on the following reactions. 1. MnO2 plus 4HCl yields MnCl2 plus Cl2 plus 2H2O. 2. Cl plus Ki yields KCl plus I. To how much MnO2 is 1 gram of iodine, I, equivalent? 4. A mineral has the following composition: carbonic acid, CO2, 19.09, copper oxide, CuO, 71.46, water, H2O, 9.02. What is its formula? 5. How much copper is contained in 1.5 grams of crystallized copper sulfate, CuSO4.5H2O? How much of these crystals must be taken to give 0.4 of a gram of copper? 6. How much ferrous sulfate crystals, FeSO4.7H2O, must be taken to yield 2 litres of a solution, 100 cc's of which shall contain 0.56 of a gram of iron? 7. Galena is PbS, and hematite Fe2O3. What percentages of metal do these minerals contain? End of section 7. Section 8 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 8. Specific gravity. The relation of the weight of a substance to its volume should be kept in mind in all cases where both weight and volume are dealt with. Students are apt to imagine that on mixing equal volumes of, say, sulfuric acid and water, an acid of half the strength must be obtained. If the statement of strength is in parts by weight, this will lead to considerable error. For example, 100 cc's of sulfuric acid containing 98% by weight of real acid will, if diluted with 100 cc's of water, yield a solution containing not 49% by weight, but about 63.5% of the acid. The reason is this: the 100 cc's of sulfuric acid weighs 184 grams and contains 180.32 grams of real acid, while 100 cc's of water weighs only 100 grams. The mixed water and acid weighs 284 grams and contains 180.32 of real acid, which is equivalent to nearly 63.5% by weight. If, however, the method of statement be volumetric, it would be correct to say that doubling the volume halves the strength. If 100 cc's of brine contains 10 grams of salt, and is diluted with water to 200 cc's, it would be of 1/2 the former strength, that is, 100 cc's of the solution would contain 5 grams of salt. This confusion is avoided by always stating the strengths as so many grams, or cc's, in 100 cc's of the liquid. But obviously it would be advantageous to be able to determine quickly the weight of any particular substance corresponding to 1 cc, or some other given volume. Moreover, in descriptions of processes, the strengths of acids and solutions are frequently defined neither by their gravimetric nor volumetric composition, but by a statement either of specific gravity or the degrees registered by Twaddell's or Baume's hydrometer. Thus, in the description of the process of gold parting, one writer gives, "The acid should be of 1.2 specific gravity," and another says, "The acid must not be stronger than 32 degrees Baume." These considerations justify an account of the subject in such a work as this. And, on other grounds, the determination of a specific gravity is one of the operations with which an assayer should be familiar. The meaning of specific gravity is present in the mind of everyone who uses the sentence, "Lead is heavier than water." This is meaningless, except some such phrase as bulk for bulk be added. Make the sentence quantitative by saying, "Bulk for bulk, lead is 11.36 times heavier than water," and one has the exact meaning of the specific gravity of lead is 11.36. A table of the specific gravities of liquids and solids shows how many times heavier the substances are than water. It is better, however, to look upon the specific gravity, written shortly SPG, as the weight of a substance divided by its volume. In the metric system, 1 cc of water at 4 degrees centigrade weighs with sufficient exactness 1 gram. Consequently, the SPG, which states how many times heavier than water the substance is, also expresses the weight in grams of 1 cc of it. So that if a 100 cc flask of nitric acid weighs, after the weight of the flask has been deducted, 120 grams, 1 cc of the acid weighs 1.2 grams, and the SPG is 1.2. The specific gravity then may be determined by dividing the weight of a substance in grams by its volume in cc's, but it is more convenient in practice to determine it by dividing the weight of the substance by the weight of an equal volume of water. And since the volumes of all substances, water included, vary with the temperature at which the SPG is determined should be recorded. Even then, there is room for ambiguity to the extent that such a statement as the following, "The specific gravity of the substance at 50 degrees centigrade is 0.9010, may mean when compared with water at 50 degrees centigrade, or 4 degrees centigrade, or even 15.5 degrees centigrade. For practical purposes it should mean the first of these, for in the actual experiments the water and the substance are compared at the same temperature, and it is well to give the statement of results without any superfluous calculation. In the metric system, the standard temperature is 4 degrees centigrade, for it is at this point that 1 cc of water weighs exactly 1 gram. In England, the standard temperature is 60 degrees Fahrenheit, 15.5 degrees centigrade, which is supposed to be an average temperature of the balance room. The convenience of the English standard, however, is merely apparent. It demands warming sometimes and sometimes cooling. For most purposes it is more convenient to select a temperature sufficiently high to avoid the necessity of cooling at any time. Warming to the required temperature gives very little trouble. Determination of specific gravity. There is a quick and easy method of determining the density or SPG of a liquid, based upon the fact that a floating body is buoyed up more by a heavy liquid than by a light one. The method is more remarkable for speed than accuracy, but still is sufficiently exact. The piece of apparatus used for the purpose is endowed with a variety of names: SPG spindle, hydrometer, areometer, salinometer, alcoholimeter, lactometer, and so on, according to the special liquid upon which it is intended to be used. It consists of a float with a sinker at one end and a graduated tube or rod at the other. It is made of metal or glass. Generally, 2 are required, one for liquids ranging in SPG from 1.000 to 2.000, and another which will indicate a specific gravity between 0.700 and 1.000. The range depends on the size of the instrument. For special work, in which variations within narrow limits are to be determined, more delicate instruments with a narrower range are made. In using a hydrometer, the liquid to be tested is placed in a cylinder, tall enough to allow the instrument to float, and not too narrow. Figure 34. Reader's note.
Figure 34 shows a hydrometer floating partially immersed in a liquid in a glass measuring cylinder. The body of the hydrometer is separated from the walls of the cylinder by approximately its own diameter. End reader's note. The temperature is taken and the hydrometer is immersed in the fluid. The mark on the hydrometer stem, level with the surface of the liquid, is read off. With transparent liquids it is best to read the mark under and over the water surface and take the mean. The graduation of hydrometers is not made to any uniform system. Those marked in degrees Baumé or Twaddell, or according to specific gravity, are most commonly used. The degrees on Baumé's hydrometer agree among themselves in being at equal distances along the stem, but they are proportional neither to the specific gravity nor to the percentage of salt in the solution. They may be converted into an ordinary statement of specific gravity by the following formulae. SPG equals 144.3 divided by 144.3 minus degrees Baumé. Or, putting the rule in words, subtract the degrees Baumé from 144.3 and divide 144.3 with the number thus obtained. For example, 32 degrees Baumé equals an SPG of 1.285. 144.3 divided by 144.3 minus 32 equals 144.3 divided by 112.3, which equals 1.285. This rule is for liquids heavier than water. For the lighter liquids, the rule is as follows. SPG equals 146 divided by 136 plus degrees Baumé. Or, in words, divide 146 by the number of degrees Baumé added to 136. For example, ammonia of 30 degrees Baumé has a specific gravity of 0.880, nearly. 146 divided by 136 plus 30 equals 146 divided by 166, which equals 0.8795. A simple series of calculations enables one to convert a Baumé hydrometer into one showing the actual SPG. Graduation according to SPG is the most convenient for general purposes. In these instruments, the distances between the divisions become less as the densities increase. Twaddell's hydrometer is graduated in this way. Each degree Twaddell is 0.005 in excess of unity. To convert into specific gravity, multiply the degrees Twaddell by 0.005 and add 1. For example, 25 degrees Twaddell equals a specific gravity of 1.125. 25 multiplied by 0.005 equals 0.125 plus 1.000 equals 1.125. There is a practice which ignores the decimal point and speaks of a specific gravity of 1125 instead of 1.125. In some cases it is convenient, and inasmuch as no substance has a real specific gravity of much over 20, it can lead to no confusion. The figures expressed in this way represent the weight of a litre in grams. Some hydrometers are graduated so as to show at a glance the percentage composition of the liquid they are intended to be used with. Gay-Lussac designed one to show the alcoholic strength of mixtures of alcohol and water. The construction of others upon the same principle is easy and perhaps useful, but when the principle is applied to complex liquids and mixed solutions it is misleading. The various methods of graduation ought to give place to one showing a simple statement of the SPG. The method of determining SPG with the hydrometer is obviously inapplicable to the case of solids, and in the case of liquids it should not be used where exact figures are required. There are several other methods which may be used, but on the whole those with the specific gravity bottle are most convenient. The specific gravity bottle is a light flask of about 25 cc capacity, provided with a well-fitting perforated stopper. It is essentially a graduated flask which measures a constant volume, but it does not much matter what the volume is. Reader's note: the stopper of the flask has a very narrow perforation running through it from top to bottom. End reader's note. In taking the specific gravity of a liquid, or
what is the same thing, a fused solid, there is wanted the weights 1 of the flaskful of water and 2 of the flaskful of the liquid. Dividing the second by the first gives the required specific gravity. The actual weighings required are 1 of the dry and empty flask, 2 of the flask filled with water, and 3 of the flask filled with the liquid. The weighing of the flask once made need not be often repeated. It is well to do so now and then for safety's sake, but one weighing will serve for a large number of determinations. The same remarks apply to the weighing of the bottle filled with water. The bottle is dried by rinsing out first with alcohol and afterwards with ether. Ether is very volatile, and a short exposure in a warm place will soon drive off the little remaining about the sides. The ether vapour should be sucked out through a glass tube. See that the bore of the stopper is dry as well as the bottle. Let the dry bottle stand in the box of the balance for a minute or two before weighing. The weight is, strictly speaking, not that of the empty bottle, but of the bottle filled with air. The empty bottle would weigh from 20 to 30 milligrams less. Correcting for this would in most cases only make a difference in the fourth place of decimals, so that it is better to ignore the error. Note: the difference of 20 or 30 milligrams is disregarded here because it detracts equally from the actual weight of the water and liquid to be determined. If the liquid is a heavy one, the difference shows itself in the third or second place of decimals. The correction may be made by deducting from the weight of the flask 0.0012 grams for each gram of water it holds. End note. The weight of the flask filled with water is got by filling it with distilled water and inserting the stopper. The excess of water will overflow at the margin and through the bore. The bottle is wiped with a soft dry cloth, taking care not to squeeze or warm the bottle. The bottle will remain filled to the top of the stopper. It is allowed to stand in the balance box for a minute or two and then weighed. Distilled water, as stated, should be used. The use of ordinary water may increase the weight by 5 or 6 milligrams. Many waters, if they have not previously been boiled, give off bubbles of air which render the weighing worthless. The temperature of the water is of greater importance. Lowering the temperature 2 degrees will increase the weight by 10 or 12 milligrams. A beaker of water may be warmed or cooled to the required temperature. Then the bottle is filled from it and quickly weighed. If the balance room is cooler than the water, the latter will draw back into the bottle and a few small bubbles of air will enter. But even in extreme cases, this will only increase the weight by a very small fraction of a milligram. There is more trouble caused when the room is warmer, for the liquid then expands and protrudes as a drop resting on the top of the stopper. There will in this case be loss by evaporation, which in the case of the more volatile liquids such as alcohol is serious. To prevent this loss, as well as any that may arise by overflow, the stopper should be dilated above into a small cup, which may itself be stoppered. In a bottle of this kind, the neck of the stopper is graduated, and the bottle is considered full when the liquid stands at the level of the mark in the neck. On inserting the stopper, the liquid rises into the cup and is reduced to the level of the mark by absorption with pieces of filter paper. For most purposes, however, there is no need for cooling and allowing room for subsequent expansion. The assayer, as a rule, can select his own standard temperature and may choose one which will always necessitate warming. It will be handier in this case to have a bottle with a thermometer stopper. Of the two types shown in figure 37, that with the external thermometer tube is more generally useful. Reader's note: Figure 37 shows two bottles with thermometer stoppers. In one, the bulb of the thermometer is directly exposed to the liquid within the flask. In the other, the thermometer bulb and stem are within the stopper that sits in the liquid in the flask. The first sort is the external thermometer tube mentioned in the text. End reader's note. The bottle is filled at a lower temperature and is then gently warmed so as to slowly raise the temperature to the required degree. The superfluous liquid is then at once wiped off and the bottle cooled and weighed. The weight of the flask filled with the liquid whose specific gravity has to be determined is ascertained in a similar way. Of course, the temperature must be the same. If the liquid does not mix with water, the bottle should be dried before filling, but otherwise the flask need only be rinsed out 2 or 3 times with the liquid. Having obtained the 3 weighings, deduct the weight of the bottle from each of the others to get the weights of the water and liquid respectively. Divide the latter by the former. The result shows the specific gravity. As an example, take the following, in which a rather large specific gravity bottle was used. 1. Weight of bottle 39.299 grams. 2. Weight of bottle and water 81.884 grams. 3. Weight of bottle and paraffin 73.146 grams. By subtracting 1 from 2 and 3, the result is as follows. 81.884 grams minus 39.299 grams equals 42.585 of water. 73.146 grams minus 39.299 grams equals 33.847 of paraffin. Divide the weight of the paraffin by that of the water. 33.8470 divided by 42.585 equals 0.7948. The specific gravity of the paraffin is 0.7948. The specific gravity of a fusible solid may be obtained in the same way at a temperature some degrees above its fusing point. The specific gravity of a solid in powder or gravel sufficiently fine to pass through the neck of the bottle is easily determined. If the bottle filled with water weighs 50 grams and there is placed on the pan alongside it 20 grams of a sand, the weight of the 2 together will, of course, be 70 grams. But if the sand is put in the bottle, it evidently displaces its own bulk of water, and if, on again weighing, the weight is found to be 62 instead of 70, it is because the 20 grams of sand has displaced 8 grams of water. Bulk for bulk, the sand is 2.5 times as heavy. In practice, the weight of the bottle filled with water will probably be already known. If not, it must be determined. A certain quantity, say 20 grams of the powdered substance, is then transferred carefully to the bottle. The bottle need not be dry inside, but its neck and outside must be. In making this transference, a careful worker will make no loss, and the mode of working saves a little time. But it is better to weigh the dry flask, put into it 10 to 20 grams of the powder, and weigh again. The increase in weight gives accurately the weight of powder in the bottle. About 2/3 fill the bottle with distilled water and mix with the powder by gentle shaking. Air bubbles will disentangle themselves and rise to the surface of the water. Wash back anything adhering to the stopper with a jet of water and fill the bottle almost to overflowing. Allow it to stand for a minute or so, replace the stopper, warm to the required temperature, take off the superfluous moisture, wipe and weigh. As an example, take the following. 1. Weight of bottle 12.681 grams. 2. Weight of bottle filled with water 37.708 grams. 3. Weight of bottle with wolfram 40.821 grams. 4. Weight of bottle with wolfram and water 61.199 grams. Subtract 1 from 3 to get the weight of wolfram taken. 40.821 minus 12.681 equals 28.140 grams. Add the weight of the wolfram to the weight of the bottle filled with water. 28.140 plus 37.708 equals 65.848 grams. Subtract 4 from this to get the weight of water displaced. 65.848 minus 61.199 equals 4.649 grams. Divide the weight of the wolfram by the weight of the water displaced to get specific gravity. 28.140 divided by 4.649 equals 6.053. If the solid is soluble in water or has a tendency to float, some liquid other than water is used. Paraffin oil or oil of turpentine will do. The process is as follows. The weight of the dry and empty bottle having been determined, add a sufficiency of the substance and weigh again to find how much has been added. Fill up with paraffin oil and weigh again. Clean out the substance by rinsing with paraffin, fill up and weigh. Calculate the specific gravity as if water had been used and multiply by the specific gravity of the paraffin.
For example, weight of bottle 39.299 grams, 2. Weight of bottle and nitre 57.830 grams, 3. Weight of bottle and paraffin 73.146 grams, 4. Weight of bottle and paraffin and nitre 84.665 grams, 5. Weight of bottle and water 81.884 grams. First, from 1 and 3 and 5, calculate the specific gravity of the paraffin, as already shown. It will be 0.7948. Deduct 1 from 2 to get the weight of the nitre, 57.830 minus 39.299 equals 18.531 grams. Add this to 3. 18.531 minus 73.146 equals 91.677 grams. And deduct 4 to find the weight of the equal bulk of paraffin. 91.677 minus 84.665 equals 7.012 grams. Divide the weight of the nitre by the weight of the paraffin. 18.531 divided by 7.012 equals 2.6427. The specific gravity, taking paraffin as a standard instead of water, is 2.6427. Multiply this by the specific gravity of paraffin, 0.7948, and the result is 2.1004 as the specific gravity of nitre compared with water. Similarly, a specific gravity compared with water at, say, 50 degrees centigrade can be converted into one compared with water at standard temperature by multiplying by the specific gravity of water at 50 degrees centigrade. The following table gives the specific gravity of water at various temperatures. Reader's note, table omitted, end reader's note. If, for example, a substance at 50 degrees centigrade has a specific gravity of 0.9010, as compared with water at 50 degrees centigrade, it will have, compared with water at 4 degrees centigrade, a specific gravity of 0.9010 times 0.9881, or 0.8903. The figures 0.8903 represent the specific gravity of the substance at 50 degrees centigrade compared with water at 4 degrees centigrade. Except in comparing the specific gravities of the same substance at different temperatures, a calculation of this kind serves no useful purpose. In taking the specific gravity of a solid not in powder, a lump of it is freed from loose particles and its exact weight determined. By means of a horsehair with a slip knot, it is suspended to the balance, and beneath it is placed, out of contact with the balance pan, a beaker of distilled water. The horsehair must be long enough to keep the mineral well beneath the surface of the water, so as to allow the balance to vibrate. Air bubbles are removed by touching with a camel hair pencil. Whilst the mineral is suspended in water, the weight is again taken. It will weigh less than before, and the difference between the two weighings gives the weight of water and consequently the volume displaced by the mineral. The weight in air divided by the difference is the specific gravity. Thus, weight in air equals 3.2170, weight in water equals 2.7050, difference 0.5120 grams. 3.2170 divided by 0.5120 equals 6.28, the specific gravity. The specific gravity of a substance depends mainly on its composition, but is affected by certain conditions. The effect of temperature has already been considered. Air holes and empty spaces lessen the specific gravity of otherwise solid bodies, and metals which, after fusion, become imperfect solids have their density increased by hammering or rolling. But metals, when free from pores, have their density diminished when rolled without annealing. The effects of these conditions are slight when compared with those due to the presence of impurities. For simple substances or mixtures of only two substances, a determination of specific gravity is a sufficient check on the composition for many practical purposes, and with more complex mixtures such as slags and some of the products of dressing operations, in which the material does not differ much in its nature from time to time, such a determination will yield information of considerable value and afford a check upon the proper working of a process. When the mixing of two substances is accompanied by a change in volume, the specific gravity of the mixture can only be learnt by experiment. But when the substances have no such action on each other, the resulting specific gravity can be calculated. Some of these calculations have a practical interest as well as an educational value. Students should practice them so as to become familiar with the relations between weight and volume. When substances are mixed by volume, the specific gravity of the mixture is the mean of those of its constituents, and may be calculated in the usual way for obtaining averages. 1 cc of a substance having a specific gravity of 1.4 mixed with 1 cc of another having a specific gravity of 1.0 will yield 2 cc's of a substance having a specific gravity of 1.2. If, however, we write gram instead of cc's in the above statement, the resulting specific gravity will be 1.16. The simplest plan is to remember that the specific gravity is the weight divided by the volume, and the specific gravity of a mixture is the sum of the weights divided by the sum of the volumes. In the above example, the sum of the volumes is 2 cc's. The weights, got by multiplying each volume by its corresponding specific gravity, are 1.4 grams and 1 gram. The sum of the weights divided by the sum of the volumes is 2.4 divided by 2, or 1.2. The specific gravity of a mixture of 10 cc's of a substance having a specific gravity of 1.2 with 15 cc's of another having a specific gravity of 1.5 may be thus found. SPG equals 12 plus 22.5 divided by 10 plus 15 equals 1.38. Multiply each volume by its specific gravity to get its weight. 10 times 1.2 equals 12, and 15 times 1.5 equals 22.5. Add these together, 12 plus 22.5 equals 34.5, and divide by the sum of the volumes. 10 plus 15 equals 25. 34.5 divided by 25 equals 1.38. The specific gravity will be 1.38, provided the mixture is not accompanied by any change of volume. The same formula will serve when the proportion of the ingredients is given by weight. A mixture of 4 parts by weight of galena, specific gravity 7.5, with 5 parts of blend, specific gravity 4, will have a specific gravity of 5.06. SPG equals 4 plus 5 divided by 0.53 plus 1.25 equals 9 divided by 1.78 equals 5.06. It is necessary in this case to calculate the volumes of the galena and of the blend, which is done by dividing the weights by the specific gravities. Thus 4 divided by 7.5 gives 0.53, and 5 divided by 4 gives 1.25. The converse problem is a little more difficult. Given the specific gravity of a mixture and of each of the 2 ingredients, the percentage by weight of the heavier ingredient may be ascertained by the following rule, which is best expressed as a formula. There are 3 specific gravities given. If the highest be written H, the lowest L, and that of the mixture M, then percentage of heavier mineral equals 100 times H times open bracket M minus L, close bracket, all divided by M plus open brackets H minus L, close bracket. Suppose a sample of tailings has a specific gravity of 3.0 and is made up of quartz, SPG 2.6, and pyrites, SPG 5.1. Then the percentage of pyrites is 27. 100 times 5.1 times 3 minus 2.6 divided by 3 times 5.1 minus 2.6 equals 510 times 0.4 divided by 3 times 2.5 equals 204 divided by 7.5 equals 27.2. The same problem could be solved with the help of a little algebra by the rule already given, as thus. The SPG of a mixture equals the sum of the weights of the constituents divided by the sum of the volumes. Then 100 grams of the tailings with X% of pyrites contains 100 minus X% of quartz. The sum of the weights is 100. The volume of the pyrites is x divided by 5.1 and of the quartz 100 minus x divided by 2.6. Then we have by the rule 3 equals 100 divided by open brackets x over 5.1 plus 100 minus x over 2.6 close brackets. 3 equals 1326 divided by 510 minus 2.5x. 204 equals 7.5x and x equals 27.2. If the percentage P and specific gravity H of one constituent and the SPG M of the mixture are known, the SPG of the other constituent may be calculated by the following formula, in which x is the required SPG. X equals open brackets 100 minus P close brackets times M times H, all divided by open brackets 100 times H close brackets minus P times M. For example, tailings, specific gravity 3.0, containing 27.2% of pyrites, SPG 5.1, will contain 100 minus 27.2, that is 72.8%, of earthy matter, having a mean specific gravity of x. X equals 100 minus 27.2, all multiplied by 3 times 5.1, divided by 100 times 5.1 minus 27.2 times 3, which equals 113.84 divided by 428.4, which equals 2.6. The differences in specific gravity corresponding to differences in strength have been carefully determined and tabulated in the case of the stronger acids and of many other liquids. Such tables are given at the end of this book. To calculate the weight of a measured volume of mineral or rock, multiply the cubic feet by 62.4 and then multiply by the specific gravity of the stuff. The answer gives the weight in pounds. For example, 100 cubic feet of quartz weighs 100 times 62.4 times 2.6 equals 16,224 pounds. The weight of any mass of mineral of known extent and specific gravity is ascertained in this way. The following table gives the specific gravities of some of the commoner minerals: barytes 4.5, blende 4.0, calcite 2.6, cassiterite 6.9, chelybite 3.8, copper pyrites 4.2, fluor 3.1, galena 7.5, hematite 5.0, mispickel 6.2, pyrites 5.0, quartz 2.6.
End of section 8. Section 9 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 9. Silver, Gold, Cyanides, Platinum, Mercury. Part 1. Silver. Silver is widely diffused and has been found in most mining districts. It occurs native in sufficient quantity to constitute one of the chief ores of the metal. It also occurs combined with sulphur, as in argentite, with sulphur and antimony, as in stephanite or brittle silver ore, and in pyrargyrite, or ruby silver, and with copper, sulphur, antimony, and arsenic, as in polybasite. Chloride of silver occurs native as horn silver or kerargyrite. Silver is found in the ores of other metals, such as fahlerz, which sometimes contains from 2 to 10% of the metal, and galena, which is an important source of it. In fact, galena is never found entirely free from silver. It is present also in greater or less quantity in the ores of copper and zinc. Silver dissolves readily in nitric acid, forming silver nitrate. It only forms one family of salts, and of these the chloride and nitrate are of chief importance to the assayer. The formation of the chloride of silver, on the addition of hydrochloric acid or a soluble chloride to the nitric acid solution, serves for the recognition and separation of silver. The precipitated chloride is white, becoming violet on exposure to light, insoluble in nitric acid, soluble in ammonia, hyposulfite of soda, or concentrated solutions of chlorides. The best confirmatory test is made by wrapping the precipitate in a little sheet lead and cupelling, when the silver will be left in the metallic state and is easily recognized. Dry assay. This assay is made up of two parts. 1. The concentration of the silver in a button of lead, and 2. The cupellation of the resulting alloy. The concentration of the button of lead may be affected either by scorification or by fusion in a crucible. The scorification assay is performed in a scorifier, which is a very shallow open-mouthed dish about 2½ inches across, with a very thick bottom to enable it to withstand the corrosive action of the slag. A charge of more than 3 or 5 grams of the ore cannot be worked in one, and with such small charges the unavoidable variations have a serious effect on the figures reported. A difference of 1 milligram on the weight of the button of silver got represents a difference of 6 or 10 ounces per ton. With rich ores, such variation is unavoidable under any conditions, and the only safe plan is to take the mean of several assays. But with poorer ores, the accuracy of the assay, as well as convenience in working, is much increased by working in a crucible with larger charges. In scorification, the proportions of lead required for scorifying 1 gram of ore is, in average cases, from 10 to 15 grams, sinking in the case of galena to 2 grams, and rising with earthy and refractory substances to from 30 to 40 grams. But by fusing in a crucible with well-selected fluxes, a proportion of 4 of flux to 1 of ore is generally sufficient. And not only is the proportion of added matter less, but it is also easier to manipulate large quantities in crucibles, so that although in some cases the crucible assay is more troublesome and less satisfactory, yet with poor and earthy ores it is the best method of dealing with them, while when properly worked it yields results as accurate as scorification does. As a general rule, if more than 5 grams of ore must be taken, the crucible assay should be adopted. Scorification assay. The charge of ore is usually 3 grams, sometimes 5. The lead varies from 30 to 70 grams, and the quantity of soda, borax, or powdered glass added varies from 0.3 to 3 or 4 grams. It is generally recommended to have the lead granulated, and to mix the ore with about half of it in the scorifier, then to put on the rest of the lead, and finally to sprinkle the borax or glass on the top. Note: lead may be granulated by heating it to a little above the melting point, pouring it into a closed wooden box, and rapidly agitating it as it solidifies. End note. It answers just as well, however, to use the lead in the shape of foil and wrap the ore up in it, and if the ore contains much sulphur, the borax may with advantage be added, wrapped in a little tissue paper, some 5 or 10 minutes after the operation has started. The process of scorification is as follows. A scorifier of convenient size having been selected, one 2½ inches across is most generally useful. It is dried at a gentle heat for about 10 minutes. The charge is then put into it, and it is introduced with the help of a scorifier tongs into a muffle heated considerably above redness. Reader's note: the scorifier is a circular shallow dish with sloping sides and a shallow depression in the top, perhaps 1/3 of the depth of the overall scorifier. The scorifier tongs resemble a long pair of tweezers, with the lower arm having a U-shaped extension to hold the scorifier, where the upper arm presses on the top of the scorifier. End reader's note. The muffle is then closed, and when the metal has melted down it is opened, but the temperature is kept up. A ring of slag will, after a time, form around the metal, and when this appearance, known as the eye, presents itself, the temperature may be lowered. When the eye has disappeared, that is, when the layer of slag has quite closed in, a pinch of powdered culm wrapped in tissue paper is added. As soon as the slag has again become tranquil, the scorifier is taken out and its contents are poured into a mould. The slag is detached and saved. Reader's note: the mould consists of 2 hemispherical depressions in an oblong block. End reader's note. If the button of metal weighs more than 30 grams, its size is reduced by another scorification in the same scorifier, which should have been replaced in the muffle immediately after the contents had been poured out. If the ore is not a very rich one, the button of lead will carry practically all the silver, but with rich ores it is more satisfactory to save the slag and subsequently to melt it down with the cupel on which the lead has been treated, so as to recover the silver lost in the slag together with that absorbed in the cupel at one operation. Or, if the cupellation loss is neglected or calculated in some other manner, the slag or slags from the scorifier may be powdered and mixed with 20 grams of oxide of lead, 5 grams of borax and 1 gram of charcoal. This should be melted down in a small crucible and the resulting button of lead cupelled. If the scorification has been unsatisfactory, the quantity of silver obtained from the slag will be by no means inconsiderable. The usual explanation is that with sulphury ores, compounds of metallic oxides and sulfides, oxysulfides, are formed, which remain in the slag, retaining considerable quantities of the precious metal. It is said that under certain conditions such a slag may contain as much as 10% of silver. An excess of lead and a high temperature prevents the formation of these oxysulfides. But if much silver is present in the ore, the slag cannot be safely thrown away, even if sulphur is absent and the process has been satisfactorily performed. If the crust which appears on the surface of the lead does not clear, add a small lump of borax and 20 grams more lead. Then close the muffle and keep the temperature as high as possible. If the slag forms properly but shows unfused or only half-fused lumps, even when the scorification has proceeded for some time, add more borax and stir with an iron rod. The slag adhering to the rod must be detached by hammering and replaced in the scorifier. If the ore consists largely of quartz, soda should be added instead of borax, or if it contains much copper, powdered quartz may be used. If the scorifier at the end of an operation is more than usually corroded, the borax should be replaced in subsequent assays on similar ores by powdered glass or quartz. If a fairly fluid slag is formed which does not clear from the metal and show the eye, more lead and a higher temperature is wanted. As a general rule, it may be stated that when a scorification is unsatisfactory, what is wanted is more heat, more lead, or more borax. It is a safe plan when work has to be done on a strange ore to make 3 or 4 assays with varying quantities of lead. The proportion of lead is right when a further addition does not yield a higher result. The proper proportion having been found, a note of it should be made for further use. Pot assays. The object of the fusion in a crucible, like that of scorification, is to concentrate the silver in a button of lead, which is to be subsequently cupelled, and to retain the earthy and waste matters in the slag. It is necessary to consider the quality of the slag and the weight and quality of the lead. The slag, when fused, should be liquid and homogeneous, and not too corrosive on the crucible. The button of lead should be soft, malleable, and free from a coating of regulus. Note: a rod of iron placed in the crucible with the assays will decompose any regulus that may be formed. End note. In weight, it should not differ much from the ore taken. With 20 grams of ore, for example, a button of lead weighing from 18 to 25 grams will be satisfactory. Less than this would leave an undue proportion of silver in the slag, and more would be unnecessarily large for cupelling and would increase the loss in that operation. With average ores, take 20 grams of the powdered ore and mix with 30 grams of soda, 40 grams of red lead or litharge, 5 grams of borax, and from 2 to 2.5 grams of flour, and place in an E crucible. Note: Battersea round. End note. Put these in the furnace at a red heat, cover the crucible, and gradually raise the temperature until the whole charge has melted down and is in a state of tranquil fusion. Pour into a mould and replace the crucible in the furnace. As soon as the lead is solid, detach the slag and put it back into the crucible, and when it is again fluid, charge onto it with a copper scoop a measure of 20 grams of oxide of lead and 1 gram of charcoal. When fusion has again become tranquil, pour and detach the button of lead. The lead buttons should be hammered into discs with rounded edges and be freed from slag. If too big for a cupel, they may be scorified together in a small scorifier, but it is better to cupel them separately. Ores containing metallic oxides. Peroxides of iron, manganese and copper interfere by counteracting the effect of the charcoal or flour, and thus reducing the size of the lead button. Peroxide of iron will reduce the weight of lead by a little more than its own weight, and peroxide of manganese has about twice this effect. When these oxides are present, an additional quantity of flour must be used, and precautions must be taken to prevent reoxidation of the slag by the furnace gases. This may best be prevented by using a layer of common salt as a cover to the charge. When the ores contain a good deal of quartz or stony matter, the fluxes just given, for average ores, will do, but the proportion of soda should be diminished, and that of the borax, oxide of lead, and flour increased, as the quantity of metallic oxides become greater. If the ore contains practically no quartz, the soda may be altogether omitted, and some glass or powdered quartz added. The following charge may be taken as an example. Weigh up to 20 grams of the powdered ore, 15 grams each of soda and borax, 60 grams of oxide of lead, and 5 grams of flour. Mix and place them in an E crucible, and cover with a layer of from 1/4 to 1/2 inch of common salt. Place in the furnace as before. The salt will give off a considerable amount of fume, which will to a certain extent conceal the state of the charge. When the crucible has been in the furnace for about 25 minutes, remove it and pour out the contents immediately. With ores that produce a thick slag, the addition of 5 grams of fluorspar will be an advantage. It may happen that with an unknown ore the first assay will be more or less unsatisfactory, but from it the necessity for adding more or less flour will be learnt, and a second assay, with the necessary modification of the charge, should give a good result. Ores containing much sulphides. Ores of this class may be easily recognized either by the appearance of the minerals they contain, or by the odour of sulphurous oxide, SO2, which they evolve when roasted on a spatula. The sulphides most commonly present, in addition to the sulphurized minerals of silver, are pyrites, galena, blende, and mispickel. When they are present in only a moderate amount, their effect is simply to increase the weight of the button of lead, and this is easily counteracted by reducing the amount of flour or by omitting it. When in larger amounts, they not only yield large buttons, but also render the metal sulphury, sometimes even giving a button of regulus instead of lead. This last evil may be remedied, 1, by putting in a rod of iron as soon as the charge has fused, or 2, it may be counteracted by a proper addition of nitre, or 3, when the sulphides present are only those of iron or copper, the sulphur may be removed by calcining, and the ore converted into one of the class containing metallic oxides. The calcination is effected as follows. Weigh up 20 grams of the powdered ore and place it in a wide-mouthed crucible sufficiently large to perform the subsequent melting down in. The roasting must be done at a gentle heat at first, so as to avoid clotting. The mouth of the crucible should project considerably above the coke, and should slope forward towards the worker. The charge must be occasionally stirred with the stirrer, so as to expose fresh surfaces to the action of the air, and to prevent adhesion to the sides of the crucible. The stirrer should not be removed till the calcination is finished. The temperature should be raised at the end to a good red heat, and to ensure the decomposition of any sulphate that may be formed, the roasted ore should be rubbed up in a mortar with a pinch of anthracite, and again calcined. It is then mixed with fluxes as described, and fused in the same crucible. The calcination of an ore is a work occupying a good deal of time, and in most cases it is better to take advantage of the desulphurizing power of red lead or nitre. Red lead by itself will do, but a large quantity of it will be required. 1 part of a metallic sulphide needs from 20 to 50 parts of red lead to yield a button free from sulphur, whereas at most from 2 to 2.5 parts of nitre are sufficient. There is sometimes an advantage in having a considerable excess of oxide of lead in the slag, but where there is no such reason, 2 parts of red lead to 1 of ore is enough. A charge which will do for most sulphides is the following: 20 grams of ore, 40 to 100 grams of red lead, 20 grams of soda, 5 of borax, and sufficient nitre, or perhaps flour, to give a button of about 25 grams of lead. How much this must be, if not already known, may be approximately determined by fusing 3 grams of the ore and 3 grams of soda in a small crucible, note a C crucible, end note, with 50 grams of litharge, not red lead, under a cover of salt, and weighing the resulting button of lead. Subtract 3 from the weight of lead obtained, and the difference multiplied by 1.3 will give the quantity in grams of nitre required. If the button of lead weighs less than 3 grams, flour must be added. If this is not satisfactory, repeat the assay, adding an extra gram of nitre for each 4 grams of lead in excess of that required, or 1 gram of flour for a 12 gram deficiency. In the method in which iron is used as a desulfurizing agent, only as much oxide of lead should be added as will give a button of lead of the required size. Rather, a large button of lead should be got, and the slag should be strongly alkaline. If the ore does not already carry a large amount of sulphur, some should be added. The fusion should be performed at a low temperature, similar to that for a galena assay, and should be continued for some time after it has become tranquil. Take 20 grams of the ore, 40 grams of soda, 40 grams of oxide of lead, and 5 or 10 grams of borax. Place this mixture in a crucible with a rod of iron, as in the galena assay, cover, and fuse for about half an hour. Take out the rod, washing it in the slag, and in a minute or two pour. Clean and cupel the button of lead. General remarks on the fusion. Other things being equal, the smaller the quantity of the slag, the better, provided there is sufficient to cover the metal. The presence of peroxides of the heavy metals is prejudicial, since they tend to increase the quantity of silver retained in the slag. It may be given as a general rule that when iron, copper, manganese, etc. are present, there is a more than ordinary need for cleaning the slags, and care must be taken to keep these metals in the state of lower oxide. In selecting the fluxes, it should be remembered that soda is the best for quartz and borax for lime and metallic oxides, and that with ores almost free from gangue, some quartz or glass should be added to protect the crucible. 2 parts of soda are enough to flux 1 part of quartz, whilst of borax or oxide of lead 4 parts are barely sufficient. Oxide of lead has the advantage of being heavy, and so does not occupy much space in the crucible. On the other hand, if the melting down be performed too quickly, or if oxide of lead only is used, this high specific gravity is a disadvantage, for the lighter earthy matter floats as a pasty mass on the more fluid oxide of lead, and thus escapes its action. When metallic sulphides are present in the ore, an excess of oxide of lead helps to keep the sulphur out of the button of metal. In addition to the oxide of lead required as a flux, some will be required to provide the lead in which the silver is to be collected. Oxide of lead mixed with charcoal or flour yields, when heated, a multitude of minute buttons of metal uniformly distributed through the mass of the charge. As the charge melts down, these run together and fall to the bottom. This shower of lead collects the silver more easily than a single button at the bottom of the crucible could do. Only that portion of the oxide of lead which remains in the slag can be considered as a flux. Very often the first indication of an excessive reduction of lead is the pastiness of the slag rendered thick by the withdrawal of the oxide of lead which would have kept it fluid. If in an assay it is found that 5 parts of flux are not sufficient for 1 part of ore, the remedy lies in using a different flux rather than in taking a larger quantity. On the reducing effect of charcoal, flour, and tartar. The weight to be got from a given charge will depend, provided sufficient oxide of lead is present, upon the proportion of the reducing agents in it. We have thought it well to illustrate this part of the subject by a series of experiments, which the learner will do well to practice for himself before proceeding to the assay of actual ores. Take 80 grams of litharge and 20 grams of a mixture of borax and soda. Fuse 3 lots. 1 with 1.5 grams of charcoal, 2 with 3 grams of flour, and 3 with 7.5 grams of tartar. Weigh the buttons of lead obtained, and divide each by the weight of reducing agent used. The results will differ somewhat with the dryness and quality of the flour, etc. used. In one series of experiments they were as follows. 1.5 grams of charcoal gave 34 grams of lead, therefore 1 gram of charcoal gives 22.6 grams of lead. 3.0 grams of flour gave 33.5 grams of lead, therefore 1 gram of flour gives 11.2 grams of lead. 7.5 grams of tartar gave 38.0 grams of lead, therefore 1 gram of tartar gave 5.0 grams of lead. The use of flour as a reducing agent has many advantages, and it is well to remember that 1 gram of flour reduces about 11 grams of lead, and that charcoal has twice and tartar 1/2 this reducing effect. On the reducing effect of charcoal, etc., on red lead. It is often easier to obtain red lead of good quality than it is litharge, and by a large number of assayers red lead is the form of oxide of lead always used. Red lead, however, contains an excess of oxygen, which will use up some of the reducing agent before lead separates out. On making a series of experiments similar to the last, but using 80 grams of red lead instead of the litharge, the results were, with the same quantities of the reducing agents, with charcoal 18 grams of lead, with flour 18 grams of lead, with tartar 22 grams of lead. Comparing these with the results with litharge in the previous table, it will be seen that the same quantity of reducing agent has in each case brought down 16 grams less of lead, so that a larger amount of the reducing agent must be added to get a button of the same weight as that obtained with litharge. To get a button of a desired weight, say 22 grams, we must add reducing agent sufficient to throw down 22 plus 16, or 38 grams of lead, which would require 3.4 grams of flour. If this amount of flour is fused with 80 grams of red lead, a button of lead weighing 22 grams will be formed, the other 16 grams being kept up by the oxygen of the red lead. If the quantity of red lead differs from 80 grams, this rule must be modified. With 40 grams of red lead, for example, we should add an excess of reducing agent sufficient to throw down 8 grams of lead instead of 16. Similarly, with 160 grams of red lead, we should add enough to throw down 32 grams. The following rule will enable one to calculate the weight of flour required to produce a button of lead of any desired weight from any given quantity of red lead. Each 5 grams of red lead present diminishes the weight of the lead by 1 gram. If then we divide the weight of red lead in a charge by 5, and add this to the weight of lead required, the sum, divided by 11, will give the weight of flour which must be added. Using 80 grams of red lead and wanting a button of 20 grams, we should add 3.3 grams of flour. 80 divided by 5 equals 16, 16 plus 20 equals 36, 36 divided by 11 equals 3.3 nearly. The following are some results obtained which will illustrate the rule. Red lead used 40 grams, flour used 3 grams, lead got 25 grams. Red lead used 100 grams, flour used 3 grams, lead got 13.5 grams. Red lead used 80 grams, flour used 4 grams, lead got 30.0 grams. Red lead used 80 grams, flour used 5 grams, lead got 40 grams. On the reducing effect of metallic sulfides and the counteracting effect of nitre. The sulfides found in ores will reduce a button of lead from oxide of lead just as flour does, and as charcoal, flour and tartar differ in their reducing power, so equal weights of the different mineral sulfides throw down different weights of lead. 1 gram of iron pyrites yields about 11 grams of lead. 1 gram of copper pyrites, blend, fahlerz or mispickle yields 7 or 8 grams of lead, while 1 gram of antimonite will give 6, and 1 gram of galena only a little over 3 grams. It is evident that if an ore carries much of these sulfides, the quantity of lead reduced will be very much larger than that required for an assay. To counteract this effect, nitre is added. 1 gram is added for each 4 grams of lead in excess of that required. For example, with a 20 gram charge of an ore containing 50% of pyrites, if no nitre were added, 110 grams of lead would be got. Or if there was not sufficient oxide of lead to yield this quantity of metal, the button would be sulphury. To reduce the weight of the button by 80 grams, we should add 20 grams of nitre if litharge were used. or if red lead were used, we should add 16 grams of nitre, since the oxidizing effect of 20 grams of red lead is equivalent to that of 1 of nitre, and since 80 grams of red lead are generally used in a charge. 2 assays of an ore of this kind, with these quantities of nitre, gave 26.0 grams of lead with litharge and 22.5 grams with red lead. It is best to use in these assays 80 grams of red lead, 20 of soda and 5 of borax, with 20 grams of the ore. If the lead got by the preliminary fusion in a small crucible with litharge, described under ores containing much sulfides, is known, the following table will indicate the quantity of nitre or flour to be added with this charge. Reader's note. There are 3 columns of figures. Lead got in preliminary fusion with 3 grams of ore, flour to be added to the assay, nitre to be added to the assay. This has been abbreviated to lead, flour and nitre. End reader's note. 0.0 grams of lead, 3.3 grams of flour, no nitre. 3.0 grams of lead, 1.3 grams of flour, no nitre. 6.0 grams of lead, no flour, 4.0 grams of nitre. 9.0 grams of lead, no flour, 9.0 grams of nitre. 12.0 grams of lead, no flour, 14.0 grams of nitre. 15.0 grams of lead, no flour, 19.0 grams of nitre. 18.0 grams of lead, no flour, 24.0 grams of nitre. 21.0 grams of lead, no flour, 29.0 grams of nitre. If litharge is used in the assay instead of red lead, 4 grams more nitre or 1.5 grams less flour must be used. When more than a few grams of nitre are added to a charge, the proportion of soda and borax should be increased, because one of the products of the reaction of nitre upon sulfides in the presence of soda is sulfate of soda, and because the soda thus used up no longer serves as a flux. More borax should be added, as it is the best flux for the metallic oxides which are formed in the process. If in an assay too large a button of lead is got, even after this calculation has been made, and the assay is repeated, add 1 gram more nitre for each 4 grams of lead in excess. Sometimes the assay appears tranquil before the nitre has produced its full effect. In such cases it is well to seize the crucible with the tongs and mix its fused contents by rotating them. If this causes an effervescence, the crucible should be replaced in the fire and the fusion continued. The following experiments will illustrate the extent to which the above rules may be relied on. In all of them, the standard flux was used, that is, 80 grams of red lead, 20 of soda and 5 of borax. Reader's note. These experimental results have been omitted. They cover the lead retrieved in the presence of pyrites, copper pyrites, antimonite, galena, and blende, using red lead and litharge. End reader's note. The variation in some of these experiments, in which we might have expected similar results, is due to the fact that the sulphur, and in some cases the metals, are capable of 2 degrees of oxidation. For example, theoretically, 1 gram of iron pyrites, FeS2, would yield 8.6 grams of lead if the sulphur were oxidized to sulphurous oxide, SO2, and the iron to ferrous oxide, FeO, whilst if the sulphur were oxidized to sulfate, SO3, and the iron to ferric oxide, 12.9 grams of lead will be thrown down. Similarly, the yield with copper pyrites would be 7.5 or 11.6, with blende 6.4 or 8.5, with antimonite 5.5 or 8, and with galena 2.6 or 3.4. As regards the metals, the lower oxide will always be formed if the assay is carried out properly, fused under a cover and with a sufficiency of reducing agent. But the proportion of sulphur oxidized completely will vary with the conditions of the assay. With a slag containing much soda, the tendency will be to form sulfate, and in consequence a big reduction of lead, whilst with an acid slag containing much quartz, the tendency will be for the sulphur to go off as sulphurous oxide, SO2. In a fusion with litharge alone,
all the sulphur will be liberated as the lower oxide, whilst with much soda it will be wholly converted into sulphate. For example, 3 grams of an ore containing a good deal of pyrites and a little galena gave, when fused with litharge, 16.5 grams of lead. A similar charge, containing in addition 20.0 grams of soda, gave 22.5 grams of lead. It will be noted from the experiments that 1 gram of nitre kept up on the average 4 grams of lead, the range being from 3.2 with acid slags to 5.3 with very basic ones. These facts serve to explain some apparently irregular results got in practice.
End of section 9. Section 10 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 9. Silver, Gold, Cyanides, Platinum, Mercury. Cupellation. The process is as follows. The cupels, which should have been made some time before and stored in a dry place, are first cleaned by gentle rubbing with the finger and blowing off the loose dust, and then placed in a hot muffle and heated to redness for from 5 to 10 minutes before the alloy to be cupelled is placed on them. The reasons for this are sufficiently obvious. The sudden evolution of much steam will blow a cupel to pieces, and if the whole of the water has not been removed before the cupel is filled with molten lead, the escaping steam will bubble through and scatter about particles of the metal. If some particles of unburnt carbon remain in the bone ash, a similar result will be produced by the escape of bubbles of carbonic acid as soon as the fused litharge comes in contact with them. The cupels having been prepared are arranged in a definite order in the muffle, and the assay buttons are arranged in a corresponding order on some suitable tray, the heat of the muffle being at bright redness. Then, with the help of the tongs, the assay buttons should be placed each in its proper cupel, a note having been previously made of the position it is to occupy, and the door of the muffle closed. This part of the work should be done promptly so as not to unduly cool the muffle. The start requires a fairly high temperature and is a critical part of the process. A black crust forms at once on the surface of the lead, but this ought soon to fuse and flow in greasy drops from off the face of the metal, so as to leave the latter fluid with a well-defined outline, and much brighter than the cupel. If this clearing does not take place, the buttons are said to be frozen, in which case the temperature must be raised, some pieces of charcoal put in the muffle, and the door closed. If they still do not clear, the heat must have been much too low, and it is best to reject them and repeat the assays. When the buttons have cleared, it is well to check the draught of the furnace and to partly open the door of the muffle, so as to work at as low a temperature as is compatible with the continuation of the process. Note, with buttons poor in silver, the lowering of the temperature at this stage is not a matter of importance. End note. Too low a temperature is indicated by the freezing of the buttons and the consequent spoiling of the assays. Experience soon enables one to judge when the heat is getting too low. A commoner error is to have the heat too high. It should be remembered that that which was high enough to clear the buttons at starting is more than sufficient to keep the process going. At the finish a higher temperature is again required, therefore the door of the muffle should be closed and the furnace urged. The finish is easily recognised. The drops of litharge which in the earlier stages flow steadily from the surface of the alloy thin off later to a luminous film. At the end this film appears in commotion, then presents a brilliant play of colours, and with a sudden extinction the operation is finished. The metal again glows for an instant whilst becoming solid. If the button is a small one, the cupel is withdrawn at once and placed on that square of the cupel tray which corresponds to the position it occupied in the muffle. If, however, it is fairly large, precautions must be taken to prevent spurting. Molten silver dissolves oxygen from the air and gives it off on solidifying. The escape of the gas on sudden cooling is violent, and by throwing off particles of the metal may cause loss. This is called vegetation or spurting. The silver is apparently solid when spurting takes place. The crust breaks suddenly, and some of the metal is forced out. The evil is best guarded against by slow cooling and avoiding draughts. With large buttons of silver, precautions should never be omitted. One plan is to allow the cupels to cool in the muffle itself, the mouth being closed with hot charcoal. Another is to cover the cupel with another cupel previously heated to redness. In this case, the silver cools between two hot cupels and, of course, cools slowly. A third plan is to withdraw the cupel to the door of the muffle, holding it until it begins to get solid, and then immediately to put it back into the hotter part of the muffle. Silver remains after cupellation in flattened elliptical buttons, adhering but only slightly to the cupel. Its upper surface should show faint markings as if it were crystalline. The presence of platinum renders it still more crystalline, but removes the characteristic luster and renders the metal dull and grey. Copper, if not completely removed, has a very marked effect on the appearance of the button. The metal is spread out, damping, as it were, and firmly adhering to the cupel, which latter in the neighbourhood of the metal is almost black with oxide of copper. Sometimes a silver button is globular, or even more sharply rounded on its under than on its upper surface. It is said that this is due to the presence of lead. Gold may be present even to the extent of 50% without showing any yellow colour. The appearance of the cupel affords some useful information. The presence of cracks, evidently due to shrinkage, indicates a badly made cupel. If, however, they are accompanied by a peculiar unfolding of the cupel, the margin losing its distinctness, it is because of the presence of antimony. When lead is the only easily oxidizable metal present, the stained portion of cupel is yellow when cold. A greenish tint may be due to small quantities of copper or perhaps nickel, cobalt or platinum. Larger quantities of copper give a greenish-grey or almost black colour. A dark green and corroded cupel may be due to iron. Rings of pale coloured scoria may be due to tin, zinc, antimony or arsenic. When the cupels show signs of the presence of these metals in objectionable quantity, it is well to repeat the assay and scorify so as to remove them before cupellation. The button should be detached from the cold cupel by seizing with a pair of pliers. The undersurface should be distorted by squeezing or hammering the button so as to loosen the adhering bone ash. The cleaning is easily completed by rubbing with a clean hard brush. After cleaning, the buttons are best put on a tray of marked watch glasses and then taken to the balance and weighed. The weight of silver got needs a small correction, one by deducting for the amount of silver introduced by the lead or oxide of lead used in the assay. Note 100 grams of the lead or of its oxide will contain from 1.5 to 2.5 milligrams. End note. And 2 by adding for the cupellation loss. Loss in cupellation. During the whole process of cupelling a silver-lead alloy, a more or less abundant fume may be observed rising from the cupel. This furnishes an evident loss of lead and a possible loss of silver, for although silver at the temperature of cupellation gives off no appreciable vapour, it is known that such fume formed on a large scale contains silver. It is, however, difficult to believe that the small amount of lead vaporized carries with it a weighable amount of silver. That it does not do so in the ordinary way of working is shown by the fact that a button of silver equal in weight to the silver lost in cupelling may be got by smelting the cupel and cupelling the resulting button of lead. The loss of silver by volatilization is altogether inconsiderable, unless the temperature at which the operation is performed is much too high. Another possible source of loss is the infiltration of small particles of alloy into the cupel. The cupel is necessarily porous, and particles of metal may perhaps drain into it, more especially if the bone ash is not in fine powder. But if this is the main source of loss, it is hard to see why, in cupelling equal weights of silver and gold, the loss is not equal in each case. It is not easy to believe that the mere filtration of the fused alloy will effect such a change in the proportion of the metals as that which actually occurs. For example, a cupel on which an alloy consisting of 0.80 of a gram of silver, 0.47 of a gram of gold, and 25 grams of lead had been cupelled, was found to contain 7.5 milligrams of silver and rather less than half a milligram of gold. Assuming, for the sake of argument, that the gold present had filtered into the cupel in the form of small drops of alloy, it would have been accompanied by less than a milligram of silver, and the presence of the extra 6 or 7 milligrams of silver must have been due to a different cause. There can thus be little doubt that the cause of the greater part of the cupellation loss is a chemical one, and cannot be counteracted by a mechanical contrivance. Note: still, the precautions of having cupels well made from bone ash in fine powder, and of working the cupellation at as low a temperature as possible, are very proper ones, provided they are not carried to an absurd excess. End note. In cupellation, then, there is a loss, apart from imperfect working, inherent in the process itself, and as the amount of this loss varies under different conditions, it is necessary to study it somewhat in detail. The following experiments are taken without selection from the work of one student. 3 experiments were made for each determination, and the mean result is given. By range is meant the difference between the highest and lowest result, and the percentage loss is calculated on the silver present. The silver added in the lead used has been deducted. Effect of varying lead. In each experiment, 0.4 of a gram of silver was taken and cupelled with the lead. The silver loss and range are expressed in milligrams. Lead used, 10 grams, 20, 40, and 60. Silver lost, 6.5 grams, 7.0, 12.0, and 12.7. Range, 1.0, 1.0, 1.5, 0.5. Percentage loss, 1.62, 1.75, 3.00, 3.17. The loss increases with the lead used. Effect of varying temperature. 0.4 of a gram of silver was cupelled with 20 grams of lead. Temperature, bright red, silver lost 7.0, range 1.0, percentage loss 1.75. Temperature, clear yellow, silver lost 17.3, range 1.7, percentage loss 4.32. The difference in temperature in these experiments was much greater than would occur even with careless work. Effect of varying silver. 20 grams of lead were used in each cupellation. Reader's note: the contents of the table are summarised. Silver taken ranging from 12.5 milligrams to 800.0 milligrams. Silver lost ranges from 0.7 up to 9.7. Range varied from 0.2 and 0.1, corresponding to 12.5 and 25 milligrams of silver, up to 1.0, corresponding to 400 and 800 milligrams of silver. Percentage loss ranged from 5.6 for 12.5 and 25.0 milligrams of silver, down to 1.7 and 1.2, corresponding to 400 and 800 milligrams of silver. End reader's note. It will be seen that although the quantity of silver lost increases with the silver present, the percentage loss is greater on the smaller buttons. The following results are often quoted. Cupelling 1 grain of silver with 10 grains of lead, the loss was 1.22%. 10 grains of silver with 100 grains of lead, loss 1.13%. 25 grains of silver cupelled with 250 grains of lead, lost 1.07%. The proportion of silver to lead was the same in the 3 experiments, and the largest button gave the best results. Evidently, if the quantities of lead had been the same in the 3 experiments, say 250 grains in each case, the loss on the smaller quantities of silver would appear worse in the comparison.
In judging these results, it must be borne in mind that it is difficult to regulate the temperature, etc., in consecutive experiments so as to get exactly similar results, so that the range in consecutive cupellations is greater than that in a batch cupelled side by side. Effect of copper and antimony. 0.1 gram of silver was cupelled with 20 grams of lead, and to one batch 0.5 gram of antimony, and to another 0.5 gram of copper was added. Without addition, silver lost 2.9, range 0.3, loss in percentage 2.9. With antimony, silver lost 3.2, range 0.2, loss in percentage 3.2. With copper, silver lost 4.9, range 1.7, loss in percentage 4.9. Perhaps the antimony has so small an effect because it is eliminated in the earlier part of the process while the silver is still alloyed with and protected by a large proportion of lead, whilst the copper, on the other hand, makes its fiercest attack towards the close, when the silver is least capable of resisting it. The ill effects of copper are most strongly felt when the quantity of lead present is not sufficient to remove it. The coppery button of silver got under these conditions is very considerably less than the weight of silver originally taken. Although the above is a fair statement of the loss attending average work, it will not do in very important and exact work to place too much reliance on the figures given, or indeed on any other set of figures, with the object of correcting the result of an assay. Each man must rely on his own work. It is easy to determine what allowance must be made for the loss in cupellation by cupelling side by side with the assay piece an alloy of similar and known composition. For if the two pieces are very nearly alike, we may justly conclude that the loss on each will be the same, and if, further, we take the average of 3 or 4 such determinations, we shall get results accurate within 0.1%. The method of getting such results may be best explained by 1 or 2 illustrations. This method of working is termed assaying by checks. Suppose we have an alloy of silver and lead in unknown proportions, and that by cupelling 2 lots of 10 grams each, there is got from one 0.1226 gram of silver, and from 2 0.1229 gram. We should know from general experience that the actual quantity of silver present was from 2 to 4 milligrams more than this. To determine more exactly what the loss is, the following plan is recommended. The 2 silver buttons are wrapped up each in 10 grams of lead, and cupelled side by side with 2 other lots of 10 grams of the original alloy. If now the 2 buttons 1 and 2 weigh 0.1202 and 0.1203, they will have suffered in this second cupellation an average loss of 2.5 milligrams. Suppose the 2 fresh lots of alloy gave 0.1233 and 0.1235 of silver. The average loss on these would also be 2.5 milligrams. Add this loss to each result and take the mean, which is in this case 0.1259. If copper is present in the alloy as well as silver, it is necessary to add about the same quantity of copper to the checks as is supposed or known to be present in the assays. If the substance to be assayed is an alloy of silver and copper, first cupel 0.5 gram of it with, say, 10 grams of lead, and weigh the resulting button of silver, in order to get an approximate knowledge of its composition. Suppose the button weighs 0.3935 gram. We know that this is below the truth. For the sake of round numbers, take it as 0.4, and assume that the rest of the alloy, 0.1 gram, was copper. 2 check pieces are then weighed out, each containing 0.4 gram of silver and 0.1 gram of copper, wrapped in 5 grams of lead. Of course, the silver must be pure. And there is also weighed out 2, or better, 4, assay pieces, each containing 0.5 gram of the alloy wrapped in 5 grams of lead. The whole lot are then cupelled as nearly as possible under the same conditions. With 4 assay pieces, the cupels should be placed close together in 2 rows of 3 across the muffle.
the two check pieces are put in the middle cupels. Suppose the buttons of silver got weighed as follows: check pieces 1, 0.3940, 2, 0.3945, assay pieces 1, 0.3905, 2, 0.3912, 3, 0.3910, and 4, 0.3909. The average loss on the two check pieces is 5.7 milligrams, and the average result of the 4 assay pieces is 0.3909. Add the average loss to the average result, and there is got the corrected result, 0.3966. And if 0.5 of a gram of alloy contains 0.3966 of silver, 1000 will contain 793.2 of silver, and this is the degree of fineness. A correction for the loss in cupellation is always made in this way when rich alloys are being assayed, and in the case of rich ores it may be done after the manner of the first of the above illustrations. There is another method of working which relies more on experiment. This is to smelt the cupel as described further on, and to again cupel the resulting button of lead. The button of silver got in this second cupellation is added to that first obtained. It will sometimes, but not often, happen that the two buttons together will slightly exceed in weight the silver which was actually present. This is because of the retention in the buttons of a small quantity of lead. It has been stated that the proportion of lead thus retained may be as much as 1% of the silver present. This, however, can only be under exceptional conditions. A determination of the actual silver in the buttons got in the series of cupellations quoted on pages 102 and 103, reader's note, in the sections headed Effect of varying lead, temperature, silver, and the effect of copper and antimony, end reader's note, gave an average percentage of 99.85, so that even with the larger buttons the effect of the retained lead would be only to increase the weight by about 1 milligram. In the method of working with checks, the retained lead has no disturbing influence. The proportion of lead required for the cupellation of any particular alloy requires consideration. With too much lead, the time occupied in the process is increased, and so is the loss of silver. On the other hand, too little lead is of greater disadvantage than too much. From 8 to 16 parts of lead are required for each part of silver alloy, or if gold is present, about twice as much as this must be used. For the cupellation of 1 gram of a silver-copper alloy containing different percentages of copper, the following quantities of lead should be used. Reader's note: the first figure refers to the percentage of copper in 1 gram of the alloy, the second the lead required. End reader's note. 5% copper, 6 grams of lead. 10% copper, 8 grams of lead. 20% copper, 10 grams of lead. 30% copper, 12 grams of lead. 40% copper, 14 grams of lead. 50 to 100% copper, 16 to 18 grams of lead. The alloy, in not too large pieces, is wrapped in the required weight of lead foil and charged into the cupel at once. Or the lead may be put in first, and when the cupellation has fairly started, the alloy may be added wrapped in tissue paper. Or a portion of the lead may be first started, and the alloy wrapped in the remaining lead, and subsequently added. The cupellation of large quantities of alloy, or of alloys which contain tin, antimony, iron, or any substance which produces a scoria or corrodes the cupel, must be preceded by a scorification. The advantages of this are that the slag is poorer in precious metal than that found on a cupel, and is more easily collected and cleaned, that larger quantities of metal can be treated, and that even if the substance is in part infusible, or produces at the start a clinkery mass or scoria, the oxide of lead gradually accumulates, fluxes the solid matters, and produces a good final result. But if the oxide of lead by itself is not sufficient for the purpose, borax or some other flux can be easily added. If the button of silver got is very small, its weight may be estimated from its size.
but it must be remembered that the weight varies as the cube of the diameter. If one button has twice the diameter of another, it is 8 times as heavy, and so on. Scales specially constructed for measuring silver and gold buttons may be purchased, but it is much better to make the measurement with the help of a microscope provided with an eyepiece micrometer. If the length of the long diameter of a silver button be taken, the following table will give the corresponding weight in milligrams. Reader's note: this table is summarized. Diameter 0.04 of an inch, weight 3.6. Through 0.010 of an inch with a weight of 0.056. Down to diameter 0.004 of an inch with a weight of 0.004. End reader's note. The weight of a corresponding button of gold is got by multiplying by 2.25. These figures are based on those given by Plattner, and apply only to buttons of such shape as those left after cupellation. A sphere of silver 0.01 of an inch in diameter would weigh 0.09 of a milligram, and a similar sphere of gold weighs 0.167 of a milligram. It is safer, however, to compare with a micrometer the diameter of the button whose weight has to be determined with that of a standard button of nearly equal size, whose weight is known. The weights of the two buttons are proportional to the cubes of their diameters. This plan of working is described more fully in Appendix B. Calculation of the results. After deducting for the silver added and correcting for the cupellation loss, the calculation is made in the usual way, reporting as so many parts per thousand in the case of rich alloys, and as so many ounces and pennyweights, or better as ounces and decimals of an ounce, in the case of poor alloys and ores. In this last case, however, it is less fatiguing to refer to a set of tables, which give either directly or by means of simple addition the produce corresponding to any weight obtained from certain given weights of the substance. The following table gives the produce in ounces and decimals of an ounce per ton of 2,240 pounds. Reader's note: this table has been omitted. In outline, the first column of the table defines a number of rows corresponding to the weight of metal got from a sample of ore, ranging from 0.0001 of a gram to 1.0 gram. There are then 5 columns corresponding to ore sample sizes of 3, 5, 20, 50 and 100 grams. So for each value of metal got there are 5 columns giving the size of sample from which the metal was extracted, with figures in the body of the table showing the corresponding amount of metal to be got in ounces per ton. End reader's note. When, as in this table, the fraction of an ounce is expressed by 2 places of decimals, it may be reduced to pennyweights, note DWTS, end note, by dividing by 5. For example, 0.40 of an ounce is 8 pennyweights. The fraction of a pennyweight, similarly expressed, may be converted into grains with sufficient exactness by dividing by 4. Thus 1.63 ounces equal 1 ounce 12.60 pennyweights, or 1 ounce 12 pennyweights 15 grains. In England it is usual to report in ounces and decimals of an ounce. The way to use the table is best shown by an example. Suppose a button of silver weighing 0.0435 of a gram was obtained from 20 grams of ore. Look down the 20 gram column of the table and select the values corresponding to each figure of the weight. Thus 0.04 corresponds to 65.33 ounces to the ton, 0.003 to 4.90 ounces to the ton, and 0.0005 to 0.82 ounces to the ton. Add these together, the produce is 71.05 ounces, or 71 ounces, 1 pennyweight, to the ton. Or suppose an ore is known to contain 1.24% of silver. Look down the 100 gram column, select the values and add them together as before. 1.0 corresponds to 326.67 ounces per ton, 0.2 to 65.33 ounces per ton, 0.04 to 13.07 ounces per ton. Adding corresponds to 405.07 ounces per ton. This gives 405 ounces 1 pennyweight, 10 grains to the ton. The calculation becomes more complicated when, as is frequently the case, the ore contains metallic particles. These show themselves by refusing to pass through the sieve when the ore is powdered. When they are present, a large portion, or if feasible, the whole of the sample is powdered and sifted. The weights of the sifted portion and of the metallics, or prills, are taken. The sum of these weights gives that of the whole of the sample taken. It is very important that nothing be lost during the operation of powdering. Each portion has to be assayed separately. It is usual to assay a portion of the sifted sample, say 20 or 50 grams, and to add to the produce of this its share of the metallics. This way of calculating, which is more convenient than correct, is illustrated by the following example. Weight of whole sample, 400 grams, made up of sifted portions, 399 grams, and metallics, 1 gram, total 400 grams. 20 grams of the sifted portion, when assayed, gave 0.1050 of a gram of silver. The whole of the metallics, scorified and cupelled, gave 0.842 of a gram of silver. Since the 20 grams assayed was 1/20th of the whole, 1/20th part of the 0.842 of a gram of silver from the metallics must be added to its produce. We thus get 0.1471 of a gram. Note 0.1050 plus 0.0421. End note. Referring to the 20 gram column, we get 0.1 corresponds to 163.33, 0.04 to 65.33, 0.007 to 11.43, and 0.0001 to 0.16. Adding 0.147 corresponds to 240.25 ounces per ton. A more legitimate method of calculation is as follows. Calculate separately the produce of each fraction as if they were from different ores. Multiply each produce, best stated in percents, by the weight of the corresponding fraction. Add together the products and divide by the weight of the whole sample. Taking the same sample for illustration, we have metallics, weight 1 gram. 1 gram of it yielded 0.842 grams of silver. Therefore, produce equals 84.2%. Produce multiplied by the weight is still 84.2. Sifted portion, weight 399 grams. 20 grams of it yielded 0.105 of a gram of silver. Therefore, produce equals 0.525%, and produce multiplied by weight, 0.525 times 399, is 209.475. Add together and divide by 400 the weight of the whole sample. 84.2 plus 209.475 equals 293.675 divided by 400, 0.7342. 0.7342 is the total produce of the ore in percent. Referring to the 100 gram column in the table, we find 239.84 ounces to the ton as the produce. 0.7 corresponds to 228.67, 0.03 to 9.80, 0.004 to 1.31, and 0.0002 to 0.06. Total 239.84. Comparing this with the result calculated by the first method, that is 240.26, we see that was 0.38 of an ounce, or between 7 and 8 pennyweights too high. With ores containing metallics, it is of great importance to powder the whole of the selected sample without loss during the process, and of even greater importance to well mix the sifted portion, of which the last portions to come through the sieve are apt to be more than ordinarily rich through the grinding down of some portions of the metallic prills. End of section 10. Section 11 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley.
Chapter 9. Silver, Gold, Cyanides, Platinum, Mercury. Part 3. Remarks on cupellation. Cupellation is at once the neatest and the most important of the dry methods of assaying. Its purpose is to remove easily oxidizable metals, such as lead and copper, from silver and gold, which are oxidizable with difficulty. Metals of the first class are often spoken of as base, and gold and silver as noble metals. When lead is exposed to the action of air at a temperature a little above redness, it combines with the oxygen of the air to form litharge, an oxide of lead, which, at the temperature of its formation, is a liquid. Consequently, if the lead rests on a porous support, which allows the fused litharge to drain away as fast as it is formed, a fresh surface of the lead will be continually exposed to the action of the air, and the operation goes on until the whole of the lead has been removed. Silver or gold exposed to similar treatment does not oxidize, but retains its metallic condition, so that an alloy of lead and silver similarly treated would yield its lead as oxide, which would sink into the support, while the silver would remain as a button of metal. The porous support, which is called a cupel, should absorb the slag, oxide of lead, etc., just as a sponge absorbs water, but must be sufficiently fine-grained to be impervious to the molten metal. At first sight, it appears difficult to filter, as it were, a fluid slag from a fluid metal, but an ordinary filter paper damped with oil will allow oils to run through and yet retain the water, but damped with water it will allow water to run through and retain oils. Similarly, fused slags damp and filter through a cupel, but the molten metal, not damping it, withdraws itself into a button, which is retained, although of course if the cupel is very coarse-grained, the metal may sink into the hollows. Copper, antimony, tin, and most other metals form powdery oxides which are not of themselves easily fusible, and it is necessary when these are present to add some solvent or flux to render the oxide sufficiently fluid. Fortunately, oxide of lead is sufficient for the purpose. Hence, mixed oxides of copper and lead, provided the lead is present in proper proportion, form a fluid slag. In separating copper from silver or gold, advantage is taken of this fact, for although we cannot cupel an alloy of copper and silver, it is easy to cupel an alloy of copper, silver, and lead. If, however, the lead is not present in sufficient quantity, the whole of the copper will not be removed, and the button of silver, still retaining copper, will be found embedded in a coating of black oxide of copper. Copper oxidizes less easily than lead does, and consequently the alloy which is being cupelled becomes relatively richer in copper as the operation proceeds. It is on this account that the ill effects of the copper make themselves felt at the close of the operation, and that the oxide of copper is found accumulated around the button of silver. Tin and antimony, on the other hand, are more easily oxidized, and the tendency of their oxides to thicken the slag makes itself felt at the commencement. If the button of alloy once frees itself from the ring or crust of unfused oxide first formed, the cupellation proceeds quietly, and leaves a clean button of silver in the centre. But in either case the cupellation is imperfect, and should be repeated with a larger proportion of lead. An unfused and consequently unabsorbed slag tends to retain small buttons of alloy or metal, and thus cause serious loss. There is a principle underlying many of the phenomena of dry silver assaying which the students should endeavour to understand, and which serves to emphasize and explain some facts which, without an explanation, may present difficulties. If a button of melted lead be covered with a layer of slag rich in oxide of lead, and a second metal be added, this other metal distributes itself between the metal and slag in proportions which depend mainly upon the ease with which it is oxidized, and to a large extent upon the relative quantities of material present. Easily oxidizable metals such as zinc, iron, antimony, and tin will go mainly into the slag, and if the proportion of the slag is large, very little will go into the metal. On the other hand, with metals oxidizable with difficulty, such as silver, gold, and platinum, the reverse holds true. Nearly the whole of the metals will go into the lead, and very little into the slag. If, however, the slag be very rich, say in antimony, the lead will contain antimony, and on the other hand, if the lead be very rich in silver, the slag will contain silver in appreciable quantity. Copper, which is near lead in the facility with which it is oxidized, will serve for the purpose of a detailed example. The results of actual analyses of metal and slag formed in contact with each other are shown in the following table.
Reader's note. The table is presented in two columns, percentage composition of the metal and percentage composition of the slag, with percents for lead and copper given under each heading. End reader's note. Sample 1. 6.8% lead and 93.2% copper in the metal, 71.4% lead and 21.4% copper in the slag. Sample 2. 20.0% lead and 80.0% copper in the metal, 78.0% lead and 17.0% copper in the slag. Sample 3. 28.0% lead and 72.0% copper in the metal, 80.0% lead and 12.5% copper in the slag. Sample 4. 32.0% lead and 68.0% copper in the metal, 86.0% lead and 6.7% copper in the slag. Sample 5. 85.0% lead and 15.0% copper in the metal, 90.0% lead and 3.6% copper in the slag.
It will be seen from this table that the slag is always much richer in lead and poorer in copper than the metal with which it is in contact. The ratio of lead to copper in these 5 samples is: sample 1, in the metal 1 to 14, in the slag 1 to 0.3, sample 2, in the metal 1 to 4, in the slag 1 to 0.2, sample 3, in the metal 1 to 2.5, in the slag 1 to 0.16, sample 4, in the metal 1 to 2, in the slag 1 to 0.08, sample 5, in the metal 1 to 0.16, in the slag 1 to 0.04. Assuming these figures to be correct, the following statement is approximately true. On oxidizing an alloy of 10 grams of copper and 10 grams of lead, and pouring off the slag when 3 grams of lead have gone into it, there will be a loss of, owing to the slag carrying it off, about 0.2 of a gram of copper. On repeating the operation, the next 3 grams of lead will carry with them about 0.5 of a gram of copper, and on again repeating, 3 grams of lead will remove 0.8 of a gram of copper. Finally, the last gram of lead will carry with it 0.3 of a gram of copper, and there will be left a button of copper weighing 8.3 grams. The slag will have carried off altogether 1.7 gram of copper, which is 17% of the metal originally present. With the more perfect exposure to the air and quicker removal of the slag which results from heating on a cupel, the loss would be heavier. Carsten got by actual experiment on cupelling copper and lead in equal proportions a loss of 21.25%. Going back to the example, if the slag were collected and fused with a suitable reducing agent so as to convert, say, half of it into metal, that half would contain nearly the whole of the copper. Such a reduction is called cleaning the slag. On reoxidizing this metal, another button of copper is formed which, added to the first, would reduce the loss from 17% to, say, 7 or 8%. And it is conceivable that by a series of similar operations, almost the whole of the 10 grams of copper originally taken might be recovered. In practice, the problem is, as far as the copper is concerned, not how to save, but how most easily to remove it. And since the removal of this metal is quicker from an alloy containing not too much lead, it is evident that 2 or 3 operations with small quantities of lead will be more effectual than a single treatment with a larger quantity. With those metals, tin, antimony, etc., which pass quickly into the slag, the contrary is true. Hence, with these, it is necessary to have enough lead present so that the slag formed at the outset shall contain enough oxide of lead to make it fluid. As silver is so much less easily oxidized than copper, we should reasonably expect that the proportion of silver carried off in the oxide of lead would be considerably less than that of the copper indicated in the above example. Indeed, there are 1 or 2 facts which tend to encourage the hope that the operation may be conducted without any loss. If a piece of pure silver foil is exposed on a cupel to air at the usual temperature of cupellation, it undergoes very little change. It does not even fuse. It loses nothing in weight and does not oxidize. In fact, even if oxide of silver were formed under these conditions, it could not continue to exist, for it is decomposed into silver and oxygen at a temperature considerably below redness. On the other hand, oxide of silver is not reduced to metal by heat alone when mixed with an excess of oxide of lead, while metallic silver is converted into oxide when heated with the higher oxides of lead, copper, and some other metals. That silver and even gold, which is more difficult to oxidize than silver, may be carried off in the slag in this way is in agreement with general experience. If 10 grams of silver are cupelled with 10 grams of lead, there will be a loss of about 50 milligrams of silver, which is in round numbers 1/30th of the corresponding copper loss. With 10 grams of gold and 10 grams of lead, the loss will be 4 or 5 milligrams, which is about 1/12th of the corresponding silver loss. Determination of silver in assay lead. Scorify 50 grams of the lead with 0.5 of a gram of powdered quartz or glass at not too high a temperature. When the eye has closed in, pour. Reject the slag and cupel the button of lead. Remove the cupel from the muffle immediately the operation is finished. Weigh and make a prominent note of the result in the assay book, as so many milligrams of silver contained in 100 grams of lead. Determination of silver in red lead or litharge. Fuse 100 grams of the oxide with from 10 to 20 grams of borax, and in the case of litharge with 2 grams, or with red lead 4 grams, of flour. Cupel the lead and weigh the button of silver. Note the results as in the last case. Determination of silver in argentiferous lead. Be careful in taking the sample, since with rich silver-lead alloys the error from bad sampling may amount to several parts per cent. Cupel 2 lots of 20 grams each and weigh the buttons of silver. Add to these the estimated cupel loss and calculate the result. Or wrap each button of silver in 20 grams of assay lead and recupel side by side with 2 fresh lots of 20 grams each of the alloy. Calculate the loss incurred and add on to the weight of the 2 fresh buttons got. Determination of silver in bullion. The remarks made under the last heading as to the importance of correct sampling apply with equal force here. Make a preliminary assay by cupelling 0.1 of a gram of the alloy with 1 gram of assay lead. Calculate the percentage composition. Refer to the table on page 105 to find what weight of lead is required for cupelling 1 gram of alloy. Reader's note: the table on page 105 is given in section 10 of this recording, dealing with cupellation. End reader's note. Weigh out 4 lots of 1 gram each and wrap them in the required quantity of lead. Make 2 check pieces by weighing up 2 lots of fine silver equal to that which you believe to be present in the assay pieces. Add copper to make up the weight to 1 gram and wrap in the same quantity of lead as was used for the assays. Prepare 6 cupels and charge them in the annexed order and cupel. Reader's note: Figure 43 consists of 2 rows of 3 samples, each row assay, check, assay. End reader's note. Guard against spurting. Clean and weigh the buttons of silver.
Add the mean loss on the 2 check pieces to the mean weight of the 4 assay pieces. This, multiplied by 1000, will give the degree of fineness. Determination of silver in copper. The silver is best separated in the wet way before cupelling, but if the proportion is not too small, it can be found by cupellation. Weigh up 3 grams of the metal, wrap in 30 grams of sheet lead, and cupel. When the cupellation has proceeded for 15 minutes, add 20 grams more lead, and continue till finished. Weigh the button of silver. The cupellation loss will be 5 or 6% of the silver present. Determine it by powdering the saturated portion of the cupel and fusing in a large Cornish crucible with 30 grams each of soda and borax, 10 grams of fluorspar, and 1½ grams of charcoal. Cupel the resulting button of lead and add 10 grams more of lead towards the close of the operation. Deduct the weight of silver contained in the lead used from the weight of the 2 buttons and calculate to ounces to the ton. In an experiment in which 0.1975 of a gram of silver was present, the weight of the button from the first cupellation was 0.1867, and that of the button from the second, after correcting for the lead added, was 0.0110 of a gram. Determination of silver in galena. By pot assay. Mix 20 grams of the powdered ore with 30 grams of red lead, 20 grams of soda, and 5 grams of borax, as also with from 7 to 10 grams of nitre. Fuse and pour. Clean the slag if the ore is rich. Cupel the buttons of lead. Make the usual corrections and calculate in ounces to the ton. By scorification. Take 10 grams of the ore, 30 grams of lead, and 0.5 of a gram of borax. Scorify. Clean the slag by adding anthracite after the eye has closed in. Cupel the button of lead. Weigh the button of silver, make the necessary corrections, and calculate to ounces to the ton. The determination may also be made by cupelling the button of lead got in the dry lead assay. A sample of galena determined by the 3 methods gave the following results. By pot assay, 7.18 ounces per ton. By scorification, 7.02 ounces per ton. By lead assay, 6.72 ounces per ton. Determination of silver in an ore. By pot assay, take 20 grams of the powdered ore and mix with 30 grams of soda, 40 grams of red lead, and 5 grams of borax, as also with from 2 to 3 grams of flour. Fuse, pour. Clean the slag by fusing with 20 grams of red lead and 2 grams of flour. Cupel the buttons of lead, weigh, make the necessary corrections, and calculate to ounces to the ton. By scorification. Take 5 grams of the powdered ore, 50 grams of lead, and 0.5 of a gram of soda or borax. Scorify. Clean the slag by fusing in a crucible, as in the pot assay. Cupel, etc. Example. By pot assay, ore taken 20 grams, silver got 0.2893 of a gram, silver from slag 0.0060 of a gram, silver lost in cupellation 0.0100 of a gram, total 0.3053 of a gram. Deduct silver in red lead 0.0017 of a gram. Therefore, silver in ore 0.3036 of a gram, which corresponds to 495.9 ounces per ton. By scorification, ore taken 3 grams, silver got 0.0425 of a gram, silver from slag 0.0022 of a gram, silver lost in cupellation 0.0020 of a gram, total 0.0467 of a gram. Deduct silver in lead 0.0015 of a gram, therefore silver in ore 0.0452 of a gram, which corresponds to 492.2 ounces per ton. Determination of silver in silver precipitate. This substance contains, in addition to metallic silver and gold, sulfates of lead and lime, oxides of zinc, copper, and iron, and more or less organic matter.
The sample as received is generally free from water at 100 degrees centigrade, and since it rapidly absorbs water, care should be taken in weighing it. Since it contains combined water, it is not suited for scorifying. Therefore, the determination of silver and gold, fine metal, is made by pot assay. Weigh up 5 grams of the precipitate, mix with 100 grams of litharge and 1 gram of charcoal. Melt in a crucible at a moderate heat and pour. Detach the slag, replace in the crucible, and when fused, add a mixture of 20 grams of litharge and 1 gram of charcoal. When the fusion is again tranquil, pour and cupel the 2 buttons of lead. In a sample worked in this manner, the mean of 4 determinations gave 0.6819 of a gram of fine metal. Deducting 1 milligram for the silver contained in the oxide of lead and adding 8 milligrams for the cupellation loss, there is got 0.6889 of a gram, or 13.778% of silver and gold in the sample. Determination of silver in burnt ores. By pot assay, roasted cupriferous pyrites containing small quantities of gold and silver comes under this heading. The following mixture will give a fluid slag which is heavy and tough when cold. Ore 100, borax 50, sand 50, litharge 100, charcoal 7. Mix. Place in a large crucible, cover with salt, and melt down under cover. When fused, drop in an iron rod for a few minutes, and about a couple of minutes after its withdrawal, pour the charge quickly into a large conical mould. The button of lead should weigh about 50 grams. Cupel and weigh the silver. The litharge may be replaced by red lead, in which case another gram of charcoal powder must be added. In our experience, the results obtained by this method are about 20% less than the actual content of the ore. The results of 2 assays after deducting for the silver in the litharge used were 3.9 and 4.1 milligrams, and a third assay in which 5.4 milligrams of silver had been added gave 9.2, which after deducting the added silver leaves 3.8 milligrams. The average of the 3 results is 3.9 milligrams from the 100 grams of ore. 2 lots of 100 grams of the same ore treated in the wet way gave 5.2 and 5.0 milligrams of silver. Burnt ores from Spanish pyrites carry about 0.005% of silver. End of section 11. Chapter 9, Part 3. Section 12 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 9. Silver, Gold, Cyanides, Platinum, Mercury. Part 4. Wet Methods. Silver is got into solution from its ores by attacking with nitric acid, but it is best, after dissolving, to cautiously add dilute hydrochloric acid, and to carefully avoid excess. If the quantity of silver is very small, the solution is allowed to stand 24 hours, but otherwise it is warmed and filtered as soon as it clears. Dry the residue and concentrate the silver in a button of lead by pot method or scorification, according to the amount of stony matter present. Cupel the lead, and the resulting button will be free from all metals except perhaps gold. It may be weighed, or dissolved in nitric acid, and the silver determined gravimetrically in the diluted and filtered solution. It is better to weigh the metal and afterwards to determine the gold in it, estimating the silver by difference. Silver alloys are dissolved in dilute nitric acid, free from chlorides, diluted and filtered. The solution is then ready for gravimetric determination. Sulphuretted hydrogen precipitates silver, like copper, completely, even from fairly acid solutions. Gravimetric determination. Add dilute hydrochloric acid in small excess to the hot dilute solution, which must contain free nitric acid. Heat and stir until the solution clears. Decant through a small filter and wash with hot water. Acidulated at first with a little nitric acid if bismuth is suspected to be present. Dry quickly, transfer as much as possible of the precipitate to a watch glass, burn and ignite the filter paper, treating the ash first with 2 drops of nitric acid and then with 1 of hydrochloric, and again dry. Add the rest of the silver chloride and heat slowly over a Bunsen burner until it begins to fuse. Cool and weigh. The precipitate is silver chloride, AgCl, and contains 75.27% of silver. The moist precipitate is heavy and curdy. It is decomposed by direct sunlight, becoming violet under its influence. When heated, it is yellowish, and since it is volatile at a high temperature, it must not, in drying, be heated above its fusing point. The fused chloride can be removed from the crucible, to which it adheres strongly, by digesting with dilute acid and zinc. For the determination of silver in nearly pure bullion, the following process is used. Weigh up 1.5054 grams of the alloy. With this amount of alloy, each 2 milligrams of silver chloride formed is equivalent to 1 degree of fineness, so that the weight of the silver chloride obtained, stated in milligrams and divided by 2, will give the degree of fineness. Transfer to a bottle, known as bottles for the Indian mint assay, and dissolve in 10 c.c. of dilute nitric acid. Then make up with water to 200 c.c. and add 3 c.c. of dilute hydrochloric acid. Allow to stand a few minutes and then shake. Fill the bottle completely with water, allow to settle, and siphon off the clear liquid. Pour on more water. Shake gently to break up the lumps, and again fill the bottle with water. Invert over the mouth of the bottle a porous Wedgwood crucible, somewhat similar to those used in gold parting. Take firm hold of the crucible and bottle and invert promptly so that the silver chloride may be collected in the crucible. Allow to stand a little while for the precipitate to settle, and then carefully remove the crucible under water. Note: be careful to remove the crucible before taking the bottle out of the basin of water. If this is not done, the chloride may be washed out of it. End note. Drain off most of the water and break up the silver chloride with the help of a well-rounded glass rod. This greatly facilitates the subsequent drying. Dry first on the water bath and then on the iron plate. Remove the dried silver chloride by inverting the crucible and weigh it. As an example, 3 determinations of silver in a coin carried out in this way gave: sample 1, 1.8500 of a gram of silver chloride, equivalent to 925.0 fineness. Sample 2, 1.8498 of a gram of silver chloride, equivalent to 924.9 fineness. Sample 3, 1.8502 of a gram of silver chloride, equivalent to 925.1 fineness. Determination of silver in burnt ores. Take 100 grams of the ore and place in a large beaker of 2.5 litres capacity, and cover with 375 c.c. of hydrochloric acid. Boil for half an hour until the oxides are dissolved and the residue looks like sand and pyrites. Then add 20 c.c. of nitric acid and boil till free from nitrous fumes. Dilute to 2 litres with water and pass a current of sulphuretted hydrogen till the iron is reduced, the copper and silver precipitated, and the liquor smells of the gas. This takes about 1 hour and a half. Filter off the precipitate, rejecting the solution, and wash with warm water. Dry and transfer to an evaporating dish, adding the ashes of the filter paper. Heat gently with a Bunsen burner until the sulphur burns, and then calcine until no more sulphurous oxide comes off. When cold, add 30 c.c. of nitric acid, boil, and dilute to 100 c.c. Add 1 c.c. of very dilute hydrochloric acid, 1 to 100. Note: 1 c.c. of this dilute acid will precipitate 8 or 9 milligrams of silver. End note. Stir well, and allow to stand overnight. Decant onto a Swedish filter paper, dry and calcine. Mix the ashes with 100 grams of litharge and 1 gram of charcoal and fuse in a small crucible. Detach the button of lead and cupel. Weigh and make the usual corrections. As an example, 100 grams of ore treated in this way gave 5.8 milligrams of silver. Deducting 0.8 for the silver added in the oxide of lead leaves 5 milligrams obtained from the ore. Another experiment on 100 grams of the same ore, to which 5 milligrams of silver had been added, gave 11.0 milligrams. Deduct 5.8 for the silver added. This leaves 5.2 milligrams as the silver obtained from the ore. These give as a mean result 0.0051%, or 1.66 ounce per ton. Determination of silver in commercial copper. For the method of doing this, with an example and experiment, see under the heading of Examination of Commercial Copper. Volumetric methods. There are two of these, one adapted for the determination of silver in alloys of approximately known composition, and the other of more general application. The first of these, generally known as Gay-Lussac's method, is, as regards its working, perfect in principle, but it requires a practically constant quantity of silver, that is, one which varies by a few milligrams only in each determination. It is a confirmatory method rather than a determinative one. The other is known as Volhardt's, and resembles in principle and method an ordinary volumetric process. Gay-Lussac's method is based on the precipitation of silver from a nitric acid solution by a solution of sodium chloride, the point at which the whole of the silver is precipitated being recognized by the standard solution ceasing to give a precipitate. The process depends for its success upon 1. The ease which silver chloride separates out from the solution, leaving it clear after shaking, and 2. The cloudiness produced by the reaction of very small quantities of silver nitrate and sodium chloride. In working, a quantity of the sodium chloride solution equal to 1 gram of silver is added at once to the assay, and when the solution has been rendered clear by shaking, the residual silver, which should not exceed a few milligrams, is estimated with the help of a weaker solution of sodium chloride. The success in working evidently depends upon the accuracy with which the first addition of the salt solution is made. On this account, the standard solution is run in from a special pipette capable of delivering a practically invariable volume of solution. It is not so important that this shall deliver exactly 100 cc's as that in 2 consecutive deliveries the volume shall not differ by more than 0.05 of a cc. The dilute salt solution is 1/10 of the strength of that first run in, and 1 cc of it is equivalent to 1 milligram of silver. Ordinarily it is run in 1 cc at a time, and an ordinary burette may be used for this purpose, shaking between each addition until it ceases to give a precipitate. If many such additions have to be made, the operation not only becomes tedious, but the solution also ceases to clear after shaking, so that it becomes impossible to determine the finishing point. If the assay contains less than 1 gram of silver, the first addition of the dilute salt solution of course produces no precipitate. 5 milligrams of silver in solution, 5 cc's, is then added, and the assay proceeded with in the usual way, 5 milligrams of silver being deducted from the amount found. There is required for the assay a standard solution of sodium chloride, which is prepared by dissolving 5.4162 grams of the salt, made by neutralizing carbonate of soda with hydrochloric acid, in water, and diluting to 1 litre. 100 cc's of this is equivalent to 1 gram of silver. The weaker solution of salt is made by diluting 100 cc's of the stronger one to 1 litre. 1 cc of this will equal 1 milligram of silver, or 0.1 of a cc of the stronger solution. A standard solution of silver equivalent to the dilute salt solution is made by dissolving 1 gram of fine silver in 10 cc of dilute nitric acid and diluting with water to 1 litre. The solution of salt is standardized as follows. Weigh up 1.003 of a gram of fine silver and dissolve in 25 cc of dilute nitric acid in a bottle provided with a well-fitting flat-headed stopper. Heat on the water bath to assist solution, resting the bottle in an inclined position. When dissolved, blow out the nitrous fumes with the help of a glass tube bent at right angles. Run in from a stoppered pipette 100 cc of the standard salt solution and shake vigorously until the solution clears. Reader's note: the stoppered pipette is illustrated and has a tap just above its lower nozzle. End reader's note. Fill an ordinary burette with the weaker standard salt solution and run 1 cc into the assay bottle, letting it run down the side so that it forms a layer resting on the assay solution. If any silver remains in solution, a cloudy layer will be formed at the junction where the two liquids meet. This is best observed against a black background. If a cloudiness is seen, shake to clear the liquid and run in another cc of salt, and continue this until a cloudiness is no longer visible. Deduct 1.5 cc from the amount of the weaker sodium chloride solution run in. Divide the corrected reading by 10 and add to the 100 cc. This will give the volume of strong salt solution equivalent to the silver taken. If the first addition of the weaker salt solution causes no cloudiness, add 5 cc of the silver solution from an ordinary pipette, shake, and then run in the weaker salt solution, working as before. These 5 mg of silver added must be allowed for before calculating. As an example, 1.0100 of a gram of fine silver was taken for standardizing a solution, and 4 cc of the weaker salt solution were run in. Deducting 1.5 and dividing by 10 gives 0.25 of a cc to be added to the 100 cc. 100.25 to 1.0100 is equivalent to 100 to x. Therefore x equals 1.0075, which is the standard of the salt solution. The method of working an assay may be gathered from the following example. In the determination of silver in some buttons left after cupellation, it was assumed that these would contain 99.5% of silver. For the assay, it was necessary to take a quantity that should contain a little more than 1.0075 grams of silver. Then 99.5 to 100 is equivalent to 1.0075 to x. Therefore x equals 1.0125. To ensure a slight excess, there was taken 1.0150 of a gram of the buttons, which was treated in exactly the same way as for the standardizing. The quantity of the weaker salt solution required was 7 cc. Deducting 1.5 cc and dividing by 10 gives 100.55 cc of strong salt solution, which is equivalent to 1.0130 of a gram of silver. This, being obtained from 1.015 of a gram of alloy, is equal to 99.8%, or 998.0 fine. The effect of temperature. The standardizing and the assay must be done at the same time, since a difference of 5 degrees centigrade makes a difference of 0.1 of a cc in measuring the 100 cc of strong solution of salt. It is always best to prepare a standard with each batch of assays. Sulfocyanate method. Volhard's process is based upon the precipitation of silver in nitric acid solutions with potassium sulfocyanate, the finishing point being the development of a reddish-brown colour, produced by the action of the excess of sulfocyanate upon ferric sulfate. The white sulfocyanate settles readily, leaving the liquor clear, and a persistent brown coloration in the liquid indicates the finish. The assay must be carried out in the cold, and water free from chlorides must be used. Note: chlorides interfere not merely by removing silver as insoluble silver chloride, but also by making it difficult to get a good finishing point. owing to the silver chloride removing the colour from the reddened solution. End note. The standard sulfocyanate of potassium solution is made by dissolving 4.5 or 5 grams of the salt KCyS in water and diluting to 1 litre. 100 cc's are about equivalent to 0.5 gram of silver. The standard silver nitrate solution is made by dissolving 5 grams of fine silver in 50 cc's of dilute nitric acid, boiling off nitrous fumes and diluting to 1 litre. The indicator is a saturated solution of iron alum or a solution of ferric sulfate of equivalent strength, made by titrating acid ferrous sulfate with potassium permanganate. Use 2 cc's for each assay. The sulfocyanate solution is standardized by placing 50 cc's of the silver nitrate solution in a flask with 20 cc's of dilute nitric acid, diluting to 100 cc's with water, and running in the sulfocyanate until the greater part of the silver is precipitated, then adding 2 cc's of the ferric indicator, and continuing the titration until a reddish-brown colour is developed and remains permanent after shaking continuously. The assay is similarly performed, the silver being used in the state of a nitric acid solution. The effect of variations in the conditions of the assay may be seen from the following experiments, in which 20 cc's of standard silver nitrate were used. Effect of varying temperature. Temperature 10 degrees centigrade, sulfocyanate required 19.6 cc's. Temperature 30 degrees centigrade, sulfocyanate required 19.3 cc's. Temperature 70 degrees centigrade, sulfocyanate required 19.0 cc's. Temperature 100 degrees centigrade, 18.6 cc's. Effect of varying nitric acid. Varying nitric acid has no effect, except that with a fairly acid solution the finishing point is somewhat sharper. Nitric acid added 5 cc's. Sulfocyanate required 19.6 cc's. Nitric acid 10 cc's. Sulfocyanate 19.5 cc's. Nitric acid 20 cc's. Sulfocyanate 19.6 cc's. Nitric acid 50 cc's. Sulfocyanate 19.6 cc's. Effect of varying bulk. Bulk 50 cc's. Sulfocyanate required 19.5 cc's. Bulk 100 cc's. Sulfocyanate 19.6 cc's. Bulk 200 cc's. Sulfocyanate 19.6 cc's. Bulk 300 cc's. Sulfocyanate 19.7 cc's. Effect of varying ammonic nitrate. Ammonic nitrate 0 grams. Sulfocyanate required 19.6 cc's. 1 gram sulfocyanate 19.6 cc's. 5 grams sulfocyanate 19.7 cc's. 10 grams sulfocyanate 19.9 cc's. Effect of varying silver. Silver added 1 cc. Sulfocyanate required 1 cc. Silver 10 cc's. Sulfocyanate 9.7 cc's. Silver 20 cc's. Sulfocyanate 19.6 cc's. Silver 50 cc's. Sulfocyanate 49.4 cc's. Silver 100 cc's. Sulfocyanate 99.0 cc's. This method is valuable for determining silver in salts, alloys, and solutions where no more than an ordinary degree of accuracy is demanded. It is easy and applicable under most of the usual conditions. Its greatest disadvantage is the brown coloration produced by the sulfocyanate when the assay is nearly but not quite finished, and the slowness with which this is removed on shaking up with the precipitate. This is worse with large quantities of precipitate, and if about 1 gram of silver is present, it gives an indefiniteness to the finish which lowers the precision of the process to about 1 in 500. This is useless for the assays of bullion. One writer states that this inconvenience is due to portions of liquid being entangled in the precipitate, but it appears much more likely to be due to the action of the precipitate itself. In attempting to apply the process to the assay of bullion, by working it on the principle of a Gay-Lussac assay, it was found that a very considerable excess of silver was required to complete the reaction. In these experiments, 100 cc's of sulfocyanate, very accurately measured, was run into the solution containing the weighed portion of bullion, fine silver, and after shaking the solution was filtered. In the filtrate, the remaining silver, if there should be any, was determined by the ordinary titration, but with sulfocyanate of 1/10 the strength. This final titration was quite satisfactory. The amount of silver precipitated by the first 100 cc's, however, varied with the quantity of silver present, as in the following series. Note, these results were obtained when using ammonium sulfocyanate, and cannot be explained by the presence of such impurities as chlorides, etc. End note. Silver present 1.1342 grams. Silver precipitated 1.1322 grams. Silver present 1.1375 grams. Silver precipitated 1.1335 grams. Silver present 1.1405 grams. Silver precipitated 1.1351 grams. Silver present 1.1484 grams. Silver precipitated 1.1379 grams. These, of course, preclude a method of the kind aimed at, and at the same time emphasize the importance of uniformity of work in the ordinary process. In the determination of chlorides in seawater, Dittmar used a combined method, precipitating the bulk of the silver as chloride, and after filtering, determining the small excess of silver by sulfocyanate. This modification answers admirably when applied to the assay of bullion. In the ordinary Gay-Lussac method, the precipitation of the bulk of the silver by the 100 cc's of salt solution leaves nothing to be desired, either as to ease in working or accuracy of result. The silver precipitate settles quickly, and leaves a clear liquor admirably fitted for the determination of the few milligrams of silver remaining in solution. But the method of determining this residual silver by adding successive small quantities of salt, so long as they continue to give a precipitate, is unsatisfactory, and, judged on its own merits, apart from the rest of the process, could hardly escape condemnation. It is clumsy in practice, for the continued adding of small portions of salt solution is laborious, and becomes impossible with more than a few milligrams of silver in solution. The proposed modification is simple. Having precipitated the silver with the 100 cc's of salt solution, as described under Gay-Lussac's method, shake till the liquor clears and filter into a flask, washing with a little distilled water. Add 2 cc's of ferric indicator to the filtrate and titrate with a standard sulfocyanate solution, made by diluting the ordinary standard solution to such an extent that 100 cc's after diluting shall be equivalent to 0.1 gram of silver. Note: multiply the standard by 1000 and dilute 100 cc's of the standard solution to the resulting number of cc's. Thus, with a solution of a standard 0.495, dilute 100 cc's to 495 cc's, using, of course, distilled water. End note. Calculate the weight of silver found by sulfocyanate and add it to the weight which 100 cc's of the salt solution will precipitate. An advantage of this modification is that an excess of 15 milligrams may be determined as easily and exactly as 5. In standardizing the salt solution, then, weigh up, say, 1.0150 gram of pure silver, dissolve and titrate. Suppose 13.5 cc's of sulfocyanate required, then these are equivalent to 0.0135 of a gram of silver. 100 cc's equivalent to 0.1. The silver precipitated by the salt is 1.0150 minus 0.0135, i.e. 1.0015 gram, which is the standard. Application of the method to assays for arsenic. If silver nitrate be added to a neutral solution of an arsenate of one of the alkali metals, silver arsenate Ag3AsO4 is thrown down as a dark red precipitate. If, after adding excess of silver nitrates to ensure a complete precipitation, the arsenate of silver be filtered off, the weight of the arsenic could be estimated from the weight of silver arsenate formed. But this may be done much more conveniently by dissolving the precipitate in nitric acid and titrating with sulfocyanate. The silver found will be to the arsenic present as 324, 108 times 3, is to 75. The mineral is best treated by the method given in the third paragraph on page 382. Reader's note in the first part of chapter 17, end reader's note. But the solution, after being acidified with nitric acid, should be made exactly neutral with ammonia. A small excess of silver nitrate should then be added, and since acid is liberated in the reaction, the liquor must again be neutralized. Note: HNA2ASO4 plus 3 AgNO3 yields Ag3ASO4 plus HNO3 plus 2NaNO3. End note. The precipitate must then be filtered off and washed with distilled water. Then dissolve it in the paper by slowly running over it 20 cc of dilute nitric acid. Wash the filter with distilled water, collecting with the filtrate in a small flask. Add 2 cc of ferric indicator and titrate. If the sulfocyanate solution be made up with 11 or 12 grams of the potassium salt to the litre, and be then standardized and diluted so that for 100 cc it shall equal 1.08 gram of silver, see page 38, reader's note, chapter 4, Volumetric Assays, end reader's note, then it will also equal 0.25 of a gram of arsenic, As. Except for ores rich in arsenic, it will be better to work with a solution 1/2 this strength. The standard as calculated from an experiment with pure silver should be checked by another using pure resublimed white arsenic, As2O3, which contains 75.75% of the metal. The quantity of white arsenic taken, 0.1 or 0.2 of a gram, should contain about as much arsenic as will be present in the assays. It is converted into sodium arsenate by evaporating to a small bulk with nitric acid and neutralizing with soda. The precipitation and titration of the silver arsenate should be exactly as in the assays. The difficulty of the method is in the neutralizing, which has to be very carefully done, since silver arsenate is soluble in even faintly acid solutions. 1 drop of nitric acid in 100 cc of water is enough to produce an absolutely worthless result, and an excess of acid much less than this is still very prejudicial. The addition of a little sodium acetate to the solution after the final neutralizing has a good effect. Arsenic in mispickle. Weigh up 0.250 gram of the finely powdered ore and place in a Berlin crucible about 1 1/4 or 1 1/2 inch in diameter. Treat with 10 or 12 drops, 1 drop at a time, of strong nitric acid. Warm very gently, but avoid much heating. Put on a thin layer of nitre, and rather more than half fill the crucible with a mixture of equal parts of soda and nitre. Heat quickly in the blowpipe flame, and when the mass is fused and effervescing, withdraw and allow to cool. Boil out with water, filter and wash. Insert a piece of litmus paper and cautiously neutralize with nitric acid, using ammonia to neutralize any accidental excess of the acid. Add a gram or so of ammonium nitrate and silver nitrate in excess, neutralize again with ammonia, and add 2 or 3 grams of sodium acetate. Filter off the precipitate, wash and titrate. In the fusion, care should be taken to avoid much effervescence. An excess of the soda mitigates this, and the operation should be stopped as soon as the whole has entered into fusion. Colorimetric determination. There is, properly speaking, no colorimetric method, but the following, which is sometimes used, is based on similar principles. It is useful for the determination of small quantities of silver in substances which yield clear solutions with nitric acid. Dissolve a weighed quantity of the substance in nitric acid, and dilute to a definite bulk. Divide into 2 equal parts. To one, add a drop or 2 of dilute hydrochloric acid, stir and filter. To the other, add a similar amount of dilute acid, and then to the filtered portion run in from a burette standard silver nitrate, 1 cc equals 0.5 mg silver, until the solutions are equally turbid. Calculate in the usual way. End of section 12. Section 13 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 9. Silver, Gold, Platinum, Cyanides, Mercury. Part 5. Gold. Gold occurs in nature chiefly as metal. It always contains more or less silver, and in alluvial sands, etc., may be associated with platinum and iridium. Gold is insoluble in hydrochloric or nitric acid, but is dissolved by aqua regia, or by solutions of iodine, bromine, or chlorine. It is taken up by mercury, forming an amalgam, from which the mercury may be driven off by heat. When gold occurs in particles of any size, it is readily detected by its appearance, but when finally disseminated through a large quantity of rock, it is separated and detected by the amalgamation assay, described below, or by a process of washing somewhat similar to vanning, or by the following test. Powder and, if necessary, roast 50 to 100 grams of the ore. Put on it 3 or 4 crystals of iodine and enough alcohol to cover it. Allow to stand for half an hour. A piece of filter paper, moistened with the liquid and burnt, leaves an ash with a distinctly purple tint if any gold is present. It is better, however, to filter off the solution, evaporate, and ignite. Then either take up with mercury and ignite the amalgam so as to get a speck of the metallic gold, or treat with a few drops of aqua regia and test the solution with stannous chloride. A purple coloration indicates gold. Amalgamation assay. This does not attempt to give the total produce of gold, but rather the quantity which can be extracted on a large scale. Therefore, it should imitate as closely as possible the process adopted in the mine or district for extracting the metal. Take 2 pounds of the ore in powder and roast. Make into a stiff paste with hot water and rub up for an hour or so with a little mercury. Wash off the sand carefully and collect the amalgam. Drive off the mercury by heat and weigh the residual gold. It is best to cupel it with lead before weighing. In an experiment on a lot of ore which contained 0.189 of a gram of gold, 0.179 of a gram was obtained by the above process, equal to about 94.5% recovered. With ores generally, the yield may be from 80 to 90% of the actual gold present. Dry assay. The dry assay of gold ores resembles in its main particulars the dry assay for silver by the crucible method, and for much that is of importance in its discussion the student is referred to what is written under silver on pages 90 to 113. Reader's note in section 9 of this recording. End reader's note. Size of assay charges. Gold ores rarely contain more than a few ounces, often only a few pennyweights of gold to the ton. Consequently, the button of gold obtainable from such quantities of ore as may be conveniently worked by assaying methods is often so small as to require more than ordinary care in its manipulation. 1 milligram of gold forms a button of about the size of one of the full stops on this page, and compared with 1,000,000 similar particles of quartz, about 4 ounces, represents a produce of 1/4 of an ounce to the ton, a proportion such as the assayer is frequently called on to determine. It is evident, therefore, that a charge of half an ounce or less of the ore, such as is usual with silver ores, would demand of the worker both skill and care in the handling of the minute quantity of gold to be obtained from it. Fortunately, the work is simple and precise, so that in practised hands and with only a 5-gram charge, the assay of a 5 pennyweight ore is practicable. With so small a charge, however, the result is barely perceptible on a sensitive balance. The button of gold should be measured under a microscope. It follows, therefore, that larger charges of, say, 50, 100 or even 200 grams have an advantage in that they lessen the strain on the worker's attention and, except in the case of the poorest mineral, bring the button of gold within the scope of the balance. On the other hand, the inconvenience of the larger charges lies in the amount of fluxes and consequent size of the crucibles required to flux them. Sampling. A further consideration in favour of the larger charges is the matter of sampling. In preparing his ore, the student should ask himself what reasonable expectation he has that the portion he puts in the furnace will be of average richness. The larger charges are likely to be nearer than the smaller ones to the average of the parcel of ore from which they are taken. In explanation of this, let us suppose a large heap of 5 pennyweight ore in sand of the coarseness of full stops and containing all its gold in particles of 1 milligram, as uniformly distributed as care and labour in the mixing can accomplish. Such a heap could not possibly occur in practice, but it will serve for purposes of illustration. Now, 1 ton of the sand, however taken, would contain appreciably the same quantity of gold as any other ton, for a ton would contain about 8,000 particles of gold, and even if 2 separate tons differed by as much as 100 particles, which they are just likely to do, this would mean only a difference of 1 or 2 grains to the ton. On the other hand, 2 portions of 14 pounds, which should contain on the average 50 particles of gold, are likely enough to differ by 10 particles, and this, calculated on a ton, means a difference of 1 pennyweight. It is easy to see that something like this should be true, for on calculating the 14-pound lot up to a ton, the deviation from the average, whatever it may be, is multiplied by 160. Whereas if the ton were made up by adding 14-pound lot to 14-pound lot up to the full tale, then a large proportion of the errors, some being in excess and some in defect, would neutralize each other. An average which is practically true when dealing with thousands, and perhaps sufficiently exact with hundreds, would be merely misleading when applied to tens and units. Reasonable safety in sampling, then, is dependent largely on the number of particles of gold in the charge taken, and the risk of an abnormal result is less the larger the charge taken. By doubling the charge, however, we merely double the number of particles. Powdering finely is much more effective, for since the weight of a particle varies as the cube of the diameter, halving the diameter of the particles increases their number 8-fold. If, now, we modify our illustration by assuming the particles to have only 1/6 the diameter of a full stop, which would represent a powder of a fineness not unusual in ores prepared for assaying, we should multiply the number of particles by 200. 6 times 6 times 6 equals 216. We should then reasonably expect a 14-pound parcel of the powder to give as safe a sample as a ton of the sand would give, and portions of a size fit for crucible work, say 50 or 100 grams, would be as safe as 10 or 20-pound samples of the coarser stuff. For example, 60 grams of such powder would contain, for a 5 pennyweight ore, about 100 particles, and in the majority of cases the error due to sampling would be less than 10 or 12 grains to the ton, and would only occasionally exceed a pennyweight. With richer ores, the actual deviation, stated as so much to the ton of ore, might be greater, but it would represent a smaller proportion, stated in percentage of the gold actually present, and would ultimately fall within the limits of unavoidable error. It will be seen that the size of the quartz particles has no direct bearing on the argument, and in fact the coarseness of the quartz only interferes by preventing the uniform mixing of the sand, and by binding together several particles of gold. In this last case, particles so united must of course count as one larger particle. Now, there are some natural ores in which the gold particles are all very small. With these, fine powdering and mixing yields a product from which a sample may be safely taken. Then again, in tailings, before or after treatment with cyanide, we have a similar material, inasmuch as the coarser gold has been removed by previous amalgamation. With these, it is not unusual to take the portion for assay without any further powdering, since they are poor in gold and have already been stamped and passed through a sieve of, say, 30 holes to the inch linear. But there are other ores, in lump showing no visible gold, which contain the gold in all possible degrees of fineness, from, say, prills of a milligram or so, down to a most impalpable powder. The treatment of these cannot be so simple and straightforward. Suppose a parcel of 1000 grams, say 2 pounds, of such ore in fine powder, containing on an average 1 particle of 1 milligram, note the presence or absence of which makes a difference of 0.6 of a pennyweight on the ton, end note, 10 others of about 0.5 of a milligram, note each representing 0.3 of a pennyweight, end note, and 100 others which are too coarse to pass through an 80 sieve, and having an average weight of 0.1 of a milligram, note each 0.06 of a pennyweight, end note, and that the rest of the gold, equivalent altogether to 2 ounces to the ton, is so finely divided that a charge of 50 grams may be taken without any considerable risk of its interfering with the sampling. Then, in a 50-gram charge, there would be 1 chance in 20 of getting the milligram particle, in which case the result would be 12.35 pennyweights too high. On the other hand, if it were not present, the result would on this account be 0.65 of a pennyweight too low. Of the 10.5 milligram particles, it is as likely as not that one will be present, and its presence or absence would cause an error of 3.3 pennyweights, more or less. Of the 100 particles of 0.1 of a milligram, there would probably be from 3 to 7, instead of 5, the proper number. This would mean a variation of 2.6 pennyweights from the true proportion, so that the probable result would range about 5 pennyweights more or less than the 2.5 ounces, which is the true produce, and there are possibilities of astounding results. It is true that the majority of the results would be well within these limits, and now and again the heart of the student would be gladdened by a beautiful concordance in duplicate assays. Nevertheless, there can be no reasonable expectation of a good assay, and to work in this way on a 50-gram charge would be to court failure. The coarse gold must ruin the assay. The difficulty may be met by concentrating the whole of the coarse gold in a small fraction of the ore, by sifting and making a separate assay of this fraction. A portion of the ore of about 1000 grams is ground to a very fine powder, and passed through an 80 sieve, regrinding when necessary, until only 20 or 30 grams is left of the coarser powder. This is mixed with fluxes and carried through as a separate assay. The sifted portion is thoroughly mixed, and a portion of it, say 30 or 50 grams, taken for assay. The weights of the two portions must be known, and care must be taken that nothing is lost in the powdering. The method of calculating the mean result from the two assays is shown on page 109. Reader's note in section 10 of this recording. End reader's note. In this way of working, there is no advantage in continuing the grinding until the coarser fraction is reduced to a gram or so, rather the contrary, and rubbing on until all the gold is sent through the sieve is to be distinctly avoided. The student must bear in mind that what he is aiming at is the exclusion of all coarse gold from the portion of ore of which he is going to take only a fraction. The question of the smaller sampling of gold ores has been dwelt on at considerable length, as befits its importance, in order that the student may be impressed with a sense of its true meaning. Sampling is not a mystery, nor does the art lie in any subtle manner of division. It is, of course, absolutely necessary that the stuff to be sampled shall be well mixed, and the fractions taken so that each part of the little heap shall contribute its share to the sample. Moreover, it must be remembered that tossing about is a poor sort of mixing, and that everything tending to separate the large from the small, the light from the heavy, or the soft from the hard, as happens in sifting, must be avoided, or, if unavoidable, must be remedied by subsequent mixing. With a well-taken sample, we may rely on a great majority of our results falling within normal limits of error, but nothing can be more certain than that in a moderately large experience we shall get, now and again, deviations much more considerable. These erratic assays can only be met by the method of working duplicates, which call attention to the fault by discordant results. Such faulty assays should be repeated in duplicate, so that we may rest the decision on 3 out of 4 determinations. The likelihood of 2 very faulty assays being concordant is remote, but with very important work, as in selling parcels of ore, even this risk should be avoided, as concordance in these cases is demanded in the reports of 2 or more assayers. The following actual reports on a disputed assay will illustrate this. A. 5 ounces 1 pennyweight. B. 5 ounces 10 pennyweights 12 grains. C. 5 ounces 11 pennyweights. D. 5 ounces 11 pennyweights 12 grains. The mean result of several assays, unless there be some fault in the method, will be very fairly exact, and individual assays with an uncertainty of 1 in 20 may, by repetition, have this reduced to 1 in 100 or less. Assay tons, etc. Having decided on taking a larger or smaller portion, the exact quantity to be used will be either some round number of grams, such as 50 or 100, easily calculable into percentage, or it will be that known as the assay ton. See page 13. Reader's note in section 1 of this recording. End reader's note. Or some simple multiple or fraction of it, which is easily calculable into ounces. The reports, too, are at least as often made as ounces in the short ton of 2,000 pounds as on the more orthodox ton of 2,240 pounds. Now the short ton is equal to 29,166.6 troy ounces, and the corresponding assay ton is got from it by replacing ounces by milligrams. The advantage of its use is that if 1 assay ton of ore has been taken, the number of milligrams of gold obtained is also the number of ounces of gold in a ton of the ore, and there is absolutely no calculation. Even if half an assay ton has been taken, the only calculation needed is multiplying the milligrams by 2. On the other hand, with the charge of 2 assay tons, the milligrams need halving. Where weights of this kind, i.e. assay tons, are not at hand, they may be easily extemporized out of buttons of tin or some suitable metal, and it is better to do this than to array out the grams and its fractions at each weighing. The sets of assay tons, however, are easily purchased. As stated on page 13, the assay ton for 2,240 pounds is 32.6667 grams, and for the short ton 29.1667 grams. If, however, the round number of grams be used and the result brought by calculation to the produce on 100 grams, the conversion to ounces to the ton may be quickly effected by the help of the table on page 107. As this table only deals with the ton of 2,240 pounds, it is supplemented here by a shortened one, dealing only with the produce of 100 grams, and stating the result in ounces troy to the short ton of 2,000 pounds. Reader's note: this table has been omitted. End reader's note. Estimation of small quantities of gold by the balance. In estimating minute quantities of gold, there are 1 or 2 points of importance to an assayer only in this assay, where they will often allow one to avoid the working of inconveniently large charges. One of these is known as weighing by the method of vibrations. Suppose a balance at rest in perfect equilibrium, with the pointer exactly over the middle point of the scale. Let the scale be a series of points at equal distances along a horizontal line, Then, if a small weight be placed on one pan, the pointer will deviate from its vertical position and come to rest opposite some definite part of the scale, which will depend upon the magnitude of the weight added. The law determining this position is a very simple one. The deviation, as measured along the points of the scale, varies directly as the weight added. For example, with an ordinarily sensitive balance, such as is used for general purposes, 1 milligram will move the pointer along, say, 3 divisions of the scale. Then 2 milligrams will move it 6 divisions, half a milligram, 1½ divisions, and so on. Of course, with a more sensitive balance, the deviations will be greater. Now, the point at which the needle comes to rest is also the middle point about which it vibrates when swinging. For example, if the needle swings from the 3rd to the 7th division on the right, then it will come to rest on the 5th. Note 7 plus 3 divided by 2, end note. In working by this method, the following conventions are useful. Always place the button to be weighed on the left pan of the balance, the weights on the right. Count the divisions of the scale from the centre to right and left, marking the former plus and the latter minus. Thus, -5 is the 5th division to the left. Then the position of rest is half the algebraic sum of 2 readings. For example, let the readings be 7 to the right and 3 to the left. Then +7 minus 3 divided by 2 equals +2. The mean division is the 2nd division to the right. If the student will place himself in front of a balance and repeat the following observations, and replace the figures here given by his own, he will have no difficulty in grasping the method. First, determine the bias of the balance. Suppose the unloaded balance swings +1.25 and -1. The bias then is 1.25 minus 1 all divided by 2 equals +0.125, or 1/8 of a division to the right. Now, having put on the button to be weighed, let the readings be +7.5 and +9.25, and 7.5 plus 9.25 all divided by 2 equals +8.375. Then the effect of the button has been to move the pointer from +0.125 to +8.375, or 8.25 divisions to the right. We should therefore add the weight equivalent of 8.25 divisions to the weights, whatever they may be, on the right-hand pan of the balance. If the divisions were to the left, minus divisions, we should subtract. The value of one division is easily determined. Suppose the button in the example were a 1 milligram weight, then we should have found that 1 milligram equals 8.25 divisions. Therefore, one division equals 0.121 milligrams. This method of working adds very considerably to the power of a balance in distinguishing small quantities. End of section 13. Section 14 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 9. Silver, Gold, Cyanides, Platinum, Mercury. Part 5. Gold. By the microscope. The use of the microscope also is a real advantage in estimating the weights of minute buttons of gold, where there is no undue risk in sampling, and where an error of, say, 1 in 20 on the quantity of gold is tolerable. For ores with copper, lead, zinc, etc., as well as for tailings rather poor in gold, this leaves a wide field of usefulness. The method is described on page 440. Reader's note. In Appendix B. End reader's note. But the description needs supplementing for those who are not accustomed to the use of a microscope. Reader's note. The figure referred to in the following sentences, figure 44A, part A, consists of a longitudinal section through a microscope eyepiece. The eyepiece consists of 2 tubes, a narrow one screwing into a slightly wider one at A. The open end of the narrow tube has an aperture for the eye, and just within it a hemiconvex lens. The wider tube has a very narrow annular diaphragm just beyond where the narrow tube screws into it, marked as lower case b, which holds a glass disc. Then at the far end of the wider tube there is a second hemiconvex lens. End reader's note. The eyepiece of a microscope, figure 44a, part A, unscrews at A, showing a diaphragm at B, which will serve as a support for an eyepiece micrometer. This last, capital B, is a scale engraved on glass, and may be purchased of any optical instrument maker, though it may be necessary to send the eyepiece to have it properly fitted. When resting on the diaphragm, it is in focus for the upper lens, so that on looking through the microscope the scale is clearly seen in whatever position the instrument may be as regards the object being looked at. Suppose this to be a small button of gold on a shallow flat watch glass on the stage of the microscope. Bring the button under the objective, i.e. the nose of the microscope, which should be about 1/4 inch above the watch glass. Then, looking through the instrument, raise the tube until the button of gold, or at least some dust on the glass, comes into focus. If the button is not in the field, rest the thumb and index fingers, using both hands, on the edge of the watch glass, pressing lightly but steadily, and give the glass a slow, short, sweeping motion. The button will perhaps appear as an ill-defined blackness, because not quite in focus. Bring this into the centre of the field. Raise or lower the microscope until the button appears with sharp outlines. If the scale does not cover the button, rotate the eyepiece. This will bring the scale into a new position. Since the divisions over the button are less distinct than the others, it is best to read the latter. Thus, in figure 44b, there are 36 divisions on one side of the button and 35 on the other, making altogether 71. Reader's note. Figure 44b simply shows a scale 80 divisions long, with a small circular button at its centre. End reader's note. The whole scale is 80, therefore the diameter of the button is 9 divisions. The value of each division obviously varies with the magnifying power employed. With most microscopes there is a telescopic arrangement whereby the tube may be lengthened. If this be done and the button again brought in focus, it will be seen that as measured on the scale the button is much larger than before. It is evident, therefore, the micrometer must always be used in the same way. The method given in the appendix, page 440, for finding the value of the scale when gold buttons are to be measured is easy and satisfactory. When the button of gold is so small that there is considerable risk of losing it in transferring to a watch glass, it may be measured on the cupel, but for this purpose it must be well illuminated. This is best done by concentrating light on it with a lens, or with what comes to the same thing, a clean flask filled with water. Most assayers, however, using a micrometer in this way, would like to know its absolute value. To do this, a stage micrometer must be purchased. This is like an ordinary microscope slide, and when looked at through a microscope it shows, figure 44c, lines ruled on the glass at distances of tenths and hundredths of a millimetre, 10 of each, so that the full scale is 1.1 millimetres. Reader's note. Figure 44c shows the circular view through the microscope, with 11 vertical spaced out lines on the stage micrometer, with the finely divided eyepiece scale lying horizontally across it. The left-hand end of the scale touches the leftmost of the vertical lines, the right-hand end of the scale lying beyond the 11th line. End reader's note. In the case illustrated, 60 divisions of the scale in the eyepiece are just equal to the 1.1 millimetres, therefore one division equals 0.0183 millimetres. A cube of this diameter would contain 0.0000061285 cubic millimetres. Note 0.0183 times 0.0183 times 0.0183. End note. The corresponding sphere is got by multiplying by 0.5236. This gives 0.0000329 cubic millimetres. The weight of 1 cubic millimetre of water is 1 milligram, and since gold is 19.2 times as heavy as water, specific gravity equals 19.2, the contents in cubic millimetres must be multiplied by 19.2. This gives 0.0000616 of a milligram as the weight of a sphere of gold measuring 1 division. If every result had to be calculated in this way, the method would be very laborious, but having the figures for the first division, those of the others may be calculated by multiplying by the cube of the corresponding number. Thus, for the third division, 3 times 3 times 3 equals 27, the content of the cube, 0.0000061285 times 27, is 0.0001655 cubic millimetres. The content of the sphere, 0.000032009 times 27, is 0.0000866 cubic millimetres, and the corresponding sphere of gold, 0.0000616 times 27, is 0.00166 of a milligram. With the help of a table of cubes, the whole calculation for 25 or 30 divisions may be made in half an hour, and the results, preserved in the form of a table, will simplify all future work. Assay operations. The actual work of the assay resolves itself into 3 operations. 1. The fusion of the ore and concentration of the fine metal, i.e. gold and silver, in a button of lead. 2. The cupellation of the lead, whereby a button of fine metal is obtained. And 3. The parting of the gold, which separates it from the accompanying silver. The following description takes the order as here given, but the student, in learning the method, should first practice cupellation, if he has not already done so. Next, he should practice the separation of gold from silver, taking known weights of fine gold. Reader's note. Described in section 6 of this recording. Reagents, etc. End reader's note. Varying from 0.5 or 0.3 of a gram down to quite minute quantities, and not resting satisfied until a sensitive balance can barely distinguish between the weights of gold taken and found. It may be noted here that if he has not a flatting mill at his disposal, then for large buttons it is better to make an alloy with 8 or 9 parts of silver to 1 of gold, and attack it with acid without previous flattening, rather than accept the risk and labour of beating out a less easily attacked alloy to the necessary thinness with a hammer. It is only after a sense of security in gold parting has been acquired that the attack of an ore can be profitably accomplished, and even then simple and easy ores should be first taken, passing on to others more difficult, either because of a more complex mineral composition or a difficulty in sampling. Concentration of the fine metal in lead. The best flux for quartz, which makes up the earthy matter of most gold ores, is soda, and this is best added as carbonate or bicarbonate. By theory, 50 grams of quartz will require 88.5 grams of the carbonate or 140 grams of the bicarbonate to form sodium silicate, which is a glassy, easily fusible substance, making a good slag. Note: SiO2 plus Na2CO3 yields CO2 plus Na2SiO3, and SiO2 plus 2NaHCO3 yields 2CO2 plus Na2SiO3 plus H2O. End note. If the bicarbonate is used and heat is applied gradually, steam and carbonic acid are given off at a comparatively low temperature, and the carbonate is left. At a higher temperature, about 800 degrees centigrade, or a cherry red heat, the carbonate fuses, attacking the quartz and giving off more carbonic acid. As the heat increases and the attack on the quartz, which of itself is infusible, becomes complete, the whole mass settles down to a liquid sodium silicate, which is sufficiently fluid to allow the gold and lead to settle to the bottom. The fluid slag does, to a certain extent, dissolve some of the crucible, but not seriously. In a perfect working of this experiment, the first evolution of gases, steam and carbonic acid, should be gentle, so as to run no risk of its blowing the fine powder out of the crucible, and the heat at which the second evolution of carbonic acid is produced should be maintained until the reaction is completed, so that there may be little or no formation of gas in the fused mass to cause an effervescence which may force some of the charge over the edges of the crucible. Of course, in practice the ideal fusion is not attained, but there is no difficulty in approaching it closely enough to prevent the charge at any time rising above the level it reached at first in the crucible, and this should be accomplished. It is usual with quartzose ores to rely mainly on the action of carbonate of soda, but not entirely. Litharge is also used. It forms, on fusion with quartz, a silicate of lead, which is a yellow glass easily fusible, and more fluid in the furnace than silicate of soda is. By theory, 50 grams of quartz would require 186 grams of litharge. Note: PbO plus SiO2 yields PbSiO3. End note. The reaction takes place without evolution of gas, and in its working the only point is to so regulate the heat that the litharge shall not fuse and drain under the unattacked quartz, leaving it as a pasty mass on the surface. Now, if in making up a charge for 50 grams of ore we took 100 grams of bicarbonate of soda, equivalent to about 63 grams of the carbonate, this being 5/7 of 140 grams, which by itself would be sufficient, leaves 2/7 of the quartz to be fluxed by other reagents. 2/7 of 186 grams, say 52 grams, of litharge would serve for this purpose. But if we used 10 grams of borax, which has a fluxing action about equal to that of the litharge, then 40 grams of the latter, or, making an allowance for the quartz being not quite pure, say 35 grams, will suffice. The fluxes, then, for the 50 grams of ore would be bicarbonate of soda 100 grams, litharge 35 grams, and borax 10 grams. We could decrease any of these and proportionately increase either or both of the others, and still rely on getting a fusible slag, which is the whole of the function of a flux, considered simply as a flux. It should be remembered, however, that the slag is a bisilicate or acid slag, and that its acid character is increased by increasing the proportion of borax. But in addition to the fluxes, there is required about 30 or 40 grams of lead to collect the silver and gold. This is best added as litharge, say 40 grams, and flour, 4 grams, or charcoal powder, 2 grams. See pages 93 and 94. Reader's note, section 9 of these recordings. The first chapter on silver, gold, cyanides, platinum, mercury. End reader's note. The full charge then would be ore, 50 grams, bicarbonate of soda, 100 grams, litharge, 75 grams, borax, 10 grams, flour, 4 grams. These should be mixed, placed in a suitable crucible, a G. Battersea round will do, and heated at first at a red heat, but finally much hotter, so as to get a fluid and clean slag. When the charge has been in tranquil fusion for some little time, take it out and pour it into an iron mould. When cold, detach the button of lead. The slag should be glassy, all through alike, and easily separable from the metal. With ordinary ores, this slag may be considered as free from gold. In an experiment in which 90 milligrams of gold were added, the full amount was obtained from the lead produced by the first fusion. But in certain cases, more especially where large amounts of metallic oxides are present, the slag is not so clean, and with these the slag should be powdered, mixed with 40 grams of litharge and 4 of flour, and melted again. It is an advantage to add a small prill of, say, 2 or 3 milligrams of silver to the charge, as it ensures a visible product in the cupellation. Indeed, this last precaution is a good one to be taken wherever there is reason to expect very small buttons. It has the further advantage that if the quantity of silver necessary for inquartation is known, the right quantity may be added here so as to save a subsequent operation. Ores containing oxides of iron. Of the metallic oxides likely to be present in a slag, oxide of iron is the most important. Gold is occasionally found in a matrix of this substance, and in the assay of concentrates largely made up of pyrites, this oxide will be formed in the preliminary calcination. Now, the lower oxide of iron, ferrous oxide, FeO, is easy to deal with. Fused borax will dissolve about its own weight of it, and a silicate of soda, such as makes up the bulk of a slag in a gold assay, will take up at least half as much. But the higher oxide, ferric oxide, Fe2O3, is more refractory. Even 6 parts of borax yields a poor product, and slags with any considerable percentage of it are not satisfactory. A student attempting to recover gold from some hematite, in which there was about half an ounce of the metal, found in the slag nearly a gram of gold, although in the first fusion the slag appeared perfectly fluid. There is, however, no difficulty in getting good slags, even with large quantities of iron. For example, with 50 grams of ferric oxide, 10 of quartz, 30 of borax, 30 of soda, 50 of litharge and 7 of flour, the result was quite satisfactory. Note, here and elsewhere in this article, when a flux is spoken of as soda, the bicarbonate is meant. End note. So too was 25 of quartz, 50 of soda, 50 of litharge and 7 of flour. It is well, however, in such cases, to have an ample proportion of flux and to aim at a larger button of lead than usual, by increasing the proportion of flour or charcoal. Note, see also page 91. Reader's note, under pot assays in section 9 of this recording. End reader's note. End note. A charge used on the rand for roasted concentrates, which we may roughly speak of as quartz and ferric oxide, is 1 assay ton, about 30 grams, each, of ore, soda and borax, and 1½ assay ton of litharge, and 2 grams of charcoal. Whilst for the same material, from which most of the gold has been extracted by chloridizing, 2.5 tons each of ore, borax and soda, 4 of litharge, and 4 grams of charcoal are needed. This quantity requires a large crucible. Note, I. Battersea, round. End note. In this, the proportion of silicate of soda and borax counted together is to the oxide of iron as 4:1, on the supposition that the quartz and oxide of iron of the ore are in about equal quantities. But in the larger charge especially, much oxide of lead would also remain as a flux. Ores containing sulphides. In assaying ores containing a large proportion of pyrites or mispickel, or both, the best plan is to take a portion and calcine so as to convert it into a product of the kind just considered. The weighed portion of ore should be placed in a clean crucible and be heated to incipient redness. With pyrites, the first effect is to drive off about half the sulphur as vapour, which burns as flame over the ore. At this stage, care should be taken that there is no great increase of temperature, otherwise there may be more or less fusion, which would spoil the operation. When the sulphur flame ceases, the solid sulphide of iron burns with visible incandescence, and the charge should now be stirred with a flattened iron rod, so as to expose fresh portions to the air. The top of the furnace must be open, so that air may have free access to the crucible. When stirring is no longer followed by visible burning, the heat may be raised to full redness. The crucible is then lifted out, the stirrer still resting in it, and if the charge gives off no odour of burning sulphur, it is shaken out into an iron mortar and mixed with the fluxes, taking care to clean the stirrer in the mixture. The charge is then replaced in the crucible in which the roasting was done, and fused in the furnace. The resulting button of lead is cupelled for fine metal. Ores rich in sulphides requiring this treatment are frequently concentrates. For their assay, take 1 assay ton, 30 grams, calcine and mix with an equal weight of soda and of borax, 30 grams each, and half as much again of litharge, 1.5 tons, or 45 grams, and with 2 grams of charcoal, or 5 grams of flour. Where the sulfides are present in smaller proportion, 10% or less, they may be taken as serving the purpose of flour or charcoal. See page 95. Reader's note. In section 9 of these recordings, the first section on silver, gold, cyanides, platinum, mercury. End reader's note. The sulphur and iron are oxidized at the expense of the litharge, with a consequent separation of lead as metal. If the proportion of sulfides is not sufficient to give a large enough button of lead, some charcoal or flour should be added. On the other hand, if they are in small excess, and give a button of lead somewhat sulphury, i.e. hard and brittle, it may be remedied by the judicious addition of nitre. This last reagent, however, should not be used in large quantity. A plan much used to prevent sulphury buttons is to insert an iron rod or a nail in the charge in the crucible. The iron takes the sulphur, forming a sulphide of iron, which in moderate quantity does not form a separate layer of matte, but dissolves in the slag. A slag formed of 50 grams of quartz, 100 soda, and some borax may take up in this way some 10 or 12 grams of sulphide of iron. If, however, an ore gives a layer of matte or speise, it is best to repeat the assay by the method of calcining before fusion. Cyanide charges, etc. In assaying the tailings which are to be treated in a cyaniding plant, the following charge is used. Tailings, 3 assay tons or 100 grams. Litharge, 4.5 assay tons or 150 grams. Soda, 4.5 assay tons or 150 grams. Borax, 0.75 of an assay ton or 25 grams. The sand is assayed without any further crushing, and the assay is made in duplicate. The residues after treatment with cyanide, differing from the tailings merely in being poorer in gold, because of the extraction by the solution of cyanide, are run down with the same fluxes in the same relative proportions. But 4 charges of 2.5 assay tons, say 75 grams, are worked, and 2 of the resulting buttons are scorified together and then cupelled, etc., so as to give duplicate assays on charges of 5 assay tons. This is one of the cases in which it is desirable to add a small portion of silver before cupelling. In assaying the cyanide liquors for gold, 2 assay tons of the liquor are measured out, 58.3 cc's for the ton of 2,000 pounds, 65.3 cc's for the other, and are evaporated to dryness in a lead dish weighing about 35 grams. Such a dish is easily extemporized out of a piece of lead foil, if the ordinary vessel is not at hand, but care must be taken that the lead is free from gold. The dish with the dried residue is then scorified, and the resulting button of lead is cupelled. In some cases, the fusion of the ore may be replaced by a treatment with solution of cyanide of potassium, and the gold recovered from the solution in the way just described. For this purpose the ore should be in not too fine powder, otherwise there will be great difficulty in filtering. A sand which will pass a 30 sieve and having no large proportion of very fine stuff will do. Not less than 200 grams should be taken, and as an extraction apparatus a bell jar capable of holding half as much again may be used. Such a jar may be extemporized by cutting off the bottom of a bottle by leading a crack around it with a red-hot poker, or a lamp chimney will serve the purpose. The smaller mouth of the jar is closed by perforated cork, provided with a clipped tube, after the manner of a burette. Note, see figure 44D, end note. Reader's note. A retort stand and clamp support a wide, open-topped cylindrical container over a beaker of about the same diameter. The cylinder, bell jar, bottle or lamp chimney, is closed off at the lower end, with a tube held closed with a clip. End reader's note. In the jar, just over the cork, put a plug of loose asbestos or glass wool, or a piece of sponge, to act as a filter. A layer of broken glass, coarse at the bottom and fine at the top, will serve the same purpose. On this, place the charge of ore to be extracted. Prepare a solution of cyanide of potassium in water, with 5 or 10 grams of the salt to the litre. It may be that the whole point of the assay depends on the solution being of a definite strength, as for example where the relative efficiency of solutions of different strengths is being determined, when it will be best to estimate the quantity of cyanide of potassium in the dilute solution by the method given at the end of this article. Note: page 160. End note. Reader's note: in section 17 of these recordings, on cyanides. End reader's note. Pour the cyanide solution onto the ore, letting the first portions to come through run into the beaker, but as soon as the ore is thoroughly wetted, close the clip and allow to stand for several hours. Then, opening the clip, run through more cyanide solution, and then water, so as to wash the gold-carrying liquor thoroughly into the beaker. It is no matter if the liquor is a little bit turbid. Transfer it to a lead dish, evaporate, scorify, and cupel in the usual fashion. The assay of gold-zinc slimes, which is the precipitate formed by zinc acting on cyanide solutions of gold, may be made by wrapping 2 or 3 grams in 40 grams of sheet lead and scorifying, cupelling, etc. The amount of impurity in the stuff varies greatly. It is usually calcined and mixed thoroughly with soda 40%, borax 30%, and sand 10%, and melted in graphite pots. The buttons of bullion obtained are afterwards remelted with borax and run into bars, the fineness of which varies from 600 to 830 thousandths. The bars are sampled by chipping off diagonally opposite corners, or better, by drilling, the drillings being freed from pieces of steel with the help of a magnet. End of section 14.